At 0726 local time on a Tuesday in June 2025, the Russian patrol ship Razul Gamatov detected two faint returns on its radar. They were small, sluggish, and closing from the west across the dark expanse of the Caspian Sea. The crew immediately scrambled to battle stations, their AK-630 cannon pivoting toward the horizon with a mechanical whine that signaled a high-stakes engagement. The crew could not have known in those frantic moments was that a fundamental design flaw etched into the ship's blueprints years ago had already effectively sealed the vessel's fate. These two Ukrainian FP-2 drones had launched hours earlier from a hidden site outside Dnipro, and their first encounter with mortality had actually come from their own side. A Ukrainian Buk M1 surface-to-air missile battery had acquired the drones much earlier that morning. To the radar operators, these low-flying contacts matched the exact profile of the suicide drones they had been hunting all week. The fire control officer's hand hovered over the launch trigger, eyes locked on the flickering green returns on his display. Only a few heartbeats remained until weapons release. Just as he was about to commit a missile worth hundreds of thousands of dollars to destroy his own hardware, he performed a final check of the restricted flight corridors. One of these paths was active during that exact window. The drones were flying precisely within that protected lane at an altitude of about 200 meters. His hand came off the firing authorization so fast he nearly dislodged his headset. They had been less than the blink of an eye away from destroying a high-priority special operation with a friendly missile. The drones passed through the sector without their internal logic ever registering how close they had come to a catastrophic error. Ahead lay 300 kilometers of contested airspace, where every operator on the ground was actually aiming to kill. The drones crossed into occupied territory shortly after, dropping their altitude to less than the height of a standard cell tower, as the frozen landscape of the Donbass scrolled beneath them. At that height, Russian radar systems were virtually blind, not because of some expensive stealth coating, but because of the unyielding laws of physics. Radar energy travels in straight lines, while the Earth itself curves away. If you place a radar antenna on a truck and point it at an object skimming the ground, the mathematical geometry is unforgiving. Beyond a certain distance, the target is effectively hidden below the horizon. The radar can pump out massive amounts of energy, and it will not matter because the signal will pass harmlessly overhead, touching nothing but empty air. The planet itself becomes a physical shield for the intruder. The drone's pre-programmed route exploited every single gap created by this fundamental curvature of the Earth. Advanced air defense batteries near Rostov had theoretical engagement ranges covering hundreds of kilometers, but that assumes targets are at high altitude where the radar can actually see them. Against something hugging the terrain, their effective detection range collapsed to a tiny fraction of its potential. The FP-2's course was a masterclass in navigation, threading between overlapping coverage zones like a needle through fabric. There were safe corridors that narrowed significantly in the tightest sections. If the drones drifted too far in either direction, a nearby battery would paint them instantly. The margins were incredibly thin, but these $500 drones did not need wide margins. They just needed the mathematical logic of the route to be exactly right. The problem was that the airspace was never truly empty, and the drones were about to encounter a mobile threat they could not predict or avoid. By 0334, the tactical situation shifted, as a Russian Mi-18 helicopter lifted off on a routine patrol. Crew was not specifically hunting for small drones. They were watching for sabotage teams near critical rail lines after previous successful strikes by partisans. However, Russian air defense saw both aircraft on the same integrated display, and an observant operator noticed that the smaller contact had been flying a perfectly straight line for over 10 minutes. Nature does not move with that kind of mechanical consistency. Someone directed the helicopter to close the gap for a visual identification. The drones could not change course even if they knew the helicopter was approaching, as they lacked any sensors to detect an incoming threat. The helicopter was not physically pushing the drone, but it was pushing Russian attention directly onto the narrow corridor the drones were using to transit the sector. Search pattern instructed every radar operator in the area to focus their sensors on that specific lane, and to look more closely at faint returns they might otherwise ignore as background static. The safe route had not moved, but the number of eyes pointed at it had grown significantly. Within a few kilometers of a major radar station, the horizon that had been protecting the drones was about to become a liability. At this range, atmospheric effects started to play a role. Temperature inversions can bend radar energy over the physical horizon, extending the detection range unexpectedly. Cold air over warmer ground creates layers that act like lenses, ducting signals into places they should not normally reach. This was the moment where the mission lived or died on a lucky bounce of a radio wave from a system that was never meant to see something this small. A Russian radar sweep found something faint and intermittent, flickering at the edge of detection like a digital ghost. The operator watched it appear and disappear, shifting position in a way that looked like textbook atmospheric clutter. But clutter does not usually hold a consistent heading for several minutes at a time. One phone call to the regional command center would have scrambled fighters and alerted the entire network. But was a flickering ghost worth the paperwork of a false alarm? He logged the contact as a low-confidence return and moved on to other sectors. That single decision saved the mission. The drones flew on toward 300 kilometers of empty steppe. This was a frozen void with no cities and no infrastructure worth protecting. After previous strikes on rear areas, the High Command had learned that they could not protect everything with stationary batteries, so they put fighters in the air instead. High above the grassland, 2 Russian fighters flew a monotonous racetrack pattern. They were burning thousands of liters of fuel every hour just to watch an empty sky. It was expensive and tedious, but it had become an absolute necessity. The radar on these jets could detect a large aircraft from very far away, but against something the size of a small drone, that range collapsed. Radar signature scales with the size of the target, and a small drone is roughly equivalent to a large bird. At very low altitudes, with ground clutter filling the scope, the practical detection range dropped to almost nothing. However, the radar was not the only tool available. The infrared sensor mounted in the nose of the fighters was a passive system. It did not emit anything. It just watched for heat that should not exist in the cold night air. While radar needs reflected energy to function, infrared looks for the source. The drone's engine was pushing exhaust hundreds of degrees hotter than the surrounding air. That temperature differential was as obvious as a lighthouse on a dark coast. The infrared return did not care about radar signature or ground clutter. Heat was heat. The only question was whether the sensor was pointed in the right direction. At that moment, it was not. The sensors looked forward and down, but the drones were dozens of kilometers behind the fighters and thousands of meters below, sitting squarely in the blind spot that exists behind any forward-looking system. The seeker was watching the ceiling while the target was on the floor, but the racetrack pattern would eventually bring the hunters around for a look at their own six, and that was when the game would change. The fighters eventually completed their assigned leg of the patrol and banked into a hard turn at 0529, their wings biting sharply into the thin, frozen air. For several minutes, they had been flying away from the suspected threat, their sensors pointed aft in routine sweeps. Now, as they rolled level again, the geometry of the encounter inverted completely. Instead of increasing distance, they were closing rapidly, their combined velocity compressing the space between them and the unknown contacts. What had been a distant possibility was now a developing engagement. Infrared arrays adjusted automatically, narrowing their focus onto the coordinates where the drones were expected to be. Only a few minutes remained before the closing distance shrank into lethal range. Under each wing, missiles waited in silent readiness, their guidance systems already warming. These weapons were designed for precisely this environment: high-contrast targets against a frozen background, where even small heat signatures stood out like flares in the darkness. Against such systems, slow-moving drones were vulnerable. The fighters' computers continuously refined firing solutions, building probability models with every passing second. Meanwhile, far ahead, the drones flew on without deviation, obediently following their programmed waypoints. Their exhaust plumes streamed faintly behind them, thin threads of heat dissipating into the polar air. They had no awareness that the hunt had reversed. A faint radar anomaly finally appeared on the lead pilot's display, little more than a weak shimmer against the clutter of atmospheric noise. It was subtle enough that many pilots would have dismissed it outright, but its movement was steady, its bearing consistent. That suggested something airborne, something deliberate. The lead pilot narrowed his scan and shifted his aircraft slightly to refine the contact. His pulse quickened as the return strengthened just enough to justify investigation. This was no longer routine patrol. This was now a potential interception. He adjusted his course, easing toward the contact, while his wingman slid smoothly into a combat spread several kilometers off his flank. The maneuver was practiced and instinctive, giving both aircraft overlapping fields of fire and sensor coverage. Together they formed a moving net, ready to collapse around whatever they had found. In the cockpit, warning tones and data overlays blended into a controlled storm of information. Everything indicated that they were closing on something real. The pilots prepared for visual confirmation, but the drone's route included a carefully calculated turn at a specific waypoint, embedded deep in its navigation code. It was a contingency built by engineers who understood that geometry could be as powerful as weapons. As the fighters accelerated, confident in their intercept, the drone reached that waypoint and pivoted precisely on schedule. Its new heading cut perpendicular to the fighter's approach path. In a matter of seconds, the entire engagement geometry shifted. From the fighter's new angle, the drone's exhaust plume was no longer exposed. Its fuselage masked the heat source, blocking the strongest infrared emissions. What had been a bright, trackable signature collapsed into a faint smear barely distinguishable from background noise. The thermal return weakened, then fragmented, then vanished altogether. The lead pilot adjusted his sensor filters, switching modes and narrowing bands, and trying to pull the contact back out of the static, but nothing solid emerged. The sky was full of phantom returns in this environment, and experienced pilots knew better than to chase every ghost. Fuel gauges were beginning to edge into uncomfortable territory. The intercept had taken longer than expected, and the extended maneuvering had burned through reserves. Command guidelines were clear: do not jeopardize recovery for uncertain contacts. With reluctance, the lead pilot disengaged, turning his aircraft back toward base. His wingman followed. Whatever they had nearly caught had slipped through their net. The hunters returned empty-handed, unaware of how close they had come. Below them, the drones cleared the final patrol zone, still hugging the terrain at extremely low altitude. Their navigation systems ticked off waypoints with mechanical precision, indifferent to the danger they had just escaped. A single programmed turn and a few seconds of timing had separated survival from destruction. Ahead, the dark expanse of the Caspian Sea began to appear on the horizon. This was the most dangerous phase of the mission. Over open water, concealment was harder, and enemy sensors were concentrated. Every radar, every receiver, every operator would be watching for them. As the drones descended to skim just meters above the waves, they activated their own seekers and tightened their formation. Sea spray misted against their fuselages. Almost immediately, the patrol ship's radar acquired them. This time, the contact was solid and unmistakable. Alarms sounded on the bridge. But detection alone was not enough. The problem lay in the approach vector. The drones were coming in from an oblique angle that placed them directly outside the optimal firing zone of the ship's main gun, whose barrels pointed forward along the bow. The weapon system was fully automated, a layered network of radar, optical trackers, fire control computers, and hydraulic actuators designed to react faster than any human crew ever could. Once a target was detected, the system calculated intercept vectors, lead angles, and ballistic solutions in fractions of a second. Servo motors whined as the turret slewed, following invisible lines of mathematics through the air. Under ideal conditions, the gun could shred incoming threats before an operator even finished registering their presence. But perfection on paper did not erase the stubborn limits of steel and structure. The ship's own masts, antennas, exhaust stacks, and sensor towers rose like a forest around the turret, creating forbidden corridors where firing would mean striking itself. Engineers had mapped these zones carefully, embedding them into the weapon's control logic as permanent no-fire sectors. The system knew, at every instant, which angles were lethal to the enemy and which were lethal to the ship. From the drone's approach vector, they drifted precisely along the outer boundary of one such sector, skimming the edge of safety by mere degrees. On the radar display, their tracks were crisp and unwavering, bright symbols sliding steadily inward. Fire control software generated perfect solutions again and again, only to discard them milliseconds later as unsafe. Each time, the turret advanced, hesitated, and stopped, its motors pressing uselessly against invisible limits. Inside the Combat Information Center, warning tones began to overlap. Operators watched in mounting frustration as targeting brackets snapped on and off, never quite settling. The automation, built to eliminate hesitation, had instead manufactured it. Locked between threat and self-preservation, the system oscillated in a narrow band of indecision. It could see the drones. It could calculate their destruction. It simply could not execute. The interface displayed a growing stack of rejected firing solutions, each annotated with the same sterile message: obstruction hazard. On the bridge, the captain read the situation instantly. Geometry, not courage or competence, was killing them. He ordered a hard turn, voice sharp and clipped, commanding the helm to swing the ship beneath the incoming trajectory. Engines surged. The rudder bit into the water, The hull leaned heavily to starboard as centrifugal force pressed the crew against railings and consoles. Outside, white water exploded along the flanks as thousands of tons of steel tried to pivot like a much smaller craft. The maneuver was violent, but necessary. Only by changing the ship's orientation could they hope to clear the gun's line of fire. For a few hopeful seconds, it seemed to work. The firing arc widened. The turret crept forward, tracking more aggressively. But geometry is relentless. As the ship rotated, the drone's apparent bearing shifted in perfect synchronization. Their relative position slid sideways across the targeting display, staying just beyond reach. Every meter of lateral movement by the ship was mirrored by a corresponding shift in firing angle. No matter how aggressively the captain maneuvered, the drones remained balanced on the edge of the forbidden zone, like stones poised on a knife's blade. The crew fought the mathematics without realizing it. Helm orders grew sharp, course corrections came faster, throttle adjustments stacked on top of one another, yet each change only fed the same invisible equation. The more desperately they tried to align the gun, the more precisely the engagement geometry denied them. It was not strategy or deception guiding the drones at this stage. It was momentum and vector relationships doing their quiet, merciless work. As the range collapsed to its final margins, the captain authorized emergency overrides. Safety margins were compressed, software tolerances were narrowed, the system was ordered to accept higher structural risk in exchange for a fleeting chance at engagement. Hydraulic pressure spiked as actuators pushed beyond normal limits. The turret shuddered, metal joints protesting. Then, briefly, impossibly, the targeting reticle stabilized. A green indicator flashed on multiple displays. Firing solution valid. For the first time since detection, the system had found a legal path through the maze of constraints. The automated trigger engaged instantly. The cannon roared, its recoil hammering through the deck. Hundreds of rounds tore outward in a dense stream, tracer lines stitching glowing arcs across the darkness. The night lit up in stuttering bursts of orange and white. For a heartbeat, it looked like salvation. But velocity favors the attacker. By the time the rounds reached the calculated intercept point, the drones had already shifted again, sliding laterally by just enough to escape the kill zone. The stream of fire passed behind them, close enough to rattle their frames but not close enough to destroy. Fragments of water and vapor exploded in their wake. The gun tried to correct, but the moment was gone. The arc collapsed. The system reverted to its blocked state. There was no time left. Seconds later, the first $500 drone struck the superstructure at full speed. It punched through layered steel like a thrown spear, rupturing fuel lines and electrical conduits in a spray of sparks and vapor. Fire bloomed instantly, feeding on atomized diesel and oxygen. Alarms screamed. Emergency lighting flickered. Before damage control teams could even mobilize, a second impact followed, tearing through communications arrays and severing command circuits. The ship staggered, still locked in its turn, momentum now carrying it blindly through smoke and flame. At 0700 hours on May 31, 2024, the radar operators inside Russia's most advanced S-400 air defense battery were fighting the kind of boredom that usually precedes a catastrophe. Stationed near Anapa on the Black Sea coast, they were guarding a critical gas terminal that fuels the Russian war machine in the south. On their screens, the morning air traffic looked perfectly routine, but what they could not see was that 3 distinct radar contacts had just dropped below the horizon line, effectively vanishing from the electromagnetic spectrum. In exactly 3 minutes, this quiet morning shift would turn into a masterclass on why billion-dollar air defense systems are sometimes helpless against high school-level physics. 3 Ukrainian FP-5 Flamingo light aircraft, converted into crude cruise missiles, were skimming the wavetops at 200 feet. Their composite fuselages, made of E-glass fiberglass woven into epoxy resin, were cutting through the salt air at 540 miles per hour. Each missile weighed 1,300 pounds. Thanks to that composite skin, they registered on radar with the cross-section of a large seagull. The Russian operators were about to learn a very expensive lesson in geometry, because the detection problem here wasn't about technology. It was about the curvature of the Earth. At 200 feet above the water, based radar simply cannot see past 22 miles. It does not matter if your radar costs $500 million. It cannot look through the ocean. The flamingos were surfing inside this blind spot, completely invisible, racing toward a target that was entirely unprepared for what was coming. The Russian 91/6E Big Bird acquisition radar finally swept the southern horizon and picked up a flicker of a signal that made no sense to the automated tracking software. The phased array antenna, designed to track 300 targets simultaneously out to 370 miles, was struggling to resolve these ghosts. The contacts would appear for 2 sweeps, vanish for 3, and reappear on a slightly different bearing, creating a nightmare for the fire control algorithms. The operator saw velocity data that proved something was moving at 500 miles per hour, but the return signature was so faint it looked like sea clutter or atmospheric noise. This was the genius of the Flamingo's design. It wasn't a stealth fighter, it was just plastic and foam. The airframe breaks down into 3 simple sections. The forward section houses a guidance package that would make a commercial pilot jealous, an inertial measurement unit containing 3 ring laser gyroscopes and 3 accelerometers, paired with a GPS receiver equipped with specific anti-jamming filters. But the real weapon was the material science. The fuselage's honeycomb core provided structural integrity without the radar-reflecting properties of aluminum. By the time the Big Bird radar finally achieved a stable classification at 073 hours, the Flamingos had crossed the 22-mile detection threshold. The system screamed a warning: velocity 541 miles per hour, altitude 190 feet, heading 047 degrees magnetic, profile match, cruise missile. The S-300 battery next door woke up 8 seconds later, confirming the track. But by then, the engagement window had already collapsed from minutes to seconds. The battery commander at the S-400 site stared at a screen that was quickly filling with bad news. He had maybe 50 seconds before the first missiles impacted the gas terminal, now just 18 miles behind him. The 92 N6E Gravestone fire control radar slewed its massive antenna toward the contact, its narrower beam burning through the electronic noise to build a precision track for interception. But as the radar locked on, the picture got worse. Behind the first Flamingo, 2 more contacts resolved into hostile tracks, and behind those, something else was emerging from the sea clutter. Slower, more numerous, and flying in a swarm formation that the system couldn't count fast enough. He didn't wait for coordination. He ordered the engagement. The launch sequence took exactly 4 seconds from the command to ignition. The gas generator inside the launch tube pressurized the ejection system, and compressed nitrogen kicked the 48 N6DM interceptor clear of the vehicle at roughly 100 feet per second. This cold launch technique protects the expensive radar vehicle from the rocket's exhaust. The solid fuel booster ignited only when the missile was safely airborne, accelerating the 4,000-pound interceptor to hypersonic speeds in the blink of an eye. The 48 NS6DM is a terrifying piece of engineering. A 2-stage interceptor nearly 23 feet long and capable of pulling 20 G-turns. But today, it was being asked to hit a target flying so low that the radar returns were mixing with the waves. The lead interceptor's proximity fuse triggered 40 feet from the first Flamingo. Close enough. The warhead's tungsten fragments shredded the drone's tail section, severing hydraulic lines and sending the cheap composite airframe tumbling into the Black Sea. 1 threat down. But the second interceptor lost its lock at the worst possible moment. The Flamingo jinked, or maybe the radar just lost it in the wave trough, and the Russian missile's onboard logic sent it into self-destruct mode rather than risk hitting friendly territory. 1 Flamingo down, 2 still inbound, and their fiberglass skins were soaking up radar energy like sponges. The gas terminal was now 14 miles away, less than 90 seconds of flight time. The S-300 battery requested a handoff on the trailing contacts, but handoff requires the 55 K6E command post to reconcile track numbers between batteries, a process that takes precious seconds. The data link was still negotiating protocols when the second Flamingo crossed the 20-mile threshold. Panic set in. 4 more missiles launched in rapid succession. 2 from the S-400, 2 from the S-300. For 6 seconds, both batteries were engaging the same target, wasting millions of dollars of ordnance on a single drone. The S-400's interceptors arrived first. 1 scored a proximity hit that gouged the Flamingo's wing root. The other missed cleanly. The S-300's missiles found only a debris field where the cruise missile used to be. 2 Flamingos down, $8.4 million in interceptors expended. And the third Flamingo was already past the engagement zone, descending toward the coast at 540 miles per hour with its 2,500-pound warhead intact. But the real nightmare was just starting to appear on the scopes. The Flamingos were just the opening act. A noisy, fast distraction designed to force the Russians to reveal their radar positions and waste their ready-to-fire missile. The contacts that actually mattered were 2 tracks now designated Hostile 07 and Hostile 08. These weren't converted light aircraft. These were the signatures the operators had trained to fear since April 2022, the same weapons that sank the Moskva. These were the Long Neptune missiles, and they exist because Ukrainian engineers asked a very simple question. What happens if we make the fuel tank bigger? The extra space in the 20-foot fuselage isn't for a larger warhead. It is almost entirely for jet fuel. The MS-400 turbofan engine, producing roughly 900 pounds of thrust, now had enough propellant to push the missile 620 miles instead of 175. The warhead did grow to 570 pounds, but the real innovation was in the guidance. The original Neptune used active radar homing, which is great until the enemy detects your radar emissions assault. The long Neptune deleted the radar seeker entirely. In its place, it uses a guidance computer running 3 navigation modes simultaneously: primary GPS, secondary inertial navigation using ring laser gyroscopes, and terrain reference navigation. It doesn't look for the target, it simply knows where the target is based on math and coordinates. The S-300 battery commander recognized the Neptune signature instantly. His operators pushed the classification up the chain, but the command post was still trying to untangle the mess from the Flamingo engagement. The Neptunes had crossed the coast near Veselovka, 40 miles southwest of the gas terminal, inbound at 560 miles per hour. Behind them, 14 drone contacts were crawling across the scope at 120 miles per hour. The S-400 had only 6 missiles remaining in its ready tubes. The S-300 had 8. That is 14 interceptors against 16 confirmed threats. The math was brutal. The Neptunes were the only targets that could inflict catastrophic damage in the next 90 seconds, so the battery commanders made the only choice they could: ignore the drones and kill the missiles. Their interceptors rippled off the rails within 4 seconds of each other. Hostile 07 took 3 hits and disintegrated over the coastline, a fireball of burning jet fuel and electronics. But Hostile 08 was luckier. As the interceptors closed in, the Neptune banked hard, dropping behind a low ridge near Golubitskaya at exactly the wrong moment for the Russian radar. The 48 NA-6DM lost its lock. One detonated 50 feet away, close enough to pepper the missile's skin with shrapnel, but not close enough to kill it. The Neptune emerged from behind the ridge trailing debris, its control surfaces chewed up, but its computer was still alive. While the strategic air defense systems were busy fighting the cruise missiles, the Buk-M3 battery positioned 15 miles east of the gas terminal was facing a completely different problem. The operator watched 14 contacts inbound from the southwest, velocity reading 130 miles per hour. These were obviously propeller-driven drones, probable type one-way attack. The Buk-M3 is optimized for hitting aircraft and cruise missiles, not slow-moving plastic toys. Its 9S-36 engagement radar painted the lead contacts, identifying them as the Ukrainian Luty drone. The Luty is nothing special to look at, a tube-launched fuselage about 12 feet long with a 22-foot wingspan, carrying 75 pounds of explosives. But inside that cheap airframe is a guidance system called Skynode S that is terrifyingly smart. It contains a multi-core processor, an inertial measurement unit, and a downward-facing camera. 10 times per second, that camera captures a frame of the terrain below, roads, rivers, buildings, and compares it to a reference map loaded before launch. It is literally navigating by sight. Even if the Russians jammed every GPS signal in the hemisphere, the Luty would still know exactly where it was by looking at the ground. The Buk commander had 36 missiles, but he couldn't reload in the field. He had to decide whether to spend a $300,000 missile on a $20,000 drone. 8 miles northeast of the gas terminal, the Russian Pol-21 jammer site was doing exactly what it was designed to do, screaming electromagnetic noise across the L-band and GPS frequencies. The Pol-21 is a distributed system, a network of small jamming nodes mounted on cell towers and utility poles that creates an 80-kilometer dead zone for satellite navigation. Against standard GPS-guided weapons, it is a force field. Against the Luty drones, it was useless. As the drones entered the jamming bubble, their GPS receivers reported signal degradation. The Skynode processor noticed the error, satellites claiming the drone had teleported 600 feet sideways instantly and simply stopped listening to the GPS. It switched priority to the visual navigation system. The camera saw a road intersection that matched the stored map coordinates, corrected the drift, and kept the drone on a rail. The Russian electronic warfare operators were pumping out megawatts of jamming energy, convinced they were blinding the enemy, while the Ukrainian drones were simply looking out the window and flying straight past them. It was a technological checkmate. You can jam a radio frequency, but you cannot jam a physical landmark unless you physically move the road. The Buk-M3 commander, realizing the electronic warfare was failing, panicked. The surviving Neptune missile, Hostile 08 was still the highest value target, but the drones were getting uncomfortably close to the tanks. He fired two 9M317M interceptors at the damaged Neptune. The first missile arrived from above, its proximity fuse triggering at 30 feet. Tungsten fragments punched through the Neptune's tail section, finally severing the hydraulic lines. The cruise missile pitched down and slammed into the Black Sea 400 yards short of the beach. Its 570-pound warhead detonated on impact, shaking the ground but sparing the gas terminal. But that left the drones. The Buck battery began firing on the lead Ludi drones. This is where the physics of radar fuses becomes a nightmare. The missile's proximity fuse works by broadcasting a continuous radar wave and listening for the reflection. Against a fighter jet, the reflection is huge. Against a Ludi drone made of foam and fiberglass, the reflection is barely a whisper. 4 missiles launched, 2 hit, 2 missed, not because they didn't get close, but because the fuse didn't realize it was close enough to detonate. The battery had just burned $1.2 million to shoot down $40,000 worth of drones, and 12 of them were still flying. With the air defense magazines depleted and the electronic warfare rendered useless by optical navigation, the terminal phase began. The lead Ludi drones crossed the perimeter fence at 0712 hours. The Panzer S-1 air defense vehicles stationed near the tanks opened fire with 30mm cannons, desperate to stop the swarm. They managed to shred 4 drones in a hail of tracer fire, but the remaining 8 were now in their terminal dives. The first drone targeted Tank 7, a massive pressure vessel filled with 200 cubic meters of liquefied petroleum gas. The 75-pound shaped charge warhead struck center mass. It didn't just explode, it punched a hole through the half-inch steel shell and injected a jet of superheated plasma into the liquid gas. The tank didn't just catch fire, it suffered a BLEVE, a boiling liquid expanding vapor explosion. The sudden pressure drop caused the liquid gas to flash boil instantly, expanding 600 times its volume in a fraction of a second. The steel tank didn't rip, it vanished. A fireball rose 200 feet into the air, creating a shockwave that flattened the perimeter fence and knocked the Panzer crews off their feet. The destruction was not linear, it was exponential. The heat from Tank 7's explosion instantly heated the neighboring Tank 9. The safety valves on Tank 9 were designed to vent excess pressure, but they were never designed for a fire this intense. The valves melted or failed, and 15 seconds later, Tank 9 ruptured in a second catastrophic explosion. The burning fuel flooded the containment berms. The remaining Ukrainian drones didn't need to hit the tanks, the fire was doing the work for them. But they hit them anyway. One drone struck the transfer manifold, severing the connection between the rail yard and the storage farm. Another hit the loading rack. By 0720 hours, 22 of the 30 storage tanks were either destroyed or burning uncontrollably. The combined thermal output created a firestorm visible from satellites, a column of black smoke rising thousands of feet into the atmosphere. The Russian air defense network had successfully engaged the decoys and the cruise missiles, expending nearly $30 million in advanced interceptors, only to lose the entire facility to a swarm of slow, cheap drones that simply refused to get lost. The fire burned for 3 days, halting fuel logistics for the entire southern front. At just past 13:45 on a rain-soaked afternoon, nearly 24 Russian armored vehicles tore down a churning, muddy dirt road near the settlement of Kostyantan, pushing toward Nivka with a sense of aggressive urgency that would soon prove fatal. The column commander had calculated his movement based on the heavy cloud cover, convinced that the torrential downpour had grounded every Ukrainian surveillance platform in the sector, essentially granting his unit a cloak of invisibility for their approach to the jumping-off point for the next day's assault. However, what the Russian officer failed to realize was that 3 separate Ukrainian drone teams had been staring at high-resolution weather radar feeds for hours, identifying a rapidly disintegrating storm cell that the Russians had assumed was static. In a matter of mere minutes, the sky cleared with a suddenness that felt almost artificial, transforming what was supposed to be a secure administrative march into a perfectly illuminated kill zone. The armored vehicles, now exposed under the breaking clouds, were racing against a clock they did not know was ticking, completely unaware that their tactical surprise had been reversed by a simple meteorological gap that the Ukrainians had been waiting to exploit with surgical patience. As the rain stopped, The three concealed Ukrainian drone teams scrambled into a choreographed frenzy of activity, powering up two distinct waves of first-person view drones simultaneously across three distinct launch sites hidden in the tree lines. The silence of the wet fields was instantly replaced by the high-pitched whine of brushless motors spinning from idle to maximum revolutions per minute in less than 2 seconds, a sound that usually signals impending violence in modern warfare. The sudden break in the weather meant that visibility surged from a claustrophobic few hundred meters to a crystal-clear field of view stretching for miles instantly, revealing the Russian column as a stark, dark contrast against the muddy road. The vehicles were strung out in a single-file formation stretching the length of several football fields, a target presentation that drone operators dream about, a mile away from the safety of the concrete structures of an abandoned collective farm. If the armor reached those hardened shelters, they would be virtually immune to light drone attacks and would be free to wreak havoc on Ukrainian lines the following dawn, meaning the column had to be stopped in the open, right here and right now. The moment those drones lifted off the wet grass and transmitted their first control signals, the electromagnetic spectrum lit up like a Christmas tree on the screens of a nearby Russian Service 5 electronic warfare array. This system, designed specifically to hunt localized radio frequency emissions, identified the unique signature of the drone control links in a fraction of a second, seemingly faster than a human operator could even blink. The control signals, broadcasting on standard commercial frequencies, were as conspicuous as flares in a dark room to the sensitive antennas of the electronic warfare complex. Within a multi-kilometer radius, the system's algorithms triangulated the Ukrainian launch positions to the precision of a city block, a margin of error that was terrifyingly accurate for the precision artillery batteries waiting in the rear. The geolocation data flowed instantly through encrypted digital channels to Russian gun crews positioned deep behind the advancing column, who were already in the process of loading laser-guided rounds into their breeches, turning a drone hunt into a race against incoming high-explosive shells. Each of the Ukrainian drones climbed rapidly through the dissipating rain clouds, their operators pushing the throttle sticks forward to gain altitude before the Russian counter-battery fire could react to their location. However, climbing high meant exposing their radio signatures above the terrain masking, the natural valleys and ridges that usually blocked radar returns, and putting them directly in the line of sight of a Russian Orlan 30 reconnaissance drone loitering a mile overhead. The Orlan's camera pod immediately swung toward the fresh launch signatures, its sensitive infrared sensors picking up the minute heat blooms generated by the operator's equipment despite their use of thermal blankets. The reconnaissance drone data-linked precise coordinates back to the waiting artillery tubes, but its role was far more critical than just spotting. Its gimbal-mounted laser designator began painting the Ukrainian positions with a coded infrared beam that the incoming artillery shells would hunt for during their terminal phase. The drone would maintain this laser lock for the entire duration of the shell's flight, constantly adjusting for wind drift and target movement to ensure a direct hit. This lethal synchronization was managed by the Russian Zoopark M1 counter-battery radar system, which was calculating firing solutions based on the initial drone transmissions while the Orlan provided the final terminal guidance. The Zoopark system worked by measuring the time difference of signal arrival at 3 separate receivers spread across the battlefield, a technique that relies on the immutable constants of physics. When a Ukrainian drone transmitted a control packet, each receiver logged the exact microsecond the signal arrived, and since radio waves travel at the speed of light, even nanosecond differences revealed the precise distance variations between the receivers and the source. These 3 receivers created intersecting geometric lines that pinpointed the transmission source like a mathematical crosshair, feeding coordinates into the fire control network. Within less than 2 minutes, guided artillery rounds would impact these coordinates with enough explosive power to collapse any bunker not built from reinforced concrete. And the Ukrainian positions, dug hastily into the earth and reinforced only with timber, offered zero protection against such precision. The stakes for the first Ukrainian drone team were brutally simple: hand off control of their airborne drones to the next team and run for their lives, or stay on the controls and get vaporized by the incoming volley. They initiated the complex transfer procedures to the second team while the Russian guided rounds were already arcing through the sky, massive shells with laser seekers adjusting their trajectory in the final seconds of flight to follow the Orlan's invisible beam. The drones under their control switched to a global positioning system waypoint following mode, creating a terrifying vulnerability window where the aircraft flew blind while the control frequencies synchronized with the new operators nearly a kilometer away. Several seconds at highway speeds meant over 100 meters of unguided flight where a gust of wind or a signal glitch could send them smashing into the ground. If the handoff failed, the attack force would be reduced significantly before the engagement even began, wasting valuable munition and alerting the convoy for nothing. The electronic handoff completed with a split-second margin to spare, the green connection lights flashing on the second team's controllers just as the first team sprinted through the wet wheat stubble carrying heavy equipment bags. Behind them, the bunker they had occupied just moments ago erupted into a geyser of earth and splintered wood as the laser-guided shells found their mark moments after the team had evacuated. On the Russian side, the column's defenses were waking up. The BMP-T Terminator support vehicles were tracking multiple air contacts on their radar. These specialized urban combat vehicles packed dual 30mm autocannons, automatic grenade launchers, and anti-tank missiles, providing enough firepower to theoretically create an impenetrable anti-drone umbrella over the entire column. Their turrets elevated rapidly as the drone signatures populated their threat displays, the mechanical whine of their traverse gears signaling that the element of total surprise had officially evaporated. The second Ukrainian team now found themselves controlling a massive swarm simultaneously, which doubled their electromagnetic signature and made them an impossible-to-miss beacon for the Russian sensors. The Orlan 30 overhead immediately locked their new position with its infrared laser, while the electronic warfare suite detected the distinct signal spike that occurred when both operators transmitted during the handoff. The accuracy of the Russian triangulation tightened significantly, giving the second team a rapidly closing window before the next salvo of guided rounds arrived at their location. Artillery rounds were already walking toward them, the first shell impacting dangerously close and throwing a massive cloud of wet dirt into the air. The operators kept their hands steady on the controls despite the ground shaking violently beneath them, their eyes glued to the drone feeds flickering across their screens, each one racing toward the Russian column at maximum attack speed. The mathematics of survival were becoming increasingly thin for the second team. Mere seconds for the Russian guns to recalculate the new coordinates, the flight time of the shells, but only a blink-and-you-miss-it window to transfer control if the shelling got too close. The third team watched their frequency scanners with intense focus, their systems powered and ready to grab control the instant the second team had to bail out. Another shell hit closer, the concussion wave hitting the operators in the chest like a physical hammer and rattling the tablets in their hands. They initiated the handoff sequence to the third team while simultaneously grabbing their most critical gear, abandoning sleeping bags, rations, and personal items to the mud. The third team smoothly accepted control of the entire swarm, their systems straining to manage the maximum bandwidth load while the second team sprinted through parallel furrows in the wheat field, using the micro-terrain for whatever cover it could provide against the shrapnel slicing through the air. Managing so many drones converging from 3 different launch sites created an immediate airspace deconfliction problem that could destroy the attack before the Russians fired a single shot. At high closure rates, drones launched from different positions would reach the same point in space simultaneously, and 2 racing quadcopters colliding in midair meant both would turn into a cloud of plastic confetti and lithium sparks. The teams had practiced this convergence for weeks, establishing a rigid altitude hierarchy. Team 1's drones would approach at a lower tier, Team 2's at a middle tier, and Team 3's at the highest ceiling. This vertical separation was the only thing preventing a fratricidal disaster. The video feeds were degrading into static, meaning the operators could not see each other's drones and had to trust the blind choreography they had rehearsed. To complicate the nightmare, the approaching storm cell was now visible to the naked eye, a towering wall of rain advancing rapidly that would arrive over the target area in a handful of minutes. Lightning flickered within the dark mass, each strike generating a powerful electromagnetic pulse that could scramble the delicate control signals of the drones if they flew too close to the charged air. The window for the attack was closing from both ends. Russian artillery was hunting the operators on the ground while the weather was squeezing the airspace from the sky. The drones had to reach their targets in the next 90 seconds, or the entire operation would fail, as the rain returned to blind the cameras and ground the fleet. Battery levels had dropped to critical levels from fighting the increasing headwinds generated by the storm front, giving the pilots exactly 1 attack run with absolutely no possibility of a second attempt or a go-around. The Russian BMP-T Terminators were built for exactly this scenario, designed to act as a meat grinder for aerial threats. But the Ukrainian operators knew the system had a fatal flaw in its fire control logic. The Terminator's computer prioritized threats by size and speed, constantly recalculating the engagement queue as new contacts appeared on the radar. With a swarm approaching simultaneously, the system stuttered, jumping its targeting lock between identical threats without completing the full engagement sequence for any single one. Worse, the turrets had limited traverse speeds, and the drones were approaching from 3 distinct vectors, forcing the vehicle to choose a sector while leaving its rear and flanks exposed. The fire control system, relying on older algorithms, could not decide which identical drone was the highest priority, so it spent more time slewing the turret back and forth than actually firing. The Ukrainians had synchronized their arrival specifically to exploit this processing bottleneck, flooding the sensor picture with more data than the onboard processors could handle in real time. Despite the saturation tactics, several units disintegrated when 30mm rounds detonated close enough, their plastic frames and electronics scattering across the wheat field as the airburst munitions did their job. But the bulk of the swarm survived the defensive fire and entered their terminal dive phase, the operators selecting specific impact points through the static-filled video feeds. They targeted the gap between the turret and the hull, the delicate engine deck grills, and the spaces where the jury-rigged cage armor, those steel cope cages welded on top of the tanks, didn't quite cover the vulnerable spots. These were not random strikes, but surgical injections of high explosives into the mechanical vitals of the Russian armor. One drone found a gap in a tank's cage armor, detonating against the turret ring and jamming it in place. Another hit a vehicle's open rear door, the explosion destroying the engine block and igniting an immediate electrical fire that filled the crew compartment with toxic smoke. The aftermath unfolded over the following minutes as the surviving Russian crews abandoned their burning vehicles, some running for drainage ditches, while others sprinted toward the tree line in a desperate attempt to escape the invisible swarm. The few remaining drones circled overhead, their operators scanning the carnage for any vehicle that might still be recoverable or operational. One by one, those drones found Russian vehicles that were still serviceable, engines running, tracks intact, and promptly dove in to ensure they would never move again, turning them into permanent fixtures of the Ukrainian countryside. The Russian column, which had begun the hour as a threatening armored fist poised to strike, was now nothing more than a collection of nearly 24 burning wrecks strung out along a muddy road, destroyed by 3 teams of operators who were already packing up their gear and vanishing into the tree line before the storm could catch them. As the storm front finally swept over the burning convoy, dousing the fires with a deluge of cold rain, the 3rd team's reconnaissance drone lingered just long enough to capture high-resolution imagery of the lead vehicle through the steam and smoke. What the operators saw on their tablets confirmed that this was not simply a random mechanized company, but a high-value breakthrough unit carrying specialized equipment that Moscow could not afford to lose. The burning wreckage of a high-mobility vehicle in the center of the formation was not carrying infantry, but was fitted with the distinctive antenna array of a Lear-2 mobile electronic warfare complex. The irony was palpable. The very system designed to jam these frequencies and create a protective electronic bubble around the convoy had been rendered into a smoking pile of scrap metal because its operators had been too slow to react to the frequency-hopping protocols of the commercial drones. The thermal feed showed the distinctive cooling fins of the jamming array warped by the heat of the vehicle's burning fuel, a visual testament to the fact that in modern warfare, expensive electronic countermeasures are only as effective as the human reflexes controlling them. And today, those reflexes were just a few seconds too slow. The economics of this engagement represent a nightmare scenario for military planners in Moscow and a masterclass in asymmetric value destruction. The total cost of the Ukrainian strike package, including the drones, the lost batteries, and the support equipment, came to the price of a mid-range luxury sedan. In exchange, they had effectively removed an entire mechanized combat group from the order of battle before it could fire a single shot in anger. The destruction of the armored vehicles, including the rare and expensive support platforms and the electronic warfare suite, represents a material loss exceeding tens of millions of dollars. That calculates to an astronomical return on investment in under 15 minutes. There is not a hedge fund manager on Wall Street who could generate those kinds of returns without going to prison. Yet on a muddy road near Nivka, 3 teams of volunteers just accomplished it with consumer electronics and duct tape, proving once again that the cost of entry for destroying heavy armor has hit an all-time low. By the time Russian rescue crews finally reached the ambush site well after the engagement, the only thing greeting them was the crackle of ammunition cooking off inside the destroyed hulls and the endless gray rain washing away the tracks of the attackers. The Ukrainian drone teams were already miles away, their equipment packed into civilian vans, blending into the local traffic as if they had never been there. They left behind no radar signature, no expensive infrastructure, and no casualties, only a decimated column that would require months to replace. The Russian artillery batteries continued to pound the empty wheat field for another hour, churning up mud and and wasting thousands of dollars in shells on a position that was occupied only by ghosts. The engagement demonstrated the brutal new reality of 21st century combat. If you can be seen, you can be hit. And if you are hitting with cheap electric motors against multi-million-dollar engines, the math will always favor the hunter, who is not afraid to lose a few toys to kill a beast. Meanwhile, the Russian command loop, still operating on a lag caused by the shock of the attack, continued to execute a retaliation plan against an enemy that no longer existed. Artillery batteries positioned deep in the rear continued to pound the empty wheat field for another hour, churning up hectares of mud and wasting thousands of dollars in high-explosive shells on a position that was now occupied only by ghosts. The fire mission was a masterclass in futility. Heavy howitzers delivered a saturation bombardment that would have decimated a fixed infantry platoon. But against a mobile drone team that requires only 5 minutes to pack up and leave, it was simply an expensive landscaping project. This disconnect between the speed of the Russian kill chain and the agility of the Ukrainian operators highlighted a critical failure in doctrine. The Russians were fighting a war of static lines and heavy fires, attempting to destroy grid squares, while their opponents were fighting a war of precise moments, appearing only long enough to kill and then dissolving before the first counter-battery radar could even calculate a firing solution. At 0530 local time, a Russian Bayan M-class corvette drifting in the Sea of Azov was in the final stages of preparing its 8-caliber cruise missiles for a strike on Ukrainian infrastructure. The crew of the 949-ton vessel believed they were operating in a secure maritime zone, completely unaware that they had been tracked for the past 45 minutes by a wolf pack of 7 Ukrainian long-range strike drones. In exactly 180 seconds, a routine dawn patrol would transform into a masterclass in asymmetric naval warfare. The lead drone, Iksamini, a customized Rubaka kamikaze unit, accelerated to 400 kilometers per hour as it crossed the coastline, instantly triggering the acoustic sensors of a Russian coastal defense checkpoint. The quiet morning air erupted with the sound of 23mm anti-aircraft fire, sending streams of tracers arcing into the dawn sky. Each high-explosive incendiary shell carried enough kinetic energy to turn the composite airframe of the drone into scattered debris. But the Russian gunners faced a physics problem they could not solve. They were firing at the sound of the engine, but at 400 kilometers per hour, the drone was already 300 meters ahead of its own acoustic signature. The gunner walked his rounds toward the distinctive whine of the modified gasoline engine, but the lead Rubaka banked hard left, pushing its engine to maximum revolutions and screaming past the kill zone before the heavy barrel could traverse to track it. The initial survival of the lead drone, however, created an immediate tactical crisis for the rest of the squadron. The gunfire had alerted every Russian air defense position within a 10-kilometer radius, and messages were already spreading through encrypted telegram channels faster than official military radio networks could process them. The element of surprise, the drone operator's most valuable currency, was gone. On the operator's screen inside a bunker 300 kilometers away, video feeds suddenly filled with the static interference of high-voltage power lines that had been invisible against the dark terrain until the final second. The drone pulled up sharply, its belly scraping just 2 meters above 110,000 volts of live electricity. For 3 agonizing seconds, every instrument in the ground control station went haywire. The magnetic field from the power lines sent the digital compass spinning wildly, while the video feed flickered into gray noise. The operator was flying blind, relying entirely on muscle memory and the drone's last known vector. When the video link re-established, a massive radio tower loomed out of the darkness directly in the flight path. With milliseconds to spare, the operator banked hard left, missing the steel guy wires by mere inches. Behind the lead Rubaka, 2 more drones followed 30 seconds apart, using the chaotic wake of the first to slip through the perimeter unnoticed. These were the Spear variants, specifically designed to blind the ship's radar defenses before the main heavy hitters arrived. While the Rubakas cleared the path, 4 Bober loitering munitions took the northern route, trading speed for payload. These drones carried heavier warheads designed to crack a ship's hull, acting as the hammer that would strike after the Spears removed the shield. The telegram warnings had traveled faster than the drone. As they approached the second defensive ring, a Repellent 1 electronic warfare system surged to life, flooding the control frequencies with 400 watts of broadband electromagnetic noise. The lead Bober's screen went black as the signal link was severed by the wall of interference. But the Ukrainians had anticipated this exact scenario. The moment the link dropped, the drone's onboard computer switched to autonomous terminal guidance. Navigating solely by internal accelerometers and optical landmark recognition, the machine flew blind through the electromagnetic storm. 3 minutes later, as it exited the jamming bubble, the video feed snapped back online. The Bober was exactly on course, having drifted less than 12 meters over a 5-kilometer distance. But the relief was short-lived. Ahead, a BTR-82 armored personnel carrier blocked the highway, its 30mm automatic cannon already firing in predetermined interdiction patterns designed to create a wall of shrapnel. The operator of the lead Bober immediately dove the aircraft down into an industrial zone, skimming rooftops to break the line of sight. However, the industrial complex was not empty. Hearing the distinct lawnmower sound of the drone motors, Russian infantry poured out of the buildings like an anthill that had been kicked over. The drone held an altitude of exactly 10 meters. At this specific height, the curvature of the Earth creates a natural radar shadow that serves as a cloak of invisibility. A hilltop radar system that can detect targets at 50 kilometers when they are flying at altitude can only see 12 kilometers when the target is skimming the ground. Physics became their shield against the long-range sensors, but it offered no protection against small arms fire. The drones threaded invisible corridors of safety, while dozens of soldiers fired assault rifles at the fleeting sounds and glimpses of the airframes. But statistics do not lie. Even with a hit probability of 0.01% per bullet, the concentrated fire from a coordinated squad eventually connected. The third Rubaka spiraled into a concrete parking lot, its warhead detonating on impact and sending a shockwave through the complex. There were now 2 Bobers and 2 Rubakas remaining. They could not afford to lose a single additional airframe if they wanted to sink the corvette. As the lead Rubaka crested the final ridge before the coastline, the operator's screen filled with a terrifying silhouette that should not have been there. The mission briefing had been catastrophically wrong. The coastal defense was not a vintage Soviet system, but a modern Panzer S-1 battery. In 4 seconds, the operator would have to make a decision that would either save the mission or destroy every remaining drone. The Panzer launch vehicle fired 6 missiles simultaneously. But these were not ordinary surface-to-air missiles. These were the new Panzer SM anti-drone interceptors, developed specifically after commercial quadcopters had humiliated Russian air defenses in previous years. Each missile weighed just 12 kilograms, but carried 200 tungsten spheres in a fragmentation warhead designed to create a donut-shaped kill zone specifically optimized for small UAVs. Upon detonation, these spheres would expand outward at 1,800 meters per second, creating a lethal cloud 10 meters in diameter that would shred the fragile composite wings of the drones. As the Panzer operator fired, he utilized ladder engagement tactics, launching missiles at staggered altitudes of 50 meters, 30 meters, and 10 meters, effectively creating a 3-dimensional box of death that the drone would have to fly through. The Rubaka's operator, however, had studied Panzer engagement envelopes extensively and knew the missiles had a critical vulnerability: a 1.2-second arming delay after launch. This safety feature was designed to prevent the warhead from detonating too close to the launcher and killing its own crew. At 432 kilometers per hour, the drone covered 144 meters in those 1.2 seconds. The moment the operator saw the missiles flare, he pushed the control stick forward, diving the drone straight toward the Panzer vehicle in a suicidal game of chicken. The interceptor missiles streaked overhead, their proximity fuses still in safety mode, unable to detonate even as the drone passed within meters of their flight path. By the time the missiles armed, the Rubaka was already below them, using the launcher's own safety protocols as a shield. The operator leveled out at 5 meters and lined up on the Podlet K-1 radar vehicle, the critical system providing targeting data to every Russian launcher within 200 kilometers. The Panzer's twin 30mm cannons opened fire, each barrel cycling at 5,000 rounds per minute, attempting to create a wall of lead in front of the incoming threat. The Russian gunner tried to employ boxing tactics, spraying rectangular zones of fire where the drone was predicted to be. But the fire control solution faced a mathematical lag that no software could fix. The system needed 1.5 seconds to calculate the trajectory, 0.5 seconds for the heavy servo motors to aim the turret, and another 1.5 seconds for the rounds to travel the 2 kilometers to the target. This created a total lag of 3.5 seconds. The drone operator simply changed course every 2 seconds, ensuring the Russian computer was always solving an outdated geometry problem. The Rubaka punched through the curtain of fire and slammed directly into the radar antenna. The shaped charge detonated, creating the Monroe effect. This phenomenon occurs when a shaped charge's explosion crushes a copper cone into a hypersonic jet, not melting it but deforming it under such extreme pressure that the solid metal behaves like a liquid, punching through armor like a needle through paper at 7,000 meters per second. The jet perforated the antenna array, destroyed the processing units, and exited through the back wall, finally dispersing into a spray of molten copper. With the primary fire control radar destroyed, the second Rubaka targeted the nearby P-18 Spoonrest early warning radar. The Panzer crew switched to their thermal imaging backup, but the dawn hour had created a phenomenon known as temperature inversion, where a layer of cool air is trapped under a layer of warm air. This atmospheric condition causes thermal shimmer and generates false heat signatures as the air layers mix. The drone's electric motors generated minimal heat, registering maybe 10 degrees above ambient temperature against the warming morning sea that still retained heat from the previous day. On the thermal display, the drone appeared as a faint cold spot, then disappeared entirely when flying over cooler patches of land. The thermal imager's processing algorithm, designed to track jet engines burning at 600 degrees, could not maintain a lock on such a small temperature differential. The Panzer gunner fired in desperation mode, using a predetermined spiral pattern starting at the drone's last known position and expanding outward. This water hose technique might work against a helicopter that cannot change direction instantly, but the drone pivoted 90 degrees in half a second. 5,000 rounds were expended, and 0 hits were achieved. The Rybaka struck the P-18 dead center, eliminating 200 kilometers of radar coverage in an instant. With both primary radars destroyed, the corvette located 4 kilometers offshore had completely lost its early warning network. Without the Podlet and the P-18 providing initial detection and tracking, the ship's own onboard radar was limited to the horizon line, meaning it could only see 40 kilometers out, giving the crew less than 2 minutes of warning against low-flying threats. The defensive shield protecting the corvette had just vanished. The ship that was preparing to launch missiles at Ukrainian cities was now blind and alone. The corvette's radar finally detected the incoming drones at 4 kilometers, but they appeared as ghost contacts that flickered in and out of existence with each wave. The Russian ship faced an impossible problem: distinguishing drones flying at 3 meters altitude from waves that were 2 meters high. Both created radar returns of similar intensity. The Doppler shift effect, which normally separates moving targets from stationary objects, failed because the drones were flying at variable speeds between 80 and 120 knots. The computer's clutter rejection algorithm, designed to filter out sea spray, started filtering out the real threats. Every third sweep of the radar, the drones disappeared entirely from the screen as the processor decided they must be false returns. That did not stop the Russian crew from trying to use their last line of defense. The AK-630 M2 Duet system spun up with a mechanical whine, and 10,000 rounds per minute erupted from the twin 30mm rotary cannons. The fire control computer tried to calculate intercept paths using Kalman filtering algorithms. Kalman filtering attempts to predict where a moving target will be next by mathematically combining its past positions with current sensor data, much like trying to guess where a zigzagging car is headed by averaging what you see with what physics says is possible. But the drone operators were throwing these calculations off by making random input adjustments every 2 seconds. The Duet system had been designed to engage P-270 Moskit missiles, 3,000-kilogram weapons flying predictable linear trajectories, not 150-kilogram drones maneuvering randomly. It was like using a sledgehammer to hit a hummingbird. The computer needed 3.5 seconds to generate a valid firing solution, but since the drones changed course every 2 seconds, the math never aligned. Undeterred by missing all their shots, the corvette deployed its PK-10 decoy system, launching clouds of chaff. These aluminum strips, cut to exactly half the wavelength of the targeting radar, created a radar return larger than the drone itself. Within seconds, hundreds of false targets bloomed on every radar screen within 50 kilometers. Against radar-guided missiles, this would create impenetrable confusion, but against drones guided by human operators watching through high-definition cameras, it created nothing but pretty sparkles in the morning sun. The operators ignored the light show and maintained visual lock on the ship. The corvette's TK-25E electronic countermeasure suite activated next, pumping out 200 watts across the spectrum from 20 megahertz to 40 gigahertz. Against normal radio-controlled drones, this would sever the control link instantly. But the Ukrainian drones used frequency-hopping spread spectrum technology, jumping between 128 channels per second in a pseudo-random pattern known only to the transmitter and receiver. The jamming affected individual hops, causing occasional frame drops and pixelation in the video feed, but it never blocked enough sequential channels to break the link. The video feed degraded from 1080p to 480p, annoying but still usable. Sensing what was coming next, the corvette captain ordered evasive S-turns at maximum speed, but physics does not negotiate. The 949-ton vessel needed 15 seconds to change heading 30 degrees. The drone needed 50 milliseconds. The lead Bober drone operator recognized the ship's movement pattern and timed his approach for the steady period between turns. At 500 meters, the operator switched to manual control, the radar mast filling his screen with 6 meters of critical electronics. The Duet cannons could not depress below -5 degrees, and at 200 meters range and 3 meters altitude, trigonometry put the drone under their engagement arc. Sailors with PKM machine guns fired from the deck, but they faced an impossible physiological problem. The drone crossed their field of view in 0.8 seconds. Human eyes need 0.2 seconds to focus on a moving target, another 0.3 seconds to track it, and 0.2 seconds to aim. By the time they pulled the trigger, the drone had moved 100 meters. They were literally firing at afterimages burned into their retinas. The first Bober slammed face-first into the mast. Instantly, every radar, communication suite, and data link on the ship went down. No longer able to fire their missiles, they were now a sitting duck. The second Bober dove toward the corvette's port side at a 30-degree angle, its operator aiming for the junction between frames 44 and 52, where the missile magazine sat behind 15 millimeters of steel plating. At 100 meters, the operator made his final adjustment, accounting for the ship's 8-knot drift and 3-degree list from the hard turn. The shaped charge needed to hit at exactly 90 degrees for maximum penetration. Too shallow, and it would deflect. Too steep, and it would waste energy. The operator had practiced this moment 500 times in simulation, but reality included variables no simulation captured. Hands shaking from adrenaline, sea spray on the camera lens, and the knowledge that missing meant friends would continue suffering under caliber bombardment. The Bober struck exactly at the missile magazine's forward bulkhead. Its shaped charge created a jet of molten metal moving at 7,000 meters per second. The 15-millimeter steel plate offered the same resistance as tissue paper. The jet punched through, spraying molten copper across stored ammunition and missile components. The explosion ruptured 3 separate systems simultaneously. Hydraulic fluid at 3,000 psi sprayed across electrical panels, creating instant arc fires. Missile coolant lines burst, releasing toxic hydrazine derivatives. And most critically, the warhead's safety interlocks disconnected, leaving 8-caliber missiles armed but useless. The corvette did not sink, but it crawled into port 12 hours later with its superstructure blackened and its hull opened in several places. Recovery would take 18 months minimum. Ukrainian operators, sitting in bunkers 300 kilometers away, had knocked out a warship costing $500 million using parts bought off the internet. The initial blast was only the catalyst for a much darker chain reaction deep within the ship's bowels. As the damage control teams rushed to Compartment 4, they were not just fighting fire. They were fighting chemistry. The corvette's superstructure, constructed from a specialized aluminum-magnesium alloy to reduce displacement, ignited at temperatures exceeding 1,200 degrees Celsius, creating a Class D metal fire that standard water hoses could not extinguish. In fact, when the desperate crew turned their nozzles on the burning bulkheads, the intense heat caused the water molecules to undergo thermal dissociation, splitting into hydrogen and oxygen upon contact with the superheated metal. This effectively fed the fire with explosive rocket fuel rather than suppressing it, turning the corridor into a blast furnace. Ventilation shafts, originally designed to circulate cool air to the sensitive electronics, now acted as high-speed chimneys, pumping toxic hydrazine vapors and combustion byproducts directly into the command information center. The captain watched his tactical screens flicker and die one by one, not because of the drone strikes, but because the silver zinc batteries in the backup power supply had reached their thermal runaway threshold. In the end, it was not the shaped charge that took the ship out of the war for the next year. It was the inescapable laws of thermodynamics turning the vessel's own advanced materials against it. At 0347 local time on June 26, 2025, a Russian S-400 radar dish sweeps the dark Crimean sky with enough focused electromagnetic energy to microwave a frozen dinner at 10 kilometers. The operators inside the command vehicle are confident, believing their bubble of airspace is impenetrable, but they are completely unaware that a clock has already started ticking down on their survival. In exactly 15 minutes, 17 Ukrainian drones will turn that sophisticated radar array and the entire S-400 battery into a $500 million heap of burning scrap metal. The Lead Beaver drone you see here has been airborne for over 2 hours at this point, burning through fuel at a rate of roughly 12 liters per hour. At current consumption rates, the onboard computer calculates it has 19 minutes to locate the target, 2 minutes to execute the terminal dive, and less than 2 minutes of reserve in case it misses the first pass. The mathematics of this mission are brutally tight. and the margin for error is effectively zero. The formation spreads across a 3-kilometer wide front while maintaining an altitude of exactly 50 meters. At this specific height, the curvature of the Earth creates a radar horizon of roughly 25 kilometers, a fundamental geometric limitation that no amount of Russian engineering can overcome. It is the tactical equivalent of sneaking up behind a couch. As long as you stay low enough, the radar simply has no line of sight to detect you. The S-400's mighty radars can track ballistic missiles in the upper atmosphere, but they cannot see through dirt and terrain. Physics does not negotiate with military budgets. Behind the 7 Beaver drones, 10 AQ-400 Scythe units maintain their station. They look exactly like what they are, plywood boxes with wings, assembled in repurposed furniture factories by workers who used to build kitchen cabinets. Each Scythe costs a base price of roughly $15,000, with an additional $30,000 for the guidance systems. The return on investment for this strike package would make any Wall Street hedge fund manager salivate. 17 drones totaling roughly $425,000 are attacking a battery worth over $500 million. That is, of course, if they can make it to the target without being jammed. Navigation relies on triple redundancy because the Crimean Peninsula has been a GPS jamming nightmare since late 2022. Each drone carries a commercial GPS chip that costs about $12 on online marketplaces, backed up by industrial-grade accelerometers and gyroscopes that track every shift in velocity and direction. The third system is pure Ukrainian engineering cleverness, optical cameras comparing the live terrain below to stored satellite imagery. Russian electronic warfare units may be able to jam satellite frequencies, but they cannot jam eyeballs or optical sensors. At 0415, the swarm executes its pre-programmed dispersal pattern. 7 drones climb to 80 meters, still below most long-range radar coverage, but high enough for steep diving attacks. 5 drones maintain their altitude at 50 meters, while the remaining 5 drop to a dangerously low 30 meters above the ground. This creates what drone operators call a vertical spread, forcing the air defense crews to divide their attention across multiple altitude bands simultaneously. On the receiving end, the S-400 battery near Jankoy runs its standard overnight routine. The 92 N6E Gravestone radar rotates once every 12 seconds, scanning for threats that theoretical doctrine says should not be there. The 91 N6E Big Bird radar searches deeper into the airspace, looking for high-altitude intruders. 4 launchers stand ready with 16 missiles in total. 2 Pantsir S-1 units provide close-in defense for the battery. The numbers on paper say this battery should be untouchable. The reality on the ground says 17 plywood drones are about to prove otherwise. At 0415 and 30 seconds, the operator inside the Pantsir vehicle stares at his radar display as it suddenly populates with 17 contacts at 32 kilometers out. His Pantsir S-1 battery is designed to engage about 3 simultaneous targets, maybe 4 if the cooling system is running perfectly and the computer does not overheat. You do not need to be a mathematics major to know that 17 targets divided by 2 Pantsir units is significantly more than 4 targets each, and that is assuming they can even lock onto them. The Pantsir's maximum engagement range is technically 20 kilometers, but its effective engagement envelope against small aircraft is closer to 15 kilometers. Against missiles, it drops to 10 kilometers, and against targets with radar cross-sections below 0.1 meters, the range shrinks to just 5 kilometers. These drones register at roughly 0.05 meters. The math says he needs to wait until they are inside 5 kilometers for any realistic chance of a hit. But here's the problem. 17 drones spread across a 3-kilometer front are approaching at 48 meters per second. The time from the 5-kilometer mark to impact is just 104 seconds. The Pantsir cannot fire its 57 E-6 missiles without reloading, and it takes roughly 5 minutes to reload the launch tubes. Time is not on their side. The targeting computer starts its engagement calculations, but the numbers look disastrous. Each engagement requires 2 seconds for target acquisition, 1 second to fire the missile, 6 to 8 seconds of flight time to the target, and about 2 seconds to assess the damage. This means the operator needs 11 to 13 seconds per drone under perfect laboratory conditions. 17 drones times 12 seconds equals 204 seconds of work. He has only 98 seconds before impact. It's like realizing your wife's birthday is today, and you have exactly 10 minutes to find a thoughtful gift, write a card, and come up with a believable excuse. Good luck with that. 20 kilometers to the north, the 91 N6E Big Bird radar continues its rhythmic rotations, completely oblivious to the approaching swarm. This L-band monster can see 600 kilometers out and track 300 targets simultaneously. It can detect an object the size of a baseball at 100 kilometers, but its minimum altitude coverage is roughly 100 meters. The drones flying at 50 meters might as well be submarines for all the good that radar does. The S-400's launchers remain in standby mode. Each 5P-85TE 2 vehicle carries 4 missiles. The battery has 16 ready to fire. In theory, they could engage 16 targets simultaneously. In practice, they need the 92 N6E radars to provide precision targeting data. Without hard radar locks, those $1.5 million missiles are just expensive lawn decorations. At 0425, the geometry of the engagement gets significantly worse for the Russians. The drones adjust their course, spreading their formation out to 5 kilometers wide. Now they are approaching across a 90-degree arc. The Pantsir's turret can traverse at 45 degrees per second, but tracking multiple targets across that wide of an arc means constant slewing back and forth. Every time the turret slews, valuable seconds are lost. The other Pantsir unit, positioned 800 meters to the south, faces the exact same mathematical equation with the exact same grim result. Between them, they have 24 ready missiles plus 16 reloads against standard aircraft or attack helicopters. That is plenty of firepower. Against a coordinated drone swarm, they would need to hit with every single shot, and even then, they would run out of missiles before they ran out of targets. The irony is perfect. The radars can track objects in low Earth orbit. Its missiles can reach into the stratosphere to kill hypersonic threats. But against 17 drones built in a basement flying lower than treetop height, the battery might as well be defending itself with harsh language. At 0445 and just a few kilometers out, the Pantsir's targeting computer finally achieves a solid lock on drone number 1, then drone number 2. Then it stutters, trying to assign priority to 15 more targets. All the targets present identical thermal signatures, and all are boring in at 48 meters per second. The operators can hear the computer's cooling fan scream as it tries to solve 17 simultaneous engagement equations. The first 57 E-6 missile leaves the rails 12 seconds later, accelerating to Mach 3 in less than 2 seconds. Racing toward drone number 3, the computer has decided that the closest threats are already within the minimum engagement range. Flight time to target is 6.3 seconds. The proximity fuse searches for radar, returns large enough to trigger detonation. It finds nothing. The missile passes within 2 meters of the Beaver drone and continues harmlessly into the dawn sky. Seeing the problem, the operator overrides the computer and switches to manual optical targeting. His screen shows the drones clearly now, dark shapes silhouetted against the lightening sky. He selects a scythe, which is larger and supposedly easier to hit. The second missile launches. This time the proximity fuse works, shredding the plywood drone with tungsten fragments. 1 down, 16 to go. The math remains relentless. Each successful engagement takes a minimum of 11 seconds. He has already burned 21 seconds. The lead drones are now at 2.8 kilometers. Time remaining is 52 seconds. Missiles remaining is 10. From Belbek Airfield, 85 kilometers to the northwest, 2 Sukhoi Su-35S fighters launch on full afterburner. The pilots received scramble orders 90 seconds ago after a patrol reported possible drone activity near critical infrastructure. At maximum thrust, they are burning 400 liters of fuel per minute, rocketing toward Jankoy at 1,900 kilometers per hour. Their flight time is 8 minutes. At this rate, they will arrive just in time to photograph the burning wreckage. The second Pantsir joins the fight 10 seconds later. Its operator is firing in full automatic mode. The computer launches missiles as fast as the system mechanicals allow, which is 1 every 3 seconds. Tungsten fragments fill the air like lethal confetti. 2 more drones disappear in puffs of smoke and plastic debris, 14 remaining. But physics has entered the chat. The drones execute their final attack profiles. The high group begins diving attacks at 30-degree angles, increasing their closure rate to 65 meters per second. The low group drops to 20 meters, using terrain masking to break any remaining radar locks. The middle group maintains steady approaches, forcing defenders to choose between multiple threat vectors. Just after 0446, both Pantsir units run dry. 24 missiles have been expended, 5 drones are destroyed, and 12 remain. Reload time is 5 minutes. Time to impact is 68 seconds. The operators switch to cannon mode, but everyone inside the vehicle knows the statistics. Trying to shoot these small drones down with cannons is like trying to hit a mosquito with a sniper rifle. The S-400 launchers finally receive authorization to engage, but it is no use without the 92 N6E radars to provide precision targeting data, leaving them firing blind into the chaotic morning air. The 48 N6E missiles launch away with a deafening roar. $3 million worth of desperation arcing into the sky on pillars of white smoke. These weapons are designed to hit high-performance aircraft at 200 kilometers, maneuvering at Mach 4. At a distance of 2 kilometers, they are useless against slow-moving drones, unable to arm their warheads or guide effectively in such a compressed timeline. Both missiles self-destruct safely in the upper atmosphere after failing to acquire targets, raining expensive debris over the surrounding fields. At 0447, the Russian operators know they are cooked. 12 drones are now inside 500 meters, approaching from 7 different vectors at 3 different altitudes. The defensive system simply cannot traverse fast enough to engage them all. The operators inside the command vehicles know exactly what is coming. They can see it on their screens, track it on their optical sensors, and even smell the ozone as the electronics push past their thermal limits. But they cannot stop it. The operators watch helplessly as 12 digital dots converge on the battery's vital systems, 2 heading for each 92N6E radar, 2 for each 91N6E, and 4 targeting the loaded launchers. The Panzer cannons traverse frantically, spraying 30mm rounds that miss by meters. But they will not do anything to stop the physics equation that is about to resolve itself. At exactly 0447, the first Beaver drone connects with the primary 92N6E radar. Its 20-kilogram shaped charge turns $50 million of Russian engineering into a twisted work of modern art in less than a blink of an eye. The shaped charge you see detonating now performs exactly as the engineers designed it to. Ukrainian specialists calculated the optimal standoff distance, the precise cone angle, and the exact explosive composition required for this specific target. The copper liner, just 3 millimeters thick, inverts and stretches into a superheated jet moving at roughly Mach 23. It punches through the radar's protective housing, slices through the delicate waveguide assembly, and obliterates the transmitter modules before emerging on the other side. 37 seconds later, the backup 92N6E takes a direct hit from drone number 7. This Beaver approached from the opposite direction, catching the radar mid-rotation and striking the antenna feed horn, the most vulnerable point in the entire system. The explosion travels down the waveguide like a directed energy weapon, frying every electronic component in sequence. The radar dish, 8 meters in diameter and weighing 3 tons, shears off its mount and crashes to the ground, kicking up a massive cloud of dust and silence. At 0448 and 22 seconds, 2 Scythe drones hit the northern Big Bird radars simultaneously. With 32-kilogram warheads, they do not need sophisticated shaped charges because pure explosive force does the job just fine. The first warhead cracks the radar's base structure, compromising the integrity of the entire mount. The second drone, arriving 7 seconds later, finds the weakened metal and tears the entire assembly apart with brute force. The 40-ton antenna array, designed to survive winds of 150 kilometers per hour, collapses like a house of cards under the shockwave. The battery is now completely blind at 0448 and 45 seconds. Scythe number 13 finds pay dirt on the 5P85TE2 launcher. 40 tons of sophisticated military hardware takes a direct hit just above missile tube number 3. The warhead punches through 20 millimeters of armor plate and detonates inside the magazine. The 48N6E missile's solid propellant, which is stable under normal storage conditions, becomes violently unstable when exposed to the shock of a high-explosive detonation. It ignites instantly. Solid rocket propellant burns at roughly 2,800 degrees Celsius, turning the inside of the launcher into a blast furnace. The missile tube, designed to channel thrust downward during a controlled launch, now channels it upward and outward in every direction. The pressure spike hits 300 atmospheres in 0.3 seconds. The tube ruptures catastrophically. Burning propellant sprays across missile tubes 2 and 4, heating them to the point of auto-ignition. In 1.3 seconds, 1,200 kilograms of propellant converts 3 missiles worth $4.5 million into the world's most expensive fireworks show. At 0449 and 10 seconds, the last 3 Beaver drones converge on the southern Big Bird radar. 3 impacts, 3 detonations, and 1 inevitable result. The radar, already damaged by flying shrapnel from the burning launcher nearby, takes 60 kilograms of high explosives in rapid sequence. It does not just collapse, it effectively disintegrates. Fragments of the antenna array rain down across a 200-meter radius, embedding themselves in the soil like jagged steel seeds. At 0450 and 35 seconds, the Sukhoi Su-35S fighters finally arrive overhead. The flight leader's radar shows absolutely no returns for the S-400 battery that should be guiding him. The radars that would normally be painting the sky are now burning wreckage on the ground. Visual contact reveals the full scale of the catastrophe. 4 distinct fire sources are visible from altitude. Black smoke columns rise 500 meters into the morning air. Secondary explosions are still cooking off as ammunition stores detonate in the heat. The pilots circle once, confirming what their sensors already show. The S-400 battery that protected Western Crimea for 3 years was completely destroyed in just over 3 minutes. 17 drones built in a basement, powered by lawnmower engines and guided by smartphone processors, have proven that in modern warfare, ingenuity is the great equalizer. The economic exchange rate of this engagement is staggering. A total Ukrainian investment of roughly $425,000 has just erased $500 million of Russian strategic assets. That is a return on investment of over 117,000%, a number that signals a fundamental shift in how wars are fought and won. At 0956 hours local time, a solitary Ukrainian MiG-29 Fulcrum was clawing for altitude through the dense cloud layer at 1,000 feet toward the hostile sector designated as Ork. The pilot's mission objective was deceptively simple: deliver a payload of precision-guided munitions to obliterate a Russian logistics hub and ammunition depot that had been fueling the offensive in the south. The flight had been a textbook routine for the past 12 minutes, but unknown to the pilot, a Russian S-400 Triumph battery positioned near Melitopol had just achieved a hard radar lock on his airframe at a range of 120 kilometers. The steady, high-pitched tone of the radar warning receiver in his headset hit him like a physical punch to the gut, instantly spiking his heart rate from a resting 70 to 140 beats per minute. The Russian operators hadn't just detected him, they had already launched. A 48 N-6 missile, 180 kilometers of explosive bad news, was already accelerating past Mach 2 in its first second of flight, burning through solid propellant at a rate that would make a drag racer weep. The mathematics of the engagement were brutal and unforgiving. At this specific range and closure rate, the pilot calculated an impact in exactly 80 seconds, maybe 90 if the laws of probability decided to be generous today. But in the cockpit, hope is not a strategy. The pilot immediately yanked the control stick hard to the right while simultaneously punching the chaff dispense button, forcing the MiG into a 90-degree aspect angle relative to the incoming radar beam, a desperate maneuver pilots call notching. He held the aircraft in a stomach-churning perpendicular, heading for 8 agonizing seconds while the countermeasure system spit out programmed bursts of aluminized glass fibers. These dipoles created a slowly expanding cloud moving at the ambient wind speed, with each individual strip reflecting radar energy like thousands of tiny mirrors, effectively making one 20-ton aircraft look like a squadron of 100 ghosts on the enemy scope. The Russian system's algorithms frantically tried to sort the fighter from the false returns and the ground clutter, but at this precise aspect angle, the physics of Doppler processing turned against them. The reason this maneuver worked is rooted in the fundamental physics of how the S-400's radar actually sees the world. The system uses Doppler processing to separate moving targets from the static background noise of mountains and trees by measuring the frequency shift of the radar return. Essentially the same principle that makes a passing ambulance siren change pitch. However, when a pilot flies perfectly perpendicular to the radar source, the relative velocity toward or away from the dish becomes zero. To the Doppler processor, the MiG-29 suddenly stops looking like a speeding fighter jet and starts looking exactly like a stationary mountain, causing the system to filter it out as ground clutter. The track quality on the Russian screens degraded from solid to intermittent, and finally to lost. The 48 N-6 missile, suddenly deprived of mid-course guidance updates, switched to its backup inertial mode, flying blindly toward the last predicted intercept point where the computer thought the plane should be. But the pilot, knowing that physics doesn't negotiate, had already changed course and was diving for the deck. The missile's onboard active radar seeker activated in the terminal phase, searching for a target that was now 2 kilometers away and obscured by a wall of chaff. Its proximity fuse found nothing but a cloud of falling aluminum rain, and the warhead detonated harmlessly, sending thousands of tungsten fragments shredding through the empty sky. The pilot leveled off at 500 feet, checking his 6 o'clock through the mirrors. The Russian Gravestone radar uses thousands of individual transmitter-receiver modules that can steer their beam electronically, jumping from the horizon to the zenith in microseconds. Unlike older Soviet systems that give up when they lose a track, this digital predator remembers. It stores the target's last position, heading, and speed, calculates a probability box of where the aircraft likely went, and starts searching there first. Pilot had bought himself maybe 30 seconds of life, but the clock was already ticking down again. The Russian operators at the S-400 command post were already adapting to the situation by switching their engagement logic to a different radar mode. And that is when they activated bistatic mode, turning the pilot's clever escape into a mathematical trap. In bistatic mode, the radar system effectively splits itself in two. The massive transmitter stays at the original site near Melitopol, blasting out energy, but a passive receiver sits 40 kilometers away at a completely different angle. Think of it like a dark room. Normally, a radar is like holding a flashlight where the bulb and your eyes are in the same place. If the target hides behind a mirror or angles away, you see nothing. Bistatic mode puts the flashlight in one corner while a second observer watches from across the room. Suddenly, you can see shadows, deflections, and reflections that were mathematically invisible before. The MiG's radar warning receiver only detected the main transmitter's signal hitting his airframe, giving the pilot no indication that a silent receiver 40 kilometers away was catching his radar reflection like a mirror catching sunlight around a corner. The geometry meant that even at 500 feet below the primary radar's horizon, the signal bounced off the aircraft's fuselage and traveled to the offset receiver from a completely different vector. The return signal was weak and intermittent, but it was enough to build a fire control solution. They had him again. This time, however, they didn't launch immediately. They had something much more sinister in mind. At 10:03 hours, a Buk M3 medium-range missile system received the data link it had been waiting for. The crew had been positioned to cover this exact geographic choke point, a slight rise overlooking a valley that the MiG would have to transit in exactly 90 seconds to reach its target. The S-400 had effectively acted as a spotter, handing off the target to the hidden killer. The automated systems on the Buk M3 took over with cold mechanical precision. The 9S-36M engagement radar went from cold standby to fully radiating in 3 seconds, its phased array antenna already physically slewed to the exact bearing where the MiG would appear. This wasn't random hunting. This was a calculated execution. The Central Battle Management computers had calculated not just where the target was, but where it would be, accounting for terrain masking, the MiG's fuel consumption profile, and even pilot psychology. Ukrainian pilots historically followed the same valley through this sector because it offered the best terrain masking against long-range threats. But today, that predictability was about to become a death sentence. The pilot's radar warning receiver exploded with a new urgent cadence. Buk acquisition tone, signal strength maximum, track mode achieved. He had been ambushed, and at this range, the engagement envelope gave him maybe 4 seconds before missile launch. The geometry was perfect for the Russians and catastrophic for the Ukrainian. He was trapped in a narrow valley with ridge lines on both sides. He couldn't dive because he would hit the ground. He couldn't climb without exposing himself to every surface-to-air missile within 50 kilometers. The Buk had him in a tactical box where every available option led to a smoking hole in the ground. 2 9M317M missiles erupted from their launch tubes, accelerating so violently they broke the sound barrier before they even cleared the surrounding tree line. Each missile weighed 690 kilograms and was capable of pulling 35 Gs in the terminal phase, turns that no human pilot could hope to outrun. The pilot watched the smoke trails climb on his missile warning system, his brain frantically calculating the intercept geometry. At current speed and altitude, impact would occur in 31 seconds. What made the Buk M3 truly terrifying in this scenario was its guidance philosophy. Unlike older systems where you could break the radar lock and the missile would go stupid, these modern interceptors used command guidance until the final seconds. The ground radar fed them constant course corrections via data link. Breaking the lock momentarily meant nothing. The missiles would just fly on inertial navigation until the data stream reconnected. The pilot had one option that might work, and it was going to hurt. He pulled the control stick deep into his stomach while ramming the throttles past the detent into full afterburner, trading all his carefully hoarded kinetic energy for altitude. The MiG rocketed upward in a maximum performance climb, the G-meter pegging at 7.5. At this load factor, the aircraft effectively weighed 7.5 times its normal mass. The pilot's G-suit inflated instantly, squeezing his legs and abdomen with pneumatic pressure to keep the blood in his brain, but the gray curtain of unconsciousness started creeping in from the edges of his vision anyway. Through the narrowing tunnel of his sight, he watched the altimeter unwind. 2,000 feet, 3,000, 4,000. At 4,500 feet, he fired every remaining chaff cartridge in his dispensers while rolling the aircraft inverted and pulling through the vertical. The MiG traced a perfect barrel roll while the aluminum strips created a radar snowstorm behind him. The first missile tried to follow the radical maneuver, but its control surfaces couldn't match the instantaneous roll rate of the fighter. It passed 100 meters below the canopy, close enough that the pilot could visually see its control fins working to correct the error. But the second missile was smarter. Its guidance computer had predicted where the MiG would be at the bottom of the roll and adjusted its trajectory to intercept. The pilot had anticipated this evolution. Instead of completing the roll as a standard evasive maneuver, he pushed negative Gs halfway through the rotation, bunting the nose toward the ground in an unpredictable direction. The missile corrected hard, but physics intervened. It was moving too fast to adjust to the sudden vector change. It overshot the aircraft by 200 meters, its proximity fuse finding nothing but chaff and empty air. He had survived the ambush, but the maneuver had cost him dearly. Fuel consumption during the max afterburner climb had burned 300 kilograms in just 40 seconds. His airspeed had dropped to 180 knots, barely above stall speed with the heavy weapons load still attached to his wings. And the Buk crew wasn't done. They were already reloading. The 9T-243 transport loader vehicle backed up to the launcher, its hydraulic crane already swinging a fresh missile container into position. The Russian crew had drilled this evolution hundreds of times. It was muscle memory and mechanical precision. The commander knew the pilot would still be in range, still be slow from his defensive maneuvering, and still be vulnerable. He watched the automated loading sequence while tracking the slow-moving MiG on his engagement screen. The Ukrainian was climbing again, this time toward his weapon release altitude. He needed 15,000 feet for the GBU-39 small-diameter bombs to achieve their maximum glide range. That climb would take 90 seconds. The reload would be complete in 45. The math was simple. The Russian crew would have a second shot before the Ukrainian could drop his payload. The third missile launched just as the pilot reached 14,000 feet, followed immediately by a fourth. But in their haste, the Russian crew had made a critical tactical error. They had fired both missiles simultaneously instead of staggering them. It seems like a small mistake to the uninitiated, but in air combat, small mistakes determine who goes home to their family and who becomes a smear on the landscape. By firing both missiles at the exact same moment, they created a single defensive problem for the pilot instead of two sequential ones. The missiles would arrive at the same millisecond, meaning one evasive maneuver could defeat both. The pilot held his course for 12 agonizing seconds, staring down the barrel of the approaching threat while letting his weapon's GPS receivers acquire satellite lock and download the target area weather data. The GBU-39s needed this initialization for their inertial navigation systems. Without it, they would be nothing more than expensive dumb bombs. At 14 seconds to impact, with the missiles closing at 4 times the speed of sound, he pickled both weapons. The GBU-39 separated cleanly from the pylons, their diamond-shaped wings deploying as the pilot immediately rolled inverted and pulled toward the Earth. 7 Gs crushed him down into the ejection seat as the missiles tried to follow the plummeting heat signature. But physics is absolute. A missile traveling at Mach 4 needs almost 2 kilometers of airspace to make a 180-degree turn. It is like a freight train trying to follow a motorcycle that just made a U-turn on a dime. The MiG could flip directions in 200 meters, while the missiles, carrying all that hypersonic momentum, carved enormous, sluggish arcs through the sky trying to come back around. Both 9M, 317M interceptors overshot, their proximity fuses triggering on empty air as they sailed past the point where the MiG had been just 3 seconds ago. The pilot leveled off at 8,000 feet, his eyes scanning the instruments. Fuel was critical at 1,850 kilograms. The extreme maneuvering had burned through his reserves faster than anticipated. He had just enough kerosene to reach Ukrainian airspace if he flew straight and level, if he didn't light the afterburners again, and if nobody else engaged him. That is exactly when his threat receiver picked up something new, something that made the previous surface-to-air threats look manageable. A search radar from a Sukhoi Su-35S Flanker E appeared on the scope. bearing 240, range 85 kilometers, and closing fast. The fighter had been vectored by the same integrated air defense network that had guided the Buk. This wasn't a random interception, this was coordinated hunting, and he was the prey. The Su-35 pilot saw the MiG on his Irbis-E radar as a bright, struggling dot crawling across his display at a pathetic speed of 280 knots, barely moving in the world of supersonic warfare. The Russian pilot pushed his throttles forward, accelerating through 500 knots. At this closure rate, he would be in optimal missile range in 3 minutes. The Ukrainian pilot had survived the S-400 and defeated the Buk, but those victories had cost him everything. He had no speed, minimal fuel, and no more tricks up his sleeve. The Su-35 barreling towards him was everything the MiG-29 wasn't: modern, powerful, and designed specifically to dominate the beyond visual range arena. The aircraft's radar could track 30 targets simultaneously while engaging 8, and right now, all that processing power was focused on just one depleted Ukrainian jet. The Ukrainian fighter appeared on the Russian screen in perfect detail. Altitude 8,000 feet and decreasing. Speed now down to 270 knots, heading 247 degrees toward home. At 60 kilometers, the Su-35 achieved a hard lock with an R-77 active radar-guided missile. The weapon had a theoretical range of 110 kilometers, but at that distance, the probability of intercept dropped below 50%. The Russian pilot decided to close the distance to ensure the kill. The Su-35 pilot, now critical on fuel, was forced to break off the engagement, leaving the battered Ukrainian MiG to run the gauntlet toward home just as the GBU-39s entered their terminal phase. At 10:14 hours, skimming the farmland at 50 feet, the MiG flew directly into the kill zone of a ZSU-23-4 Shilka that had been silently tracking its approach. The radar-guided anti-aircraft gun opened fire, unleashing a stream of 23mm high-explosive incendiary rounds at a rate of 3,400 rounds per minute, forcing the pilot to roll inverted and pull negative Gs so close to the ground that the Shilka's radar struggled to distinguish the aircraft from the earth. 3 rounds still punched through the vertical stabilizer and severed the primary hydraulic line. But as the MiG limped across friendly lines with 0 hydraulic pressure and 30 kilograms of fuel remaining, the bombs finally reached their target at the Orakov depot. The first weapon's penetrator cap punched through 3 feet of reinforced concrete before its 16 kilograms of AFX-757 explosive detonated, triggering a massive secondary chain reaction within the stored 152mm shells that vaporized 500 tons of ammunition in 0.1 seconds. Back at the forward airfield, the pilot performed a manual gear extension and touched down at 180 knots, blowing both main tires and grinding to a halt just 50 meters from the end of the runway, completing a mission where $80,000 in munitions successfully destroyed $2.4 billion worth of Russian logistics equipment, yielding a return on investment of roughly 3 million%. This mission forced a measurable tactical shift in the air war, as Russian pilots became noticeably more hesitant to engage near the border, fearing that every low-altitude radar contact could be another bait-and-switch trap designed to pull them into surface-to-air missile envelopes. Meanwhile, Ukrainian intelligence noted that the S-400 operators began radiating for significantly shorter intervals, terrified of the anti-radiation missiles that often follow these precise strike packages. In the grim calculus of attrition warfare, the survival of this specific pilot meant that the hard-won physics lessons of defeating modern Russian air defenses could be passed on to the next generation of aviators, making the entire Russian air defense network slightly less effective with every passing day. At 0540 local time, the first wave of Ukrainian Beaver drones was racing toward the Shahed assembly complex outside the Donetsk airport. But in order to even make it there, they first had to clear a path through one of the densest air defense networks in the world. And though the Russian operators had the drones locked up on their screens, it was exactly what the Ukrainians wanted. The 3 Beavers lifted out of a ravine northwest of Donetsk and immediately started taking hits from a Russian Tor air defense system. 5 kilometers ahead, 2 missiles punched out of the tree line and arched straight at the lead drone. The operator yanked the Beaver down to 1 meter off the deck and started weaving between drainage ditches while his latency spiked past 300 milliseconds. The first missile tried to follow, could not handle the aggressive angle change, and ate dirt 20 meters to his left. The second one passed overhead and detonated close by, close enough that the shockwave knocked his video feed sideways for half a second. Behind him, the other two beavers scattered, forcing the Tor to pick targets. All three drones were still flying. Now their telemetry showed something worse than a missile lock, a slow, steady sweep pattern. This is because the Russian Tor is specifically designed to take out things like beavers. Its radar does not need to see you clearly. It just needs to catch the way your propeller blades change the radar signal's frequency when it bounces back. And then it starts walking missiles onto you using steering commands every few hundred milliseconds. The lead Ukrainian operator knew this mechanical quirk, which is why he kept the drone in the dirt where the radar energy bounces off the ground and creates false readings about speed and position. But flying this low meant burning battery faster due to the increased air density and constant control adjustments. Every meter of altitude he gave up was seconds of precious flight time he would need later. The Tor crew panicked. Instead of waiting to assess and reacquire a clean track, they ripple-fired all 6 remaining missiles in under 4 seconds. A full magazine dump that lit up the horizon like a fireworks show. This was exactly what the Ukrainian operators had been hoping for. See, the Tor guides its missiles using something called command link updates. The ground radar continuously tells each missile where to go via radio signals, making hundreds of tiny course corrections per second. But the Tor's guidance transmitter can only talk to 2 missiles simultaneously with full precision. When you launch 8 missiles in rapid succession, the physics of the system breaks down. The last 6 get degraded commands, recycled targeting data, or sometimes no updates at all for critical seconds. The Ukrainian operators had trained for this exact flaw. All 3 beavers suddenly climbed to 15 meters. Not high enough to make easy targets, but high enough to get out of the ground clutter. That was confusing the Tor's overloaded guidance channels. Then they did something counterintuitive. They flew straight for exactly 2 seconds before dropping back to the deck. Those 2 seconds of predictable flight made the Tor's computer commit to intercept solutions that would be useless once the drones dove again. 2 missiles plowed into empty air. 2 hit the ground trying to follow. The last pair went ballistic. Their guidance links completely severed, arcing harmlessly into the distance. The Tor was now empty, requiring 9 minutes to reload minimum. The beavers pressed forward. The Tor crew would already be loading fresh missiles soon, probably arguing about whether they had scored hits since all 3 drones disappeared into the ground clutter. That confusion meant the Tor could not fight back now and would hand off the track to something bigger. That something bigger was already happening. The Buk M3 radar, 5 miles behind the Tor, had started painting the corridor with search pulses. Not trying to guide a missile yet, just building a picture of what was moving where. Unlike the Tor, which shoots first and asks questions later, the Buk takes its time, watching you fly for multiple sweeps to learn your patterns. The Ukrainian drone operators could tell from the way their links degraded in waves instead of spikes. Each wave meant the Buk was refining its track, getting ready to either engage directly or feed targeting data to the S-400 command post at the airport. The lead beaver dropped behind an abandoned gas station as the operator checked his battery, 72% and falling faster than the mission plan because of all the extra maneuvering. The second wave of FPV drones should already be launching from the forward position to hit the Tor before it could reset. The lead beaver emerged from behind the gas station straight into the Buk's search pattern. The operator's signal indicator started doing something different. Instead of sharp interference spikes like with the Tor, this was a steady pressure that made his video compression work harder. The Buk was taking its time, using its more powerful radar to track the drone, even when it ducked behind obstacles. Every few seconds, the radar would complete another rotation, and each time it did, it got a better idea of where the beaver was heading. The Ukrainian operator pushed his drone under a set of abandoned fuel pipes, not because it would hide him, nothing could hide from a radar that powerful, but because it would mess with the Buk's math. See, the Buk needs consistent speed readings to predict where you will be when its missile arrives. Every time the beaver flew at an angle to the radar beam or changed speed suddenly, it forced the Buk to recalculate. These were not huge errors, but they added up, creating timing gaps that might mean the difference between a direct hit and a near miss. Behind the lead drone, the other 2 beavers were having their own problems. The second operator's latency had climbed to 160 milliseconds, not from jamming, but from the Buk's search pulses interfering with his control packets. The lead operator pushed his beaver straight under the power lines, using the metal towers and cables to create what radar operators call shadowing, brief moments where the radar cannot see through all the metal. For a big aircraft, this would not matter. For a drone the size of a large bird, every bit of interference helped. The Buk's track quality dropped from solid to intermittent, but the Buk was not working alone. Somewhere behind it, the S-400 command post at Donetsk Airport had started cycling through its sector scans, trying to figure out what the hell was happening based on the fragmented data it was getting. The S-400's radar was designed to track ballistic missiles and stealth fighters at hundreds of kilometers. Asking it to track beavers at treetop level was like using a telescope to find ants. But it didn't need to track them directly. It just needed to coordinate to make sure somebody had eyes on the target at all times. The lead operator saw his latency stabilize briefly as the beaver broke through the worst of the Buk's scan zone. But breaking contact was not the same as being safe. The Buk would reacquire on the next sweep, and when it did, it would have a better idea of where they were heading. The math was simple. Every kilometer closer to Donetsk meant less reaction time. 5 minutes after the beavers scattered, 6 Ukrainian FPV drones screamed in from the northwest at 50 meters altitude. Their operators had been watching the Tor crew scramble to reload, counting the seconds since the last missile launch. The Tor could fire again in about 90 seconds if nothing interrupted the process. The lead FPV dropped to grass height and accelerated straight at the Tor while his wingman stayed higher to split the radar's attention. That is because the Tor's computer can only process so many targets moving in different directions before it starts making mistakes. 2 FPVs might not be enough, but 6 FPVs flying completely different profiles, high, low, fast, slow, straight, and weaving, turned the Tor's targeting computer into a confused mess of half-complete firing solutions. The Tor turret started spinning, trying to slew on to the nearest threat, but by the time it locked on one FPV, 2 more had appeared from different angles. The crew inside was probably screaming at each other, trying to manually override the automatic target selection. Too late. The first FPV slammed into the Tor's left side, right where the missile magazine feeds into the launcher. The explosion ripped through the thin armor. The second FPV hit the sweet spot under the turret ring where all the electronic cables were. The turret stopped to mid-rotation and locked up as smoke poured from every vent. The Tor was done. The celebration lasted exactly 3 seconds because that is when the Buk battery decided to remind everyone it was still watching. 2 9M 317 missiles launched from behind a tree line, their rocket motors lighting up the morning haze. These were not the nimble short-range interceptors the Tor used. Buk missiles are telephone poles with wings designed to reach out 40 kilometers and swat fighter jets. Using them on FPV drones was like hunting mosquitoes with a sledgehammer. But the Buk crew did not care about efficiency. They cared about keeping Ukrainian drones away from their radar. The FPV operators saw the launches and did the only thing that made sense. They ran for the deck and scattered. Buk missiles are fast, like Mach 3 fast, but they are optimized for targets that fly predictable paths. The first missile tried to track a Ukrainian beaver that was bouncing between abandoned buildings. It could not handle the angular rate change and detonated early when its proximity fuse got confused by ground returns. The second missile almost got lucky. It passed close enough to a beaver that the blast wave tumbled it, but the operator managed to recover control just before hitting the ground. The 4 FPVs survived. 2 had been knocked around badly enough that the shock waves from the near misses crashed them into the ground, but 4 was enough for what came next. The 4 surviving FPVs regrouped behind a collapsed building, while their operators figured out the approach. The Buk M2 still had 4 missiles left. The lead FPV operator made the call. Straight in. The Buk's crew was expecting the evasive FPVs to use terrain masking and pop-up attacks. They were not expecting a drone to fly directly at them like a missile. Sometimes the dumbest plan works because nobody expects you to be that dumb. All 4 drones accelerated to maximum throttle and spread into a line formation, each drone about 50 meters from the next. The Buk radar, mounted high on its mast to see over terrain, started tracking all 4 simultaneously. But here was the problem. The crew could not launch missiles at all of them. They had to pick 1 or 2 and hope those were the ones that mattered, since the probability of intercept meant at least 1 drone would leak through. The Ukrainian operator watching through the lead drone could actually see the radar antenna starting to focus its beam, probably locking up his drone for the shot. That is when the third wave hit from behind. 3 more Ukrainian drones had been circling outside the engagement zone, waiting for the Buk to commit. They came in from the Buk's rear quarter, where the radar had a partial blind spot due to the vehicle's own superstructure. The Buk crew had about 5 seconds to decide. Engage the FPVs, screaming at their face, or spin the radar around to deal with the ones coming in from behind. They could not hit both. The radar started to slew toward the rear threat, which meant for about 2 seconds, nobody was tracking the forward-facing drones. The lead operator saw his opening and dove straight at the radar array. The Buk crew realized their mistake and tried to traverse back, but radar masts do not move like fighter jet cannons. They rotate slowly and deliberately because precision matters more than speed. The first FPV hit the radar dead center, punching through the delicate transmitter arrays and into the cooling systems behind them. The explosion was not huge. FPVs do not carry much explosive, but it was enough. The radar array folded like a broken umbrella, sparking and burning as high-voltage cables shorted out. A second FPV hit the base of the mast for good measure, ensuring the whole assembly would need replacement, not just repair. Buk was blind. It could still launch missiles, but without its radar, it would be firing on last-known positions and prayers. The crew would probably abandon the vehicle within minutes, rather than sit there helpless. The Ukrainians made the decision for them as 2 more drones slammed into the stricken system. But the Ukrainian operators were not celebrating yet. With the Tor and Buk down, the S-400 system was the only thing left protecting the Shahed warehouse. And S-400s do not go down easy. The S-400 command post at Donetsk airport was having the worst morning of its existence. The system was designed to track ballistic missiles at 400 kilometers, not drones bobbing through industrial districts at highway speed. Without the Tor providing close-range coverage and the Buk handling mid-range attacks, the S-400's operators were trying to do everyone's job with equipment built for something completely different. That is when the Ukrainians played their ace. A heavy Ukrainian Ram 2X loitering munition, basically a flying bomb with a camera, had been circling at 2,000 meters altitude for the past 20 minutes, way outside the engagement zone. Now it dove not at the S-400 launchers, but at the command post itself. The 55K6 is the brain of the entire battalion. Neutralize it, and the launchers become very expensive lawn ornaments. The munition hit the command post roof right above the main processing bay, where all the computers and communications gear lived. The explosion was not spectacular, no Hollywood fireball, but the effects were immediate. Every screen went dark, every radio went silent. The entire S-400 battalion lost its coordination in an instant. Individual launchers still had local controls, but without the command post telling them what to shoot at, they might as well have been museum pieces. With the command post now down, the S-400 launcher was now easy prey. Before any drone entered the now cleared corridor, Ukrainian commanders executed something most people never hear about: combat airspace deconfliction. See, the problem with success is that everyone wants to pile through the gap you just created. Without rigid control, you get friendly drones crashing into each other, or operators jamming each other's signals trying to use the same frequencies. In this business, this is called blue on blue, and it has taken more drones than some Russian air defense systems. To prevent this, the Ukrainians divided the corridor into layers like a cake. Beavers would fly at 50 to 100 meters. Any FPVs in the area stayed below 20 meters. And loitering munitions held at 200 meters and above. Nobody was allowed to freestyle it. You flew your lane at your time, or you did not fly at all. At 0600 local time, the first Beaver crossed the commit line into Donetsk airport's perimeter. The operator could see the Shahed warehouse clearly now, a rectangular building with a curved roof looking exactly like every other military storage facility, either Shaheds being prepped for launch or battery systems charging. Either way, it was about to end. The Beaver dove from 100 meters to 20, accelerating as it dropped. Through the camera, the operator could see Russian soldiers running between buildings, some pointing at the drone, a few raising rifles. Small arms fire was not really a threat. Hitting a drone moving at 80 kilometers per hour with an AK is like hitting a baseball with a toothpick. The real danger was the warehouse itself. If the Ukrainians were right about what was inside, the secondary explosions could swat their own drones from the sky. The first Beaver hit the warehouse roof at a shallow angle, punching through the thin metal and detonating inside the main assembly area. The explosion looked small at first. A flash of light through the windows, some smoke. Then the secondary explosion started. Something inside, probably Shahed fuel cells, went up like a fuel air bomb. The second and third Beavers were already inbound when the shockwave hit them. The second operator managed to maintain control and dove his drone through a hole in the wall, adding its payload to the inferno inside. The third Beaver got tumbled by the blast wave, recovered, but could not find a way through the flaming smoke. Its operator made the call to hit an intact section of the building, ensuring complete destruction. The secondary explosions did not just destroy the Shahed inventory, they turned the assembly complex into a structural nightmare for Russian engineers. The intense heat from burning lithium-ion batteries and composite fuselages created temperatures exceeding 1,200 degrees Celsius, hot enough to warp the steel girders supporting the roof. What was once a precise assembly line for long-range attack drones became a twisted cage of melting metal. The fire suppression system, designed for standard industrial accidents, was completely overwhelmed by the chemical intensity of the burning warheads. Instead of extinguishing the flames, the water from the ruptured sprinkler pipes turned into superheated steam, adding pressure to the already failing structure until the roof collapsed inward. This collapse sealed the fate of any equipment that might have survived the initial strike, burying high-precision milling machines and carbon fiber molds under tons of debris. Russian emergency crews arriving on the scene could do nothing but set up a perimeter and watch it burn. They knew that dousing lithium fires with standard water hoses often makes the reaction more violent, releasing hydrogen gas that can trigger further explosions. The facility that was supposed to terrorize Ukrainian cities was now terrorizing its own neighborhood, sending toxic black smoke drifting over the Donetsk airport and grounding all Russian military flights for the next 6 hours. At 0514 hours local time on a mist-shrouded morning over the Black Sea, a Russian Sukhoi Su-30SM flanker jet banked sharply at 12,000 feet, its pilot scanning the dark waves below with the predatory confidence of a man sitting in a $50 million apex predator. He had been vectored to this specific grid square near Cape Tarkhankut to intercept a low-speed surface contact that Russian radar operators on the Crimean coast had dismissed as a glitch for the last 20 minutes. To the pilot, this was not a combat mission. It was merely target practice against a helpless piece of floating plastic that had wandered too close to the bear's den. But what the pilot did not know, and what he would not realize until it was catastrophically too late, was that the contact below him was not just a lost surveillance buoy or a piece of driftwood. It was a next-generation Ukrainian sea drone, specifically modified for this exact scenario. And it was being piloted via satellite link by an operator sitting comfortably in a bunker 300 kilometers away who had been waiting for this specific jet to make a mistake for 3 days. In exactly 97 seconds, the hunter would become the hunted, and the physics of modern aerial warfare were about to be rewritten by a boat that cost less than the jet's ejection seat. The Su-30SM is a marvel of super maneuverability, powered by two massive AL-31 FP turbofan engines with thrust vectoring nozzles that allow it to perform aerobatics that defy the laws of aerodynamics. But none of that mattered against the target he was stalking. The technical mismatch between the two combatants could not have been more stark or more deceptive, as the Russian jet represented the pinnacle of Soviet-era heavy engineering while the drone was a masterpiece of garage-style innovation. The Su-30SM relied on its massive N011 M-bars passive electronically scanned array radar, a system designed to track multiple fighter jets at ranges exceeding 100 kilometers, but which struggled immensely to distinguish a small, composite-hulled boat from the cresting waves of the sea surface. The drone, likely a variant of the Magura Vi-5 or the Sea Baby, was constructed almost entirely from radar-absorbent composite materials that gave it a radar cross-section similar to a small floating bird. This meant that the Russian pilot could not simply lock on with a long-range radar-guided missile from a safe distance. Instead, he was forced to descend into the thicker, turbulent air near the surface to visually acquire the target and engage it with his 30mm G31 autocannon. This was exactly what the Ukrainian operators wanted. They knew that forcing the jet down to 2,000 feet or lower stripped away its speed and altitude advantages, leveling the playing field and bringing the multi-role fighter into the engagement envelope of the drone's secret payload. The pilot, annoyed by the clutter on his radar screen, switched to his helmet-mounted sight, oblivious to the fact that he was flying a trajectory that had been mathematically modeled by his opponents weeks in advance. Down on the water, the sea drone sliced through the chop at 45 knots, its low profile making it nearly invisible against the dark water to the naked eye. This was not a standard kamikaze run where the drone would simply ram a ship. This was an air defense trap. The drone was equipped with a stabilized electro-optical sensor turret that was currently tracking the heat signature of the jet's massive engines against the cold dawn sky. The operator in the bunker watched the feed with a heart rate that remained remarkably calm, his hands resting on a controller that looked like it belonged to a video game console rather than a weapon of war. The video feed was transmitted via an encrypted Starlink terminal, a flat white dish integrated into the drone's hull that hopped frequencies thousands of times per second to punch through the heavy electronic jamming blanketing the sector. The Russian electronic warfare units on the coast were blasting static across the radio spectrum, trying to sever the link between the drone and its master. But the directional nature of the phased array antenna kept the connection alive, albeit with a latency of around 150 milliseconds. That split-second delay meant the operator had to anticipate the jet's movements rather than just react to them. As the roar of the jet's engines became audible over the drone's onboard hydrophones, the operator nudged the stick, executing a sudden erratic turn to the left, mimicking a panic maneuver to bait the pilot into a tighter, more aggressive turn. The Russian pilot took the bait with a predictability that bordered on professional negligence, rolling his massive aircraft inverted and pulling 4 Gs to bring his nose around for a gun run. At this altitude and speed, the Su-30SM burned fuel at a rate of 300 kilograms per minute, its engines screaming as they fought the thick, humid air of the marine boundary layer. The pilot armed his cannon, a weapon capable of spitting out 1,500 rounds per minute of high-explosive incendiary shells. Each shell weighed nearly 400 grams and traveled at a muzzle velocity of 860 meters per second. A single hit would turn the fiberglass drone into a cloud of splinters and burning lithium-ion batteries. But hitting a maneuvering boat that is only 5 meters long while flying at 600 kilometers per hour is exponentially more difficult than it looks in movies. The pilot had to account for the depression angle of the gun, the lead time of the bullets, and the erratic, wave-influenced movement of the target. He squeezed the trigger for a half-second burst, sending a stream of tracers tearing up the water 10 meters behind the drone. The spray of water from the missed shots washed over the drone's camera lens, momentarily blinding the operator, but the psychological effect was achieved. The pilot was now frustrated, target fixated, and rapidly losing situational awareness. He pulled up hard to avoid the water, his afterburners lighting up the pre-dawn gloom like twin blowtorches, unknowingly presenting a perfect infrared target to the surprise sitting on the drone's back. What the Russian intelligence briefings had failed to mention to their air crews was that Ukrainian engineers had begun retrofitting Select Sea drones with modified R-73 heat-seeking air-to-air missiles scavenged from grounded aircraft. These Soviet-era missiles, normally fired from the wing of a MiG-29, had been jury-rigged with custom rails and digital interfaces that allowed them to be fired from a surface vessel. The R-73 is a formidable weapon, featuring a cryogenically cooled infrared seeker capable of off-bore sight targeting, meaning it does not need to be pointed directly at the target to lock on. It steers itself with thrust vectoring paddles in its exhaust, allowing it to pull turns of up to 40 Gs, 10 times what the human body can withstand. As the Russian jet climbed away from its failed strafing run, it was essentially a massive heat source climbing against a cold background, the perfect thermal contrast for the missile's seeker head. The drone operator, seeing the jet's glowing exhaust nozzles on his thermal monitor, flipped a safety toggle on his console. A tone in his headset changed from a low growl to a high-pitched scream, indicating that the missile's seeker had achieved a solid lock on the starboard engine of the fleeing fighter. The trap was sprung, but the physics of firing an air-to-air missile from a bouncing boat added a layer of chaos that no simulation could fully predict. The launch sequence initiated at 0517 hours, just 3 minutes after the engagement began. The solid rocket motor of the R-73 ignited with a blinding flash that illuminated the dark waves for kilometers, instantly vaporizing the sea spray around the drone. The missile left the rail with a roar that momentarily swamped the drone's microphone, accelerating to Mach 1.5 in less than 2 seconds. On board the Su-30, the pilot's radar warning receiver remained silent because the missile was heat-seeking. Not radar-guided, there was no electronic emission to detect until the missile's motor was already burning. However, the jet's rear-facing missile approach warning system, which detects the ultraviolet plume of incoming rocket motors, suddenly screamed a warning that froze the pilot's blood. He reacted with pure instinct, slamming the throttle to maximum afterburner and banking hard to the right, while dumping a frantic sequence of magnesium flares. These flares burn at over 2,000 degrees Celsius, designed to seduce the missile's seeker away from the engine's heat. For a standard missile, this might have worked, but the R-73 has a two-color infrared seeker designed specifically to distinguish between the steady heat of an engine and the flickering intensity of a flare. The missile ignored the decoys, its guidance fins twitching rapidly as it calculated the intercept point, closing the distance at 600 meters per second. The Russian pilot, realizing the flares had failed, attempted a desperate high-G barrel roll, a maneuver designed to maximize the angular change relative to the missile, hoping to exceed the weapon's turning capability. The heavy fighter groaned under the aerodynamic stress, its wingtips flexing visibly. But physics is a cruel mistress. The missile, weighing only 105 kilograms compared to the jet's 25,000 kilograms, had a maneuverability advantage that no amount of pilot skill could overcome. The missile did not strike the fuselage directly. Instead, its proximity fuse detected the mass of the aircraft and detonated the 7.4-kilogram continuous rod warhead just 3 meters from the starboard engine. The explosion did not vaporize the plane, but it sent a rapidly expanding ring of tungsten alloy rods slicing through the titanium skin of the engine nacelle, severing hydraulic lines, fuel pipes, and the critical drive shaft connecting the engine to the accessory gearbox. Inside the cockpit, the master caution panel lit up like a Christmas tree, every system screaming failure simultaneously as the aircraft entered an uncontrollable yaw. The loss of the starboard engine, combined with the destruction of the hydraulic systems that controlled the flight surfaces, turned the super-maneuverable fighter into a ballistic brick. The pilot fought the stick with the desperation of a man who knows he has seconds to live, but the fly-by-wire system had lost its redundancy. The jet rolled inverted, the horizon spinning dizzyingly in the canopy. At 3,000 feet and falling, there was no altitude left to recover. The pilot reached between his legs and pulled the ejection handle, triggering a sequence of pyrotechnic charges that blew the canopy away and rocketed his K-36DM ejection seat out of the burning airframe. A moment later, the $50 million aircraft slammed into the Black Sea at nearly supersonic speed, the impact creating a massive geyser of water and debris that was visible for miles. The drone operator, watching the splashdown on his grainy monitor, did not cheer. He simply logged the timestamp and began the procedure to guide the drone back to base. This was not just a victory, it was a paradigm shift. For the first time in history, a cheap, unmanned boat had swatted a modern fighter jet out of the sky, proving that the era of uncontested air dominance was over. But as the parachute of the Russian pilot drifted slowly toward the cold water, a new set of problems was just beginning to unfold for the rescue teams scrambling from Sevastopol. At 0532 hours, the strategic situation shifted from a localized air defense incident to a frantic search and rescue operation that would compound the morning's disaster. Russian command at the Belbek Air Base, having watched their primary air superiority fighter disappear from radar screens, immediately scrambled a combat search and rescue package consisting of two Mi-8 AMTS Terminator assault helicopters and a Raptor-class patrol boat. The Mi-8 is a legendary workhorse, a 12-ton beast armored with titanium plating around the cockpit and redundant systems designed to take punishment that would ground lesser machines. However, sending a helicopter into a zone where a jet had just been shot down by an unknown surface-to-air threat is a decision fraught with extreme risk. The pilots flew low, skimming just 10 meters above the waves to mask their radar signature, their eyes glued to the water looking for the green dye marker and the tiny orange life raft of the downed airmen. The rotor wash from the massive 5-bladed main rotors whipped the sea into a frenzy of white foam, creating a distinct acoustic signature that traveled underwater for kilometers. To the passive sonar sensors of a second Ukrainian sea drone drifting silently 3 kilometers to the south, the approaching rescue team sounded less like a military operation and more like a dinner bell ringing in an empty house. This second drone was not the anti-air variant that had swatted the jet. It was a heavy strike configuration loaded with 450 kilograms of high explosives. It had been lying in wait, utilizing a tactic known as sleeping mode, where all active systems except for a passive hydrophone and a wake-up timer are powered down to conserve battery life and eliminate electronic emissions. This made it virtually undetectable to the electronic support measures on the Russian helicopters, which were blasting the spectrum with broadband jamming in a futile attempt to suppress a threat they couldn't see. When the acoustic signature of the rescue operation crossed a preset decibel threshold, the drone's onboard processor woke up the main systems. The operator, now drinking his second cup of coffee in the bunker, saw the telemetry light up green. The rescue operation had unknowingly entered a pre-planned kill box. The Russians were operating under the assumption that the area was sanitized, but in modern naval warfare, safe zones are a myth. The operator engaged the electric propulsion system, bringing the drone up to 30 knots, and steered a collision course toward the chaotic scene where the Raptor patrol boat was slowing down to fish the pilot out of the water. The Raptor-class patrol boat is a fast, maneuverable vessel designed for special operations and coastal patrols, capable of reaching speeds of 48 knots thanks to its water jet propulsion system. It is armed with a remote-controlled 14.5mm machine gun turret and features armored glass capable of stopping small arms fire. However, its hull is made of aluminum alloy, a material chosen for lightness rather than survivability against heavy anti-ship weapons. As the boat idled near the pilot's life raft, the crew was focused entirely on the recovery, their situational awareness narrowing to the few meters of water around the survivor. They failed to notice the low-profile wedge of the sea drone approaching from their stern blind spot, masked by the noise of the hovering helicopters and the choppy wake. It was only when the drone was 400 meters out that a sharp-eyed door gunner on the circling Mi-8 spotted the wake and screamed a warning over the radio. But physics, as always, is unforgiving of reaction times. The Raptor's captain slammed the throttles forward, the water jets churning the sea into a white froth as he tried to accelerate out of the danger zone. But an 18-ton boat does not accelerate like a sports car. The impact occurred at 0546 hours. The drone operator, utilizing the terminal guidance camera, adjusted his aim to strike the Raptor exactly at the waterline near the engine compartment, bypassing the thicker armor around the crew cabin. The 450-kilogram warhead detonated with a force that lifted the 17-meter boat almost entirely out of the water. The explosion was not merely a release of heat and pressure. It was a hydrodynamic event that sent a shockwave through the water moving at 1,500 meters per second, shattering the boat's keel and rupturing the fuel tanks instantly. The aluminum hull, unable to withstand the shearing forces, buckled catastrophically. Secondary explosions from the Raptor's own ammunition storage cooked off, sending tracers spiraling wildly into the morning sky. The hovering Mi-8, caught in the sudden updraft of heat and debris, was forced to pull collective hard and bank away to avoid shrapnel ingestion into its engine intakes. The rescue mission had just become a mass casualty event. The Russian pilot, who had been seconds away from salvation, was now bobbing in oil-slicked water, watching his ride home burn to the waterline. This was the brutal calculus of asymmetric warfare. A $200,000 drone had just traded itself for a $2 million boat and compromised a search and rescue operation, compounding the enemy's logistical nightmare exponentially. The strategic fallout of this morning's engagement would ripple far beyond the Black Sea. In less than an hour, the Russian Black Sea Fleet had lost a $50 million air superiority fighter and a $2 million patrol boat, along with the priceless sense of invulnerability that their pilots once held. The economic disparity was staggering. The total cost of the Ukrainian operation, including the 2 drones and the logistical support, was roughly $500,000. The Russian losses exceeded $52 million, a return on investment of over 10,000% for the Ukrainians. And shortly before 10:30 in the morning on December 14, 2024, a solitary Ukrainian Lyuty drone was tearing through the airspace above the Sea of Azov, homing in on a Russian asset of immense strategic value. Positioned on the tarmac at Yeysk Air Base, roughly 150 kilometers away, sat a Russian Ilyushin ELL-38N. This was far more than a standard transport or patrol aircraft. It represented the sole remaining platform in the entire Black Sea theater, capable of tracking modern NATO submarines. Intelligence gathered from satellite imagery just 6 hours prior revealed ground crews busily stripping the engine covers, signaling that the aircraft would be fully operational by early afternoon. This window represented the only opportunity to neutralize the target on the ground before it could take to the skies and become an airborne problem that Ukrainian forces could not solve. The countdown had already begun. As the Lyuty crossed the coastline and dropped to an altitude of 50 meters above the churning gray waters, it faced nearly 300 kilometers of open sea. Moving at speeds exceeding 200 kilometers per hour, the transit would require over an hour of absolute electronic silence. The drone's composite fuselage was engineered to diffuse radar energy rather than reflect it, acting like a stealthy shadow rather than a beacon. Flying at such a low altitude, the curvature of the Earth became the drone's greatest ally. While radar waves travel in straight lines, the planet's surface curves away, creating a blind spot known as the radar horizon. By hugging the waves, the drone remained effectively invisible to every Russian search radar stationed within 200 kilometers. For that hour over the water, the aircraft essentially vanished from the known world. However, the mission profile shifted dramatically once the drone made landfall east of Primorsko-Akhtarsk, 70 kilometers from its destination. The phase of invisibility ended the moment it crossed the shoreline, entering a zone where the Russian defense network had prepared a specific countermeasure. Attached to a cellular tower near the village of Stut-Tarovskaya was a device masquerading as standard telecom hardware. A gray, nondescript cylinder, roughly the dimensions of an industrial pipe, housed a cluster of omnidirectional microphones and a processor running advanced acoustic classification software. This system is Russia's solution to the problem of low-flying radar evaders. You might not be able to see them on a screen, but you can certainly hear them coming. The Lyuty is powered by a turbojet engine that prioritizes thrust over stealth. At a distance of 100 meters, the engine emits a noise level comparable to a chainsaw or a heavy motorcycle accelerating. Compressor blades generate a high-frequency whine, while the combustion chamber produces a deep, resonant rumble. In the frigid, dense air of a Russian winter, these sound waves propagate with exceptional efficiency, traveling much farther than they would in the heat of summer. The sensor picked up the initial acoustic signature with a signal strength that was faint but distinct against the quiet rural backdrop. Russian engineers had tuned these microphones to detect the specific auditory footprint of a drone engine from kilometers away. The onboard algorithm immediately processed the sound, dissecting it into individual frequencies to analyze the spectral fingerprint. It looked for the telltale harmonic ratios that distinguish a turbine engine from a piston engine or a passing truck. The classification result was generated in just over a second, identifying the sound as a hostile unmanned aerial vehicle with high confidence on a specific compass bearing. A single microphone can only provide a direction, not a precise location. It is akin to hearing a shout in the dark. You know where to look, but not how far away the source is. To solve this, Russia has established a chain of over 200 such sensors along the coast, spaced a few kilometers apart, to create a dense acoustic net. Within moments, 3 additional sensors reported contact on varying bearings. The central network fused these lines of bearing, using triangulation to pinpoint the source where the lines intersected. A track materialized on regional defense screens, placing the hostile drone within a 50-meter radius and updating its position constantly. The Liuti continued its flight path, oblivious to the fact that it had been detected. It carried no systems to alert it to acoustic surveillance, as such technology is not standard for this class of aircraft. Its flight computer simply maintained its course, locked onto its target coordinates, while Russian operators watched its progress like air traffic controllers guiding a plane to a landing. While the acoustic network could track the intruder, it lacked the ability to destroy it. That task fell to the kinetic defense systems. 5 minutes after the initial detection, the tracking data was relayed to a Tor M2 missile battery stationed 18 kilometers to the southeast. The Tor M2 is a formidable short-range defense system, boasting 8 ready-to-fire missiles and a radar capable of tracking dozens of targets at once. Theoretically, the Liuti should have been destroyed immediately. The battery commander received the coordinates and slewed his engagement radar toward the drone's predicted location, expecting to see a clear blip. Instead, his scope remained empty. The issue was purely geometric. The Tor's radar is designed to engage aircraft flying at higher altitudes. It requires the target to be at least a few degrees above the horizon to separate the signal from the ground clutter. Radar waves bouncing off the frozen earth create a chaotic background noise that masks low-flying objects. At a range of 18 kilometers, a drone flying at 30 meters altitude sits at an elevation angle that is barely a fraction of a degree above the horizon. To the radar, the drone was indistinguishable from the hills and trees behind it. The commander realized that for his system to acquire a lock, the target would need to come much closer, within barely a kilometer or two, to generate a sufficient angle. Moving at high speed, the Liuti would cross that narrow engagement window in less than half a minute. However, the drone was not flying directly toward the battery. It was cutting across the landscape on a tangential path. The acoustic track showed the target closing distance, but never entering the lethal envelope where the radar could see it. The drone passed well to the north, effectively slipping underneath the radar coverage through a combination of terrain masking and geometric limitations. The battery commander could only watch the digital track move away, his missiles useless against a target he could not see electronically. 47 kilometers remained to the target. The Liuti had defeated the acoustic network by using the terrain and the missile battery by exploiting physics. But another threat had been hunting it since launch. 40 kilometers to the west, an interceptor was already in the air. A modified Geran 2 drone had launched minutes after the initial alert, part of a standing patrol designed to counter Ukrainian launches. This was a Frankenstein weapon, a standard one-way attack drone that Russian engineers had jury-rigged into an air defense platform. Mounted atop its fuselage was a launcher tube containing a portable surface-to-air missile, held in place by custom brackets. It was a crude improvisation, effectively turning a slow, loitering munition into a hunter-killer. The added weight of the missile system drastically reduced the drone's flight time, leaving it with limited fuel to find a target hiding in a vast acoustic uncertainty zone. The interceptor drone utilized a thermal seeking system that relied entirely on contrast. To find a target, it needed to see a hot object against a cold background. Against a clear sky, the heat of a jet exhaust stands out starkly. However, looking down at the ground presents a much more difficult challenge. As the Liuti pulled up to clear a ridgeline, it exposed its hot exhaust against the sky for a few fleeting seconds. The interceptor's camera immediately picked up the bright thermal spike. The operator wasted no time, sending a sequence of commands through the relay network. Uncover the seeker, align the airframe, and fire. The missile roared off the rail, accelerating to supersonic speeds in an instant. It employed a guidance method known as proportional navigation, where the missile calculates the intercept point ahead of the target rather than simply chasing it from behind. This makes the projectile extremely hard to shake. However, the Liuti had unwittingly initiated a terrain masking maneuver programmed into its flight path. Just as the missile locked on, the drone dove over the ridge into a deep stream bed, breaking the line of sight and putting a wall of earth between itself and the threat. The missile, still tracking the last known trajectory, dove into the ground, its fuse triggering on a piece of scrap metal in the frozen earth rather than the drone. The explosion kicked up dirt and ice, but the Layuti flew on, unscathed. Having survived the interceptor by sheer luck and pre-programming, the drone entered the final phase of its mission. It now had to identify a specific aircraft on a crowded airfield. The challenge was distinguishing the valuable IL-38N from the standard, less critical variants parked nearby. From the air, the two aircraft looked nearly identical. Same four engines, same wing structure, same gray paint. The defining feature of the high-value target is a specialized electronic intelligence pod mounted on a strut above the cockpit, a boxy structure housing sensitive receivers. The drone's onboard AI had been trained on thousands of images to recognize this specific feature. It analyzed the video feed in real time. As the drone began its terminal dive, the AI locked onto the target aircraft with high confidence. The AI confirmed the target identity one last time as the range closed to 0. The radar altimeter measured the height above the aircraft's fuselage, preparing to trigger the warhead at the precise optimal distance. The warhead was a specialized airburst munition, designed not to blast a hole in the ground, but to spray a cone of destruction. Packed with thousands of steel cubes, the explosive charge was shaped to focus the blast energy downward. At a height of roughly 6 meters above the aircraft, the fuse triggered. The detonation unleashed a torrent of high-velocity shrapnel that shredded the aluminum skin of the aircraft like paper. The cloud of steel tore through the electronic intelligence pod, obliterating the sensitive antennas and processors inside. It continued downward, severing hydraulic lines and rupturing the fuel tanks in the wing root. The aircraft did not vanish in a fireball, but it was effectively neutralized. The complex, irreplaceable electronic brain that allowed it to hunt submarines was turned into scrap metal in the blink of an eye. The economic exchange was staggering. A drone costing roughly the price of a mid-range family car had just permanently disabled a surveillance aircraft worth millions, one that the Russian industrial base could no longer replace. The production lines for the IL-38 had shut down decades ago, and the proprietary electronics inside the pod were relics of a bygone era that could not simply be reordered. In a matter of seconds, an irreplaceable strategic capability had been erased from the board by a cheap, disposable machine. As the drone rolled into its terminal dive, the onboard optical correlator was running thousands of comparisons per second, matching the real-time video feed against the stored target library. The neural network had positively identified the silhouette of the IL-38N, locking onto the distinct geometry of the electronic warfare pod with high confidence. But reality rarely matches the simulation. The navigation sensors, scanning the approach vector via optical flow, detected a physical anomaly that the 18-hour-old satellite maps had missed. A diesel ground power unit with a heavy steel exhaust stack was positioned directly in the flight path, creating a collision risk that would trigger the warhead prematurely on the ground equipment rather than the aircraft. The flight computer's collision avoidance logic executed a reflex maneuver faster than any human pilot could process. It commanded a sharp deflection of the ailerons, banking the airframe to the right and steepening the angle of attack to shave meters off the altitude. This high-G correction meant the impact point would drift from the center of the fuselage to the wing root, a calculated compromise to ensure the drone cleared the obstacle. As the range collapsed to 0, the radar altimeter began pinging the aircraft's skin, measuring the final remaining meters to the ideal detonation height. The payload concealed within the composite nose cone was not merely a block of high explosives designed to create a generic shockwave. It was a masterpiece of lethal geometry engineered specifically for the destruction of soft, high-value targets. This was a specialized airburst munition developed to solve the complex engineering problem of neutralizing delicate electronics that are protected by a metal airframe without needing a direct physical impact. The warhead architecture featured a central high-explosive core encased in a fragmentation matrix containing thousands of preformed steel cubes, each one a kinetic penetrator waiting for release. Unlike a standard general-purpose bomb that wastes its energy expanding in a sphere, this device utilized a shaped charge design to focus the blast energy entirely downward. It created a dense, conical shotgun effect that directed nearly all of its lethal mass into a footprint the size of a tennis court, ensuring that nothing within the kill zone could escape the saturation. At a height of exactly 6 meters above the target's fuselage, The laser proximity fuse closed the firing circuit. The resulting detonation accelerated the steel cubes to hypersonic velocities in a fraction of a millisecond, transforming them into a focused cloud of metal that struck the aircraft's aluminum skin with the kinetic energy of a meteor shower. The shrapnel tore through the thin alloy sheeting of the fuselage as if it were wet cardboard, meeting almost no resistance before penetrating the critical internal volumes. Inside the electronic intelligence pod, the swarm of steel instantly shredded the delicate waveguides, multi-layer circuit boards, and liquid cooling systems that constituted the aircraft's sensory system. The kinetic wave continued downward through the airframe, severing high-pressure hydraulic lines and turning the fuel tanks located in the wing root into a colander. The aircraft did not vanish in a Hollywood-style fireball, but it was effectively euthanized on the tarmac. The complex, irreplaceable electronic brain that gave it the power to hunt submarines was reduced to a pile of useless silicon and copper in less time than it takes to blink. The financial and strategic calculus of this strike reveals the terrifying new math of modern asymmetric warfare. A drone that costs roughly the same amount as a mid-range family sedan had just permanently removed a strategic asset worth tens of millions of dollars from the Russian order of battle. However, the dollar figure is dangerously misleading because it implies that the aircraft can be replaced if the government simply spends enough money. It cannot. The production lines for the Ilyushin YL-38 airframe shut down before the Soviet Union collapsed, and the proprietary electronics inside the Novella pod are relics of a specialized industrial base that no longer exists in the Russian Federation. There is no factory to call for a replacement motherboard, and the engineers who designed these systems have long since retired or passed away. The supply chain is effectively dead. In a matter of seconds, an irreplaceable strategic capability, the ability to sanitize the Black Sea of NATO submarines, had been erased from the board by a cheap, disposable machine built from consumer-grade components. This is the new economy of attrition, where a garage-built robot can bankrupt a superpower's legacy fleet by destroying history that cannot be rebuilt. At just past 4 in the morning on a Tuesday in mid-June, 2 Ukrainian MiG-29 fighters are screaming through a limestone valley in the Sumy region, barely skimming the treetops. Their engines are guzzling fuel at an alarming rate, pushing the aging airframes close to the speed of sound, while a Russian Sukhoi Su-30 intercepts them from over a marathon's distance away. In roughly 15 minutes, these pilots will attempt to release 4 French-supplied AASM Hammer guided bombs on a Russian drone command post that has been terrorizing the local power grid for weeks. But first, they have to navigate what is essentially a suicide run through the densest air defense bubble on Earth. Standing between them and their payload is a layered network of S-400s, Tor-Ms, and Buk M3S, all talking to each other and waiting for a single slip-up. If the Ukrainians fail, the intelligence assessments are grim. The city behind them is going to be hammered by a mass drone wave before most people have even finished their morning coffee. The formation climbs slightly and banks northeast, using the rolling terrain to hide their electronic footprint. Every mile of this path has been mapped out to slip through the tiny cracks in Russian radar coverage, cracks identified through months of high-stakes electronic hide-and-seek. As they cross into the contested gray zone, both pilots know they are flying into a trap where the margin for error is effectively zero. The first sign that the element of surprise is gone comes from a Russian S-400 battalion stationed just over the border. They activate their long-range surveillance radar, a massive piece of engineering that can see birds from the next province over. This is not the spinning dish you see in old war movies. It is a phased array system that scans the entire sky electronically in a fraction of a second. Its invisible waves wash over the lead MiG at a range of over 100 kilometers. This distance, and with the fighter hugging the Earth, the radar can't get a lock solid enough to guide a missile. But physics is a snitch. It detects a faint anomaly against the background noise of the ground. The system's computer flags this ghost for a human operator, sending a data packet through the Russian digital network to a Su-30 fighter patrol cruising at high altitude to the west. The Russian pilot, likely bored on a routine dawn patrol, gets the vector. He doesn't need to see them with his eyes. He lets his massive nose-mounted radar scan the weeds, knowing that even a momentary pop-up will light up his scope like a neon sign in a dark alley. Meanwhile, a dozen miles ahead of the rushing jets, a Ukrainian Bayraktar TB2 drone is loitering in the thin air of the upper atmosphere. To a radar operator, it looks about the size of a large seagull. Its camera ball has been staring at the target area all night, documenting every cigarette break and truck movement with unblinking patience. The drone operator, sitting in a disguised van that looks like it belongs to a plumbing company, has counted over a dozen reconnaissance drones launching from a converted barn in the last hour. Each launch confirms the intel. This isn't a farm. It's a nerve center for the invasion. But the TB2 isn't just there to watch. Its secure link provides targeting data to the jets, sure, but its real job is to be the world's most expensive fishing lure. Russian air defense crews are obsessed with swatting these drones, often turning on their active radars to take the shot, which broadcasts their exact location to anyone listening. Today, a Pantsir missile system takes that bait. Its radar lights up to track the slow-moving drone, instantly screaming its position to every electronic warfare receiver in the county. The lead MiG pilot sees the threat warning on his dashboard, a simple system that blares an alarm when you're being painted by radar. He jinks the aircraft a few degrees east, putting a granite ridge between him and the missile site. It breaks the radar lock, but physics demands a toll. The maneuver burns precious jet fuel and costs them time, forcing him to push the throttles forward to stay on schedule. The roar of the engines rolls across the landscape, reaching a network of acoustic sensors miles away. These passive listening posts can't shoot you, but they can tell the command post that fast movers are inbound. The data hits the sector headquarters, and a colonel orders the entire air defense grid to wake up. Suddenly, every radar operator in the region stops drinking tea and starts scanning their screens with sweaty palms. The Su-30 pilot gets an updated vector, narrowing his search. He drops altitude and punches the afterburner, going supersonic. In a few minutes, he will be within range to fire his active radar missiles. The Ukrainian pilots are racing against a clock that is ticking faster than they realize. 10 miles from the first missile site, the lead Ukrainian pilot faces a math problem that could kill him. The mission requires them to release the bombs from high altitude to give them enough glide range to hit the target. But climbing up there means exposing themselves to every long-range radar in Russia. His warning gear is already chirping, letting him know search radars are sweeping him. Any second now, those chirps will turn into the solid tone of a weapons lock. Above them, the drone operator spots a Tor missile system powering up in a tree line. This mobile unit is the real killer. Unlike the big strategic systems, the Tor is designed to snap-shoot fast targets in seconds. The lead MiG brakes hard, pulling enough J force to make his vision blur. This defensive move plays right into the Russian hand. By forcing the jets to turn, the Tor operator has herded them straight toward a Buk missile battery waiting on their flank. It's a classic ambush. Use the short-range guy to flush the birds into the shotgun of the medium-range guy. The wingman spots the trap first. His systems light up as the Buk's radar switches from look to kill mode. This is a modern system capable of engaging targets from miles away. They are right in its throat, but these pilots have drilled for this. Instead of turning tail and running, which would make them a huge, easy target, they turn directly at the threat and floor it, dumping clouds of radar-reflective chaff. This aggressive move confuses the Russian computer, which expects targets to run away. The rapid closing speed messes up the firing solution, and by the time the operator adjusts, the MiGs have flashed past the minimum engagement range. They are safe for the moment, but the maneuvering has bled off critical speed and altitude, energy they needed to toss the bombs. The drone operator sees the problem and steps in. He commands the drone to blast out electronic noise, flooding the enemy's scopes with static. It's not military-grade jamming, but it creates enough confusion to buy the jets a few seconds of invisibility. Using the momentary confusion created by the electronic fog, the lead MiG-29 pilot pulls back hard on the center stick, initiating a zoom climb that trades his chaotic forward speed for perilous altitude. The fighter jet acts like a massive roller coaster car hitting the bottom of a loop, rocketing up from the safety of the weeds into the thin, freezing air of the upper atmosphere. The G-forces slam the pilot into his ejection seat, compressing his spine as the horizon tilts 90 degrees and disappears. At the apex of this ballistic arc, hanging in the sky just above stall speed where the controls feel mushy and unresponsive due to the lack of airflow over the wings, he releases 2 hammer bombs. The weapons drop heavily from the pylons, their rocket motors kicking in after a pre-programmed safety delay to avoid scorching the airframe's delicate skin. The pilot immediately bunts the nose forward, practically standing on the rudder pedals to pivot the jet back toward the mud, his radar warning receiver screaming about new threats that have just woken up. As the jets retreat, the bomb's guidance systems wake up to a nightmare scenario. The GPS environment is completely sterilized. Russian jamming transmitters are drowning out the faint satellite signals with a tsunami of electromagnetic white noise. But the engineers anticipated this. The bombs seamlessly switched to their internal inertial navigation systems. Inside each weapon, ring laser gyroscopes and sensitive accelerometers measure every twitch, turn, and change in velocity, calculating their position purely through the fundamental laws of motion without needing to talk to the outside world. As they glide silently toward the target, the infrared cameras in their noses open their shutters, hunting for the specific heat signatures of the command trucks against the cold ground. The second MiG reaches its release point just as a Russian missile battery achieves what pilots call a hard lock, a continuous chirping stream of radar energy that signifies imminent death. The pilot has the length of a deep breath before a missile is in the air. He ripples his bombs at the secondary target, the barracks, and immediately snaps the jet into a violent diving turn, pumping out flares and chaff cartridges to create a decoy cloud of burning magnesium and fiberglass. Two missiles erupt from the ground, riding pillars of fire and accelerating to hypersonic speeds in less than a heartbeat. These are modern, smart missiles. They don't need the ground radar to tell them where to go in the final seconds of the engagement. The pilot watches them on his threat display, a digital representation of his own mortality. He has less than half a minute to live. He throws the jet into a corkscrew dive, a punishing maneuver that forces the missiles to constantly change their intercept course, bleeding off their kinetic energy against the friction of the thick lower atmosphere. The first missile, unable to make the sharp geometric turn required to follow the spiral, flies past harmlessly, its seeker confused by the rapidly changing aspect of the target as the jet rolls around its own axis. The second missile is smarter, or perhaps just luckier. It anticipates the turn and cuts the corner, pulling lead like a skilled clay pigeon shooter to intercept the jet at its future position. With impact just a second away, the pilot yanks the stick back into his lap, straining the airframe to its absolute breaking point to reverse the turn direction. The missile tries to follow, but it cannot fight the dense air of the low altitude at that incredible speed. Physics dictates that the turning radius increases with speed. It explodes close enough to rattle the pilot's teeth, sending a spray of tungsten shrapnel into the tail section. But the Tumansky engines keep turning, drinking fuel and spitting fire. Both jets race for the border at treetop height, their bombs now gliding silently toward the target miles away. But the danger isn't over. The Russian Su-30 flanker has closed the distance and has a lock. The Ukrainian lead pilot checks his fuel state, barely enough to get home if he flies a straight, efficient line. But efficiency is out the window when a predator is on your tail. The Russian pilot fires, and the digital warble in the headset confirms the worst. The warning gear in the Ukrainian cockpit screams a new, urgent tone. Two active radar air-to-air missiles are inbound, powered by motors that push them to 4 times the speed of sound. These things have their own little radars in the nose. Once they get close, they are autonomous sharks that don't need instructions from the launch plane. The pilots have a grim choice: climb and fight, which exposes them to the surface-to-air missiles again, or stay low and pray the terrain masking works. They choose to stay low. The rising sun, now peeking over the horizon, offers a desperate lifeline. The lead pilot banks hard, placing the sun directly behind his aircraft relative to the incoming missile. The missile's seeker, designed to ignore the ground clutter, gets blinded by the massive infrared glare of the star. The pilot adds to the chaos by dumping flares, creating a blinding wall of fire that saturates the missile's sensors. The first missile gets confused, locks onto the sun's massive heat signature, and flies off into the upper atmosphere to chase a star it will never catch. The second missile ignores the decoys and tracks the distinct heat of the MiG's engines against the cool morning air. The wingman is in the crosshairs. Impact is seconds away. He pulls a desperate move, yanking the nose vertical and cutting the engines to idle. The jet acts like a massive air brake, effectively stalling in midair and losing almost all forward velocity, hanging like a falling leaf. The missile's radar relies on the Doppler effect, specifically the movement of the target, to track it. Suddenly, the target is hovering. The missile overshoots, unable to see the stationary jet against the rushing ground. As it passes, the pilot slams the throttles back to full military power and dives to regain energy before he crashes. The noise alerts the ground crews again. An S-400 commander, seeing he can't get a clean shot at the low-flying jets, orders a desperation move. He fires a salvo of massive missiles not to hit the jets directly, but to explode in their flight path. These giant telephone pole-sized missiles streak up and detonate in a pre-planned grid, filling the sky with a cloud of heavy tungsten cubes. It's a multi-million-dollar shotgun blast designed to create a no-fly zone of flying metal. The pilots have to thread the needle through this artificial storm, They drop so low they are kicking up spray from the farm ponds, flying under power lines. The wall of shrapnel rains down above them, shredding the trees. A piece of metal punches a clean hole in the lead jet's wing, severing a non-critical control cable, but miraculously, the fuel tanks hold. They punch through the wall of steel and race for home, leaving the chaos behind them. But back at the target, the clock strikes 0, and the silent killers arrive. The 4 hammer bombs enter their final dive, initiating a terminal sequence that is terrifyingly silent. At this stage, the rocket motors have long since burned out, leaving the weapons to glide on their pop-out wings like predatory birds. They are invisible to the noise-activated acoustic sensors that guard the perimeter because gravity has no engine note. Since the GPS environment is completely sterilized by the jamming, the bombs are flying on pure math, utilizing internal ring laser gyroscopes that measure the rotation of the Earth and the bomb's own velocity to calculate position. They have drifted less than the length of a family car over miles of unguided flight. As they pierce the cloud deck, the uncooled infrared cameras in their noses snap open, picking up the targets with crystal clarity and comparing what they see to a 3D wireframe model stored in their memory banks. But the guidance is just the delivery service. The fuses on these bombs are the real engineering marvels here. They are programmable smart fuses that utilize microaccelerometers to feel what they are hitting by measuring deceleration forces in real time. The armorer back at the base set them specifically for this raid, programming a different logic gate for each target. The first bomb hits the command post. The fuse feels the sharp spike of the concrete roof, waits a fraction of a second, feels the second spike of the floor, and then detects the sudden drop in resistance that indicates the empty space of the main control room. It detonates in the dead center, maximizing the overpressure to liquefy everything inside before the shockwave even hits the walls. The building implodes, dropping the heavy concrete roof onto the operators inside who never saw it coming. The second bomb hits the fuel truck. The fuse is set to hair trigger mode, exploding the moment its crush switch touches the thin metal tank. The resulting fireball is not just an explosion, it is a thermal event. It consumes the communication vans parked next to it, melting the delicate phased array antennas into puddles of unrecognizable alloy before they can even transmit a distress signal. The intense heat, exceeding 2,000 degrees, warps the chassis of the vehicles, fusing the rubber tires to the asphalt in a gruesome display of thermal physics. The third bomb hits the wooden safe house. The fuse feels the soft wood, realizes it hasn't hit anything hard enough to warrant a detonation, and waits. It punches through the floorboards like they are made of wet cardboard, and only triggers when it buries itself in the concrete foundation, blowing the structure off the map from the bottom up. The fourth bomb enters the repair warehouse and switches to proximity airburst mode, detonating exactly 3 meters above the floor. This creates a downward cone of destruction, turning the bomb's casing into a tornado of flying steel cubes that shreds the delicate electronics, optical sensors, and logic boards of the drones racked inside. The effect is instant and practically visible across the electromagnetic spectrum as a sudden deafening silence. High above the front lines, a dozen Russian Orlan-10 drones patrolling for Ukrainian artillery suddenly go stupid. Their control link is severed instantly. On the Russian operator screens, the video feeds turn to static simultaneously. Without instructions, the drones go into a default autopilot mode and start drifting back toward a base coordinates that are now nothing but a smoking crater. The pilots, safe in their own airspace, get the signal that the grid is down. The entire nerve center, the brains, the eyes, and the hands of the Russian drone war in this sector has been erased in less time than it takes to watch a short video on your phone. The enemy is blind, the artillery batteries are deaf, and the civilians in the city below will sleep through the night without air raid sirens for the first time in weeks. It was a gamble with millions of dollars of hardware and 2 irreplaceable lives, and the payout was absolute. At 0612 hours local time, the atmosphere inside the ready room at Belbek Air Base was defined by the lethargic rhythm of a routine morning shift, with pilots drinking lukewarm coffee and scanning flight logs, completely unaware that a dozen FP-2 drones were currently screaming over the Black Sea at 80 meters altitude, headed straight for their location. In less time than it takes to have a pizza delivered, a seemingly standard morning in Crimea would dissolve into one of the most embarrassing combat aviation losses of the entire war. The pilots were chatting with ground crews about maintenance schedules, while 40 kilometers to the west, 12 shaped charges were closing the distance at 95 kilometers per hour. This wasn't just an attack. It was a physics lesson delivered at terminal velocity. The base, bristling with the world's most expensive air defense systems, was about to learn that spending billions of dollars on radars doesn't matter if your software architecture contains a fatal logic error that classifies a lethal threat as a harmless migratory bird. The 12 drones flew in 3 loose formations of 4, spreading across 2 kilometers of open water to maximize their survival chances against random visual detection. At 80 meters altitude, they were flying aggressively below the radar horizon for most Russian search systems, effectively invisible until they hit the 30-kilometer mark where the curvature of the Earth could no longer hide them. The lead group crossed this invisible geometric line at 0613. Somewhere ahead on the Crimean coast, massive Russian radar antennas were already rotating, searching, and painting empty sky where the drones would appear in mere seconds. The operators in Ukraine, sitting in a bunker hundreds of kilometers away, couldn't actually see the target yet. Their video feeds wouldn't activate until the terminal approach phase to save bandwidth and maintain radio silence. For now, they just watched telemetry data. Altitude 80 meters, airspeed 95 kilometers per hour, heading 090. A stream of digital confidence flowing into a chaotic analog world. Then, the first radar found them. The Nebo SVU early warning radar sat on a strategic rise northwest of the main runway, its massive antenna rotating once every 6 seconds, like a persistent mechanical eye searching for intruders. Most modern radars struggle to see small plastic drones because their radar-absorbing coatings and composite airframes scatter the signal into background noise, effectively erasing the aircraft from the screen. But the Nebo SVU operated on VHF wavelengths, frequencies so long that they bounce off anything larger than a meter across due to the phenomenon of resonance. Stealth shaping means absolutely nothing when you are hit by a radio wave bigger than the aircraft itself. The FP2's 6-meter wingspan lit up on the operator's screen like a bonfire in a dark room. At 0614, the radar operator watched 12 distinct contacts materialize out of the electronic noise. Range 38 kilometers, bearing 315, closing fast. He immediately keyed the alert to the S-400 battery. The response from the S-400 battery came back in seconds. Negative. The system would not engage. The problem wasn't a lack of missiles or a lack of willingness. It was a hard-coded physics problem buried deep in the system's logic. The S-400's targeting software was designed in 2007 to filter out birds and weather clutter by automatically ignoring anything moving slower than 100 kilometers per hour. These drones were cruising at 95. On the S-400 screens, the contacts flickered like ghosts, appearing for one sweep and vanishing the next, never holding a solid track long enough for a firing solution. This was the result of a velocity filter, essentially a spam filter for radar. It works great until your most important message comes from a sender you didn't whitelist. The drones weren't spam. They were the main threat, and the world's most advanced air defense system was automatically deleting them from reality because they were flying 5 kilometers per hour too slow. The only system capable of engaging these slow-moving targets was the Pantsir S2, and it was currently sitting 3 kilometers away, covering the fuel depot on the other side of the base. At maximum road speed across the tarmac, it would take 4 minutes to reach the radar site. The drones would arrive in 6. It was going to be tight, but doable. The driver slammed the vehicle into gear and roared onto the access road, only to hit something that isn't in any military manual. A fuel truck parked in the middle of the road with its driver asleep. The Pantsir driver hit the horn. Nothing. He got on the radio, screaming for the vehicle to move. Still nothing. The fuel truck driver's radio was likely turned off or drowned out by his own snoring. 30 seconds burned. 45. The Pantsir had to brutally lurch around the truck, bouncing through a muddy drainage ditch, its 30-ton suspension groaning under the stress. A whole minute was lost to simple human incompetence. While the Russians played traffic jam, the FP2s crossed the coastline at 0617. Russian GPS jammers were now screaming, saturating the electromagnetic spectrum with enough noise to scramble a cruise missile's navigation. But the drones weren't relying on satellites. Each unit carried a navigation computer running 3 systems simultaneously: GPS when available, an inertial unit tracking acceleration, and a downward-facing camera comparing the ground below against stored satellite imagery. This is called terrain matching. The drone's camera takes a snapshot of the ground, breaks it into a grid of light and dark pixels, and compares it to a map stored on its hard drive. If the drone has drifted 50 meters east, the computer sees the mismatch and corrects the flight path 10 times per second. The Russians could jam every frequency from here to Moscow, and it wouldn't matter. You simply cannot jam a camera looking at the ground unless you physically cover the entire country in a tarp. At 0619, the lead drone pulled up to 400 meters for its terminal dive. The NABO radar painted it instantly, tracking the dive angle and calculating the impact point with mathematical perfection. It could see the threat, but seeing isn't stopping. The radar could do absolutely nothing to prevent what happened next. The shaped charge warhead introduced itself to the antenna array 7 seconds later. $35 million of VHF radar technology was instantly scattered across the hillside in a shower of burning composite and steel. The system designed to detect stealth fighters at 100 kilometers had been destroyed by a plastic drone it saw coming for 6 full minutes. The second NABO radar, sitting 800 meters east, suffered an identical fate 90 seconds later. Belbek Air Base had just gone blind. No early warning, no long-range detection. The door was now wide open. But the S-400 still had its fire control radar, the 92N6. This was the critical component that actually guided missiles to their targets. Without the NABO radars to warn it, the 92N6 was now scanning frantically, looking for threats it should have known about minutes ago. Someone in command had decided this radar was too valuable to lose, so they had built a metal cage around it. The only problem was that this protection was better suited for keeping chickens in than keeping missiles out. 3 FP-2s were approaching from the northeast, their terminal cameras locked onto the glowing heat signature of the radar's electronics. The lead drone began its dive at 0622, coming down at a 47-degree angle, well outside the geometry of the cage. The steel bars that would have stopped a horizontal attack did nothing against a weapon falling from the sky. The warhead punched through the top of the radar vehicle, and secondary explosions rippled through the compartment as the electronics cooked off. By the time the Panzer air defense system finally screeched to a halt at the burning radar site, the crew had less than 2 minutes to prevent total catastrophe. Skipping the standard stabilization protocols, they forced the search radar to spin up immediately, desperate to find the remaining threats in the darkness. The operator's screen lit up instantly with 3 hostile contacts approaching from just over 4 kilometers away, flying low and descending fast. On paper, this should have been an easy win for the Russian crew. Their vehicle was armed with a full magazine of interceptor missiles, each capable of accelerating to hypersonic speeds in the blink of an eye and pulling maneuvers that would tear a standard aircraft apart. Tracking radar was sensitive enough to lock onto a target the size of a grapefruit at 10 kilometers, so hitting 3 slow-moving drones flying in a straight line should have been like a grandmaster playing chess against a pigeon. But the Ukrainian operators had anticipated this exact mismatch and prepared a geometric trap. As the Panzer launched its first interceptor, 2 of the incoming drones suddenly crossed flight paths. To the radar, which sees the world in reflections rather than images, the 2 distinct signatures merged into a single, confused blob of energy. The missile's guidance computer, forced to choose between splitting targets, essentially guessed wrong. It chased a phantom echo while the real threat continued its dive uninterrupted. The second drone was intercepted successfully, disintegrating into a cloud of shrapnel about 2 kilometers out, but the third unit was now inside the critical minimum engagement zone. Every guided missile needs a certain amount of distance to arm its warhead and stabilize its flight path. Fire too close, and the weapon is just a harmless metal tube. The Panzer's interceptors required just over a kilometer of flight time to become lethal, but the final drone was already inside that boundary. The operator desperately switched to the twin 30mm cannons, weapons designed to unleash a wall of lead at 5,000 rounds per minute. However, physics once again refused to cooperate. The drone was diving at a steep angle of more than 50 degrees, while the cannons could only elevate to 45. Tracers arced harmlessly into the empty night sky, failing to intercept the threat. A split second later, the shaped charge slammed into the vehicle's engine block. Belbek had just lost its last line of defense. The early warning eyes were gone, the fire control brain was fried, and the point defense shotgun was burning. Yet 4 drones were still airborne, banking hard toward the parked aircraft. Sitting on the flight apron in the middle of this chaos was a MiG-31 interceptor, a massive aircraft worth tens of millions of dollars. In a display of decision-making that borders on negligence, the ground crew had chosen this specific moment, while explosions were literally rocking the base less than a kilometer away, to perform maintenance. The aircraft sat fully exposed with its canopies raised, effectively inviting the enemy inside. The drone approached from just under 400 meters, its camera clearly picking out the twin-tail silhouette and the dark rectangles of the open cockpit. The operator didn't hesitate, lining up the crosshairs where the wing root met the fuselage. When the warhead detonated, it demonstrated the terrifying efficiency of the Monroe effect. The explosive collapsed a copper liner into a focused jet of superplastic metal, moving at speeds that make bullets look stationary. This jet punched effortlessly through the titanium skin and ruptured the fuel cells before detonating the heavy air-to-air missiles waiting in the weapons bay. The resulting secondary blast scattered the heavy interceptor across the tarmac like a discarded toy, turning a strategic asset into a smoldering pile of scrap metal. While the MiG was burning, a panic-induced command came down from the regiment's headquarters. Scramble the fighters. Two Su-27 flankers began rolling out of their hardened shelters, their pilots hoping to get airborne and hunt down the attackers. But launching a fourth-generation fighter jet isn't like starting a getaway car. It is a complex, time-consuming ritual that cannot be rushed without risking the aircraft. The massive turbofan engines require nearly 2 minutes just to spool up from a cold start to idle thrust. If you rush the fuel injection, you risk a compressor stall that can destroy the engine before you even release the brakes. Furthermore, the navigation computers need time to align their inertial platforms, sensing the rotation of the Earth to determine which way is up. Skip this, and you are flying blind. The pilots were trying to compress a 5-minute startup sequence into 3, frantically flipping switches, while the remaining drones circled overhead like vultures waiting for a meal. The maintenance crews were still pulling wheel chocks and checking control surfaces when the drones entered their terminal dives. The pilots, strapped into their cockpits, were completely unaware that they were sitting in stationary targets while their navigation gyros slowly spun up. The first drone struck the lead flanker at the wing root, detonating the fuel stored there and igniting the air-to-air missiles hanging on the pylons. The explosion was absolute, instantly transforming the sleek fighter into a fireball that illuminated the entire flight line. 2 seconds later, the second drone slammed into the trailing aircraft, punching through the canopy and detonating inside the avionics bay. It didn't explode as violently as the first. Instead, it simply burned, with fire spreading rapidly through the fuselage as hydraulic lines ruptured. In less than 5 seconds, 2 of Russia's premier air superiority fighters, with a combined value approaching $70 million, were written off. The final drone, having no aircraft left to target, adjusted its course and slammed into the control tower, shredding the communications array and ensuring that even if an aircraft survived, it wouldn't be talking to anyone. The return on investment for Ukraine was astronomical, trading cheap plastic drones for a substantial portion of an air regiment. The strategic hangover from this morning raid will linger far beyond the smoke clearing from the runway, because replacing a Nebo SVU radar isn't like buying a new toaster at the local appliance store. These systems rely on hand-built artisanal electronics that require specific high-frequency semiconductors, components that Russia can no longer easily import due to strangled supply chains. Before the war, the lead time for a sophisticated VHF-active electronically scanned array was roughly 18 months. Now, with sanctions biting down on every microchip shipment, that timeline has likely stretched to 3 years or more. This creates a terrifying reality for Russian commanders. For the next 1,000 days, the northwestern approach to Crimea effectively has a blind spot the size of Switzerland. To compensate, the surviving S-400 batteries must keep their high-power engagement radars active 24/7, which is essentially a death sentence for the hardware. Fire control radars are like top-fuel drag racing engines. They are engineered for short, intense bursts of extreme power, not for running marathons. Forcing a 92N6 radar to transmit continuously will burn out its traveling wave tubes and liquid cooling pumps in a matter of weeks, inevitably turning the pride of Russia's air defense network into expensive static displays through sheer mechanical exhaustion. However, the most terrifying lesson for military planners analyzing this footage isn't just about gaps in radar coverage. It is about the absolute obsolescence of electronic warfare as a primary shield. For decades, Russian military doctrine rested on the arrogant assumption that they could simply blast enough noise into the radio spectrum to confuse any incoming smart weapon, effectively blinding it before impact. That assumption just evaporated in a cloud of burning aviation fuel. The FP2's integration of optical terrain matching and terminal image recognition demonstrates that the electromagnetic spectrum is no longer the undisputed king of guidance. When a munition navigates by cross-referencing real-time camera feeds with satellite maps, traditional jamming is rendered functionally useless because the kill chain doesn't rely on external signals. You can spoof a GPS satellite, but you cannot jam the visible light spectrum without blinding your own pilots. Unless the Russians can figure out a way to physically cloak an entire airfield, or fundamentally alter the topography of the Crimean Peninsula every 12 hours to confuse the image classifiers, they are defenseless. They are facing a tactical environment where their $20 million electronic warfare complexes are about as useful as a paper umbrella in a hurricane against a $2,000 camera with a cheap processor attached to it. By forcing the Russians to commute to the war, Ukraine effectively reduces the sortie rate of the Black Sea Fleet by 40% without shooting down a single additional plane. It is a soft kill achieved through pure geography and fear. Finally, the economics of this engagement are enough to make a Kremlin accountant weep. The total cost of the Ukrainian strike package, 12 FP-2 drones, launch catapults, and support equipment, comes in at roughly $300,000, which is about the price of a single luxury car in Moscow. In exchange, they deleted 2 early warning radars, a fire control system, a Panzer missile truck, a MiG-31 interceptor, and 2 Su-27 flankers. The conservative replacement cost for that hardware exceeds $150 million. That is a return on investment of roughly 50,000% delivered in under 10 minutes. In the brutal mathematics of attrition warfare, this isn't just a victory. It is a liquidation sale where Ukraine bought the operational capability of an entire air regiment for pennies on the dollar. At exactly 0545 on May 26, 2025, a Ukrainian Air Force pilot strapped himself into the cramped cockpit of a Mikoyan MiG-29 fighter that had absolutely no business carrying the weapons bolted to its underwing pylons. Within minutes, this 40-year-old Soviet-designed air superiority fighter would attempt a mission profile its original designers in Moscow never imagined in their worst nightmares, delivering French precision-guided munitions against Russia's most feared internal security agency, using American GPS satellites and a Ukrainian software solution held together by zip ties and a prayer. As the pilot ran through his pre-flight checklist, the weight of history pressed down on the airframe just as heavily as the 2,000 kilograms of fuel in the internal tanks. No one had dared to strike a Federal Security Service facility directly in this war. The intelligence services were supposed to be untouchable, protected by layers of electronic warfare, kinetic air defenses, and the implicit geopolitical understanding that some targets were simply off-limits to avoid total escalation. But today, those rules were about to be rewritten by a pilot who knew that in exactly 90 seconds after takeoff, he would be the loneliest man in the Eastern Hemisphere. The mission profile was bordering on suicidal, even by the elevated risk standards of the Ukrainian Air Force. He would have to fly at treetop height to avoid the dense radar coverage along the border, then suddenly climb to 5,000 meters for the weapon release, a maneuver known as tossing that would light him up on every Russian search radar from here to Voronezh. He would have a window of maybe 20 seconds to release the bombs and dive back into the radar shadow before the S-400 batteries in Belgorod could process a firing solution. At 0558, the pilot advanced the throttles to military power, feeling the twin Klymov RD-33 turbofans roar to life behind it. These engines, capable of generating 18,300 pounds of thrust with afterburners, were thirsty beasts that converted jet fuel into noise and velocity with terrifying efficiency. The MiG-29 lurched forward, its oleo struts compressing as it accelerated toward the runway with its impossible payload. In the growing dawn light, this Frankenstein of a fighter lifted off, carrying French aerospace engineering, American situational awareness, and Ukrainian determination toward a date with Vladimir Putin's feared security service. As the landing gear retracted with a heavy hydraulic thud, the pilot checked his primary navigation display, which in this specific jet was not a standard Soviet gauge, but a commercial tablet mounted directly over the analog dials. This wasn't just a backup, it was the brain of the entire operation. The FSB would soon learn what 3 years of desperate innovation could accomplish when engineers stop asking for permission and start welding things together. At 0615, the MiG-29 screamed across the Ukrainian countryside at just 50 meters of altitude, so low that his jet wash was physically bending wheat fields and scattering birds in terrified clouds. The terrain following flight was physically exhausting, requiring constant stick and rudder inputs to avoid high-voltage power lines, cellular towers, and the occasional farmhouse chimney. But it was the only way to stay invisible to the Russian radars that infested the border region like fleas. The margins he was flying in were incredibly slim, defined by the ruthless geometry of radar horizons. The S-400 systems protecting Belgorod could technically track and engage targets at 400 kilometers, but only if they had a line of sight. The pilot knew that the Earth's curvature was his only friend today. At 50 meters of altitude, the radar horizon for a ground-based system was only about 25 kilometers away. As long as he stayed low, stayed fast at 900 kilometers per hour, and didn't make any mistakes, he would remain a ghost in the machine, a piece of ground clutter that filters would ignore. But in exactly 3 minutes, he would have to abandon that invisibility and climb right into the heart of their kill zone with technology that was less than ideal for a high-threat environment. The target coordinates glowing on his commercially bought tablet marked the Federal Security Service headquarters in Golovchino, Belgorod Oblast, just 5 kilometers from the Ukrainian border. This wasn't some random military depot or ammunition dump that could be replaced in a week. This was the successor to the KGB, the organization that had orchestrated countless operations against Ukraine for a decade. The 2 AASM hammer bombs hanging from his wings represented everything wrong and right about this hybrid warfare. These French-made modular air-to-ground weapons were never designed to talk to Soviet avionics. The MiG-29's 1980s-era computer systems couldn't even comprehend the existence of the Global Positioning System, let alone process dynamic targeting data from satellites that weren't launched until years after the jet was built. Ukrainian engineers had solved this impossible problem with typical battlefield creativity that would give a Lockheed Martin engineer a heart attack. Custom pylons had been fabricated in Kyiv workshops with GPS antennas jury-rigged to the forward mounting points, bypassing the jet's internal wiring entirely. Power cables snaked through maintenance access panels never meant to be opened in flight, feeding sensitive French electronics with rough Soviet electricity. The AASM hammer itself was a masterpiece of French engineering, a kit that transformed dumb iron bombs into precision munitions with a terrifying degree of accuracy. Each unit, which costs roughly $160,000, more than most people's homes, featured inertial navigation backed up by GPS guidance that could put a 250-kilogram warhead through a specific ventilation shaft from 70 kilometers away. The range extension kit contained a solid rocket motor that would activate immediately after release, pushing the bomb to near supersonic speeds. But all that sophisticated technology meant absolutely nothing if the Soviet jet couldn't tell the French bomb where to go. That is where the tablet came in, running custom software that translated modern targeting data into a language the bombs could understand via a Bluetooth connection to the pylon. It was the digital equivalent of duct tape, and it was about to be tested against the most sensitive target Ukraine had ever struck. At 0622, the pilot hit the initial point and yanked back on the stick, initiating the climb. The MiG-29 responded instantly, its nose pitching up to 45 degrees as the G-forces crushed the pilot into his ejection seat. The altimeter spun wildly, 1,000 meters, 2,000, 3,000. His radar warning receiver, a piece of hardware that detects incoming radar energy, exploded into audible chaos as every air defense system in Western Russia suddenly saw a distinct fighter-sized target climbing rapidly into their engagement envelope. Cockpit filled with the electronic screams of the Sirena 3 warning system as search radars locked on. The S-400 battery southeast of Belgorod was painting him with its 92N6 gravestone radar, measuring his speed, altitude, and heading with lethal precision. In seconds, the fire control system would have a solution and authorize a launch. But the pilot had one advantage that no algorithm could account for: surprise. The Russians had less than 45 seconds from detection to engagement, and their procedures were built around conventional attack profiles where jets stayed high or stayed low, not this hybrid maneuver. They would never expect Ukraine to do something so brazenly risky, which is exactly why the mission planners believed it might work. At 5,000 meters, the pilot hit the release point. The tablet showed optimal launch parameters as his thumb found the weapon release button on the stick. 2 distinct thuds shook the airframe as the AASM hammers fell away from the pylons. Immediately, he rolled the aircraft inverted and pulled hard, executing a modified Immelmann turn that would have impressed the maneuver's World War I inventor. The MiG-29 curved through the thin air, trading altitude for airspeed, as the pilot dove desperately back toward the safety of the low-altitude radar shadow. Behind him, the 2 bombs were well on their way to the target, their rocket motors igniting with a bright flash that accelerated them along a ballistic arc toward Golovchino. GPS receivers locked onto multiple satellite signals, while inertial navigation systems measured every tiny deviation in flight path. The bombs were now flying themselves, making hundreds of micro-corrections per second to ensure they hit their pre-programmed coordinates. The toss bombing maneuver he just performed was a relic from the Cold War, originally developed when nuclear-armed fighter bombers needed to deliver gravity bombs without flying directly over their targets to avoid the blast. The physics were simple enough for a first-year engineering student. Climb at a steep angle, release the bombs in an upward trajectory to impart kinetic energy, then get out of the area while momentum carried the weapons to their target. Simple in theory, but insane in practice against modern integrated air defense networks. Well, maybe not entirely insane. The Russian response was swift, but ultimately futile due to the geometry of the engagement. Two 48N6 interceptor missiles roared off their launch rails, racing to intercept the fleeing MiG-29. But the jet was already back at treetop height, jinking hard left and right as the pilot raced back to base. The interceptors, designed to knock out high-flying bombers or cruise missiles, couldn't maintain a lock on a target hugging the Earth and hiding in ground clutter. They sailed harmlessly overhead, their proximity fuses finding nothing but empty sky. In less than 2 minutes, the bombs would impact. The FSB officers in Golovchino had absolutely no idea that justice was flying through the morning sky toward them. Guided by satellites they couldn't see and technology they couldn't stop, the pilot checked his fuel state and exhaled. His part of the mission complete. Now it was up to the math. The two AASM Hammer bombs now plummeting through the stratosphere represented 3 decades of precision weapon evolution compressed into a 250-kilogram package. As they reached the apex of their ballistic trajectory at 8,000 meters above sea level, their onboard computers were performing flight path calculations that would have required a room full of mathematicians just 50 years ago. Each bomb was essentially 3 distinct weapon systems integrated into one lethal chassis. First, the nose section contained the guidance package, a hardened marriage of military-grade global positioning system receivers and ring laser gyroscopes that could navigate with centimeter precision even if every satellite in the sky suddenly disappeared. The French engineers at Safran had learned from American experiences in Iraq and Afghanistan that GPS jamming was the first move in any modern peer-to-peer conflict. So, they had built the AASM to be effectively unjammable. The inertial navigation system could fly the bomb to within 10 meters of its target, using only the memory of its initial position and the fundamental laws of motion. But it was the middle section that made the AASM truly terrifying to Russian air defense operators. Unlike the American JDAM, which simply guided a gravity bomb to its target like a glorified glider, the French had added a solid rocket motor that turned the weapon into a hybrid missile. This wasn't just falling with style. This was powered flight that extended the standoff range to 70 kilometers and gave the bomb the kinetic energy needed to penetrate hardened targets. The rocket motor burned for just 15 seconds, but that was enough to push the bomb to Mach 0.8, fast enough to complicate any last-second interception attempts by point defense systems. The tail section contained the control surfaces that would guide the bomb through its terminal dive. Combined with the guidance system, they could fly complex trajectories, even circling back to hit targets from unexpected angles to bypass shielding. Today, however, the flight plan was brutally simple. They would drive the bombs almost straight down through the Federal Security Service building's roof at an angle of 85 degrees. At 0627, the first bomb's radar proximity fuse detected the roof rushing up at 250 meters per second. The fuse performed one final calculation, determining the exact moment to initiate the detonation sequence to maximize lethality. It had to account for the bomb's terminal velocity, the angle of impact, and the pre-programmed millisecond delay to ensure the warhead exploded at the optimal point inside the building structure. The second bomb followed exactly 0.3 seconds behind, aimed at a structural stress point 20 meters away to ensure maximum catastrophic failure. 2 precision weapons guided by satellites 20,000 kilometers above were about to deliver a very personal message to Vladimir Putin's old stomping grounds, and the recipients had less than 10 seconds to realize their mistake. At 0621, Senior Lieutenant Smirnov was halfway through his morning tea inside the command vehicle when the S-400 early warning radar he commanded detected something unusual. 2 fast-moving contacts had appeared on his scope, climbing rapidly from a low altitude approximately 40 kilometers southwest of his position. The combat management computer classified them as fighter aircraft, likely Ukrainian MiG-29s based on their radar cross-section and climb rate. Smirnov had exactly 45 seconds to prevent a catastrophe, and the clock was already ticking against him. The S-400 Triumph system he commanded was, on paper, the most sophisticated air defense system in the world, capable of tracking stealth aircraft and ballistic missiles. Each battery consisted of multiple elements working in deadly electronic harmony. The 92N6 Gravestone radar could track 300 targets simultaneously at ranges exceeding 600 kilometers. The 48N6 missiles could reach out 400 kilometers and engage targets from ground level to 30,000 meters straight up. The system could even intercept hypersonic threats, making it the undisputed crown jewel of Russian air defense and a major export product. But the S-400 needed around 10 seconds from detection to engagement when dealing with low-altitude pop-up targets that appeared suddenly over the radar horizon. First, the search radar had to detect and classify the threat amidst the background noise of birds and weather. Then, the fire control radar needed to lock on and develop a firing solution that guaranteed a kill. The missile itself required 3 seconds from the launch command to leaving the rail and igniting its main motor. Then, there was the flight time to the target. Against high-altitude bombers or cruise missiles with predictable flight paths, this timeline worked perfectly. Against a fighter executing a toss bombing maneuver that lasted less than 20 seconds, it was catastrophically slow. The Russian interceptor missiles passed within 200 meters of the bombs, close enough to trigger proximity fuses under normal circumstances against a large aircraft. But the bomb's terminal velocity and steep dive angle put them outside the lethal fragmentation zone. The 48N6 warheads detonated harmlessly, their pre-fragmented tungsten cubes spreading through empty air as the French bombs continued their dive toward Golovchino unharmed. At 0627, the first AASM hammer punched through the reinforced concrete roof of the FSB headquarters in Golovchino. The shaped charge detonated on impact, creating a hypervelocity jet of molten copper that carved through steel roof beams and concrete floors as if they were room temperature butter. The bomb's fuse, programmed for a 0.025-second delay, counted down with electronic precision as the warhead plunged through the building's upper structure. At the moment of detonation, its 87 kilograms of high explosive converted from solid to gas in microseconds. The blast wave expanded at 8,000 meters per second, creating overpressures exceeding 200 pounds per square inch, enough to liquidate anyone inside instantly. The building's interior walls, designed to protect state secrets rather than withstand military ordnance, provided absolutely no resistance to the expanding gas bubble. The explosion inside the enclosed structure created a phenomenon called reflected overpressure. Blast wave bounced off surviving walls and floors, doubling and tripling its destructive power as the waves intersected and amplified each other. Windows didn't just break, they exploded outward in a shower of glass shards that would later be found embedded in buildings 300 meters away. Office furniture became lethal projectiles. Filing cabinets full of classified documents turned into metal confetti. The second bomb arrived 0.3 seconds later, striking 20 meters from the first impact. By now, the building's structural integrity was already fatally compromised. Load-bearing walls were gone, and support columns were shattered by the first blast. The second explosion found a structure already on the verge of collapse and delivered the final blow. The blast propagated through the weakened framework like a destructive tsunami, causing what civil engineers refer to as progressive collapse. Floor by floor, the FSB headquarters began to eat itself. At 0347 hours on June 22, 2025, a Russian locomotive engineer checking his schedule had no idea that Ukrainian eyes had been watching his fuel train for the past 73 minutes from a concealed position in the tree line. In exactly 94 seconds, 840 tons of diesel fuel would become Ukraine's newest fireworks display, courtesy of $8,000 worth of modified hobby drones that were currently closing the distance at 160 kilometers per hour. The engineer was focused on maintaining the speed limit for this sector of the track, completely unaware that his cargo had been marked for destruction by a team that specializes in turning logistics nightmares into reality. The train was moving through what was supposed to be a secure rear area, far from the front lines where artillery usually falls. But the definition of a safe zone had changed dramatically in the last hour, without anyone in the locomotive cab receiving the memo. As the heavy steel wheels ground against the rails in the darkness, the countdown to a catastrophic failure of structural integrity had already begun, and there was absolutely nothing the crew could do to stop the physics equation that was about to be solved at their expense. 35 kilometers away, Ukrainian operators from the elite Kabul 9 special unit monitor thermal feeds through encrypted Starlink connections that are bouncing signals off satellites in low Earth orbit. Their modified DJI Mavic reconnaissance drones are painting the target with surgical precision, utilizing sensors that turn the night into a clear picture of impending doom. The thermal signature on the screens does not lie because that locomotive's diesel engine glows white hot at 47 degrees Celsius against the cool morning landscape. while the 12 fuel cars show subtle temperature variations that scream premium target to anyone working with brain cells. This is not some spur-of-the-moment operation that was decided on a whim. Ukrainian Defense Intelligence has been tracking this specific train for 96 hours, using a network of partisan spotters equipped with encrypted smartphones who have been risking their lives to send text messages that coordinate with strike teams. They identified its departure schedule from the Rostov-on fuel depot, its typical speed through this specific sector, and most importantly, the 20-minute window when it would be furthest from Russian air defense coverage, creating a perfect kill box that the Russians had inadvertently driven right into. The math is brutal for Moscow when you sit down and calculate the logistics of modern armored warfare. Each fuel car carries 70 tons of diesel, which is enough to keep a Russian tank battalion operational for 3 full days of high-intensity combat maneuvering. 12 cars times 70 tons equals 840 tons of fuel, which represents roughly 10 days of operations for 3 entire armored battalions that are currently waiting for this delivery. Those 10 days can make all the difference between the Russians breaking through a defensive line or simply sitting around like very expensive lawn ornaments waiting to be targeted by artillery. The strategic value of this single train exceeds the cost of the missiles used to protect it, yet it is being hunted by devices that cost less than a used sedan. The operators in the bunker know that stopping this train does not just destroy fuel, it freezes the tactical options of an entire brigade situated 50 kilometers to the south, proving that logistics is still the grim reaper of military ambition. And here is what makes this strike package even more terrifying for the air defense crews tasked with stopping it. Those are not your standard DJI drones anymore that you can buy at an electronics store. Ukrainian engineers have retrofitted them with experimental firmware, extending digital zoom to 56 times magnification and flight endurance to 45 minutes, allowing them to loiter and stalk their prey. More importantly, they have integrated custom radio frequency hardware with frequency hopping spread spectrum technology that changes frequencies 1,500 times per second across multiple bands. It is like playing electronic whack-a-mole, except the mole cannot be caught because it moves faster than the hammer can swing. And unlike that carnival game, these moles fight back with lethal intent. Each Ukrainian-built FPV quadcopter carries a modified PG-7V L-shaped charge warhead, weighing 2.6 kilograms. That is an 85-millimeter diameter, copper-lined cone that focuses explosive energy into a jet traveling at 35,000 feet per second, which is fast enough to turn 15 millimeters of Russian steel into confetti before the crew even hears the explosion. The warhead was originally designed to penetrate 500 millimeters of rolled homogeneous armor, so using it against a thin-walled fuel car is like using a sledgehammer to crack an egg. The train continues rolling through occupied territory at exactly 45 kilometers per hour, completely unaware that in 47 more seconds, this routine supply run will demonstrate why occupying Ukraine was the worst investment decision since someone bought blockbuster stock in the early 2000s. The train crew believes they are protected by the darkness and the distance from the front, but they fail to realize that the rules of engagement have shifted to favor the small and the agile. The kinetic energy stored in that shaped charge is sitting dormant, waiting for a simple electrical impulse to release a focused stream of superheated metal that will ignore the structural integrity of the tank car, as if it were made of paper. It is a mismatch of engineering where a cheap, smart weapon is about to dismantle a multi-million-dollar logistics asset. At 0348 hours, as the first strike drone enters its terminal approach, something changes the electronic landscape entirely. A Russian Lear. 3 electronic warfare systems suddenly surges to life, its operators finally spotting the electromagnetic signatures they have been trained to hunt for months. The truck-mounted system begins broadcasting jamming signals across a 30-kilometer radius, pumping out enough radio frequency energy to disrupt every civilian cell phone from here to the next village. The Lear 3 is not subtle about its approach to electronic dominance. First comes broadband jamming, which consists of high-power noise transmitted across multiple frequency ranges simultaneously, designed to overwhelm any receiver within its engagement envelope. When that proves ineffective against Ukrainian frequency-hopping technology, the operators switch to spot jamming, focusing intense interference on the specific 2.4 GHz and 5.8 GHz bands that commercial drone systems typically use. It is like your wife first blasting the vacuum cleaner to drown out your music, And when that does not work, she tries to unpair your Bluetooth speaker so you cannot hear a thing. But Ukrainian operators had anticipated this exact scenario and prepared a technological countermove that renders the jamming irrelevant. Their system employs advanced frequency hopping spread spectrum technology that laughs at Russian jamming attempts by dancing around the interference. The drones change frequencies 1,500 times per second across 4 separate bands simultaneously, making it nearly impossible for the Lear 3 to lock onto and disrupt the signal before it has already moved to a new channel. The Russian operators intensify their electronic assault, moving beyond simple GPS jamming to GPS spoofing, sending false satellite signals designed to trick the Ukrainian drones into believing they are somewhere over the Pacific Ocean. It is a sophisticated attack that would ground most commercial systems instantly. But these are not standard commercial drones. Inside each Ukrainian attack drone are precision solid-state gyros that detect the discrepancy between GPS data and actual movement patterns. The inertial measurement units do not need satellites to know where they are. They track every change in velocity and direction using the fundamental laws of physics. You can spoof GPS signals all you want, but you cannot lie to Newton's laws of motion. As the lead attack drone approaches its target, it unspools what looks like a fishing line from a canister mounted on its rear. Except this line carries light instead of a lure. The fiber optic cable you see here maintains a perfect digital connection to operators 35 kilometers away, physically tethering the drone to its pilot. Now, the readers understand why Ukrainian operators chose this over radio control for the final run. You can jam airwaves with enough power, but you cannot jam glass. Fiber core measures just 9 microns, which is thinner than a human hair, while maintaining 1.5 gigabit data transmission rates. That is enough bandwidth for uncompressed 1080p video while simultaneously carrying control signals, telemetry data, and GPS corrections without a millisecond of latency. More importantly, it creates zero electromagnetic signature for Russian sensors to detect. The drone appears autonomous on their screens, a robot acting on pre-programmed instructions rather than receiving real-time human guidance, effectively becoming a ghost in the machine. But physics does not give free lunches, and this solution comes with its own set of engineering challenges. Fiber optic cable adds weight and bulk, requiring larger drone frames and more powerful motors to compensate for the drag of the spool. The hard connection between pilot and drone also leaves a physical trail after every flight, a reflective strand that becomes visible as it accumulates on the ground or in trees. Ukrainian operators know they will need to relocate immediately after this mission because that line points directly back to their hiding spot. But that is a small price to pay for guaranteed connectivity in a heavy jamming environment. At 0348, despite maximum power jamming across every frequency band the Lear 3 can generate, the Ukrainian attack drones maintain perfect control. The Russian operators watch their expensive equipment accomplish exactly nothing while the drones approach their fuel train at 160 kilometers per hour. The electronic chess match is over. Physics just checkmated a $5 million electronic warfare system with what amounts to a very long extension cord. At 0349, the first Ukrainian attack drone impacts fuel car number 4 with surgical precision. The 2.6 kilogram PG-7V L-shaped charge does not just explode. It acts as a directed energy weapon. It vaporizes a precisely engineered hole through 15 millimeters of steel at 2,800 degrees Celsius, instantly converting 70 tons of diesel into an expanding fireball that announces to everyone within 20 kilometers that they should stay out of Ukraine's swamp. But here is where things get interesting in the worst possible way for the Russians. When that jet hits the fuel car steel wall, it does not just penetrate. It literally liquefies the metal and pushes it aside like a hot knife through butter. The fuel inside does not have time to leak out slowly. It vaporizes instantly due to the heat and pressure, creating a shockwave that treats the car's structural integrity like a mere suggestion. The explosion rips through car number 4's interior at temperatures exceeding 4,000 degrees Celsius, turning the steel container into a fragmentation grenade the size of a school bus. But the real devastation comes from something Soviet engineers never anticipated when they designed these rail cars decades ago: the interconnected ventilation systems between fuel cars. What was designed for pressure equalization during loading operations now becomes a highway for destruction, allowing the fire to bypass the external walls. Within 20 seconds, burning fuel vapors have traveled through the vents and ignited cars number 3 and number 5, turning 3 separate targets into one massive rolling fire. Russian crew members finally spot the second attack drone approaching car number 8, and panic sets in. Their response is immediate and completely ineffective. They begin firing AK-74 assault rifles, sending 5.45mm rounds at a target moving 160 kilometers per hour and maneuvering in 3 dimensions. It is like trying to shoot a hummingbird with a shotgun while riding a mechanical bull. The small arms fire forces the drone into wild, evasive maneuvering, but the operator maintains control through the chaos, proving that human reflexes combined with digital stabilization are superior to panic fire. Meanwhile, the first drone's shaped charge decides to demonstrate that Ukrainian engineering is not always perfect. Instead of the clean penetration expected, the warhead achieves only partial detonation, leaving car number 4 ruptured but not completely destroyed. The operator, watching through crystal-clear fiber optic video, makes a split-second decision that is equal parts brilliant and insane. He guides the drone's burning wreckage directly into the spilled fuel, using the lithium-ion battery of the drone itself as an incendiary device to complete the job. Then physics intervenes in ways nobody anticipated. The massive fire creates its own weather system, characterized by thermal convection currents that generate updrafts and downdrafts with wind speeds exceeding 60 kilometers per hour. The third attack drone approaching car number 11 suddenly finds itself fighting hurricane-force winds generated by its own mission success. But the problems compound when the second drone's fiber optic cable snags on a railway signal post, limiting its maneuverability to a 30-meter radius. The operator now faces an impossible choice: abort the attack and waste months of preparation, or attempt a precision strike while tethered like a flying yo-yo. He chooses the latter. The locomotive engineer applies emergency brakes, but 840 tons of rolling mass does not stop on command, and normal stopping distances do not account for multiple fuel cars burning at temperatures that can melt copper. The stationary train just became an easier target in terms of speed, but the environment has become a nightmare. As car number 4 transforms into a fireball, the massive blaze creates convection patterns that turn the remaining attack runs into aerial knife fights against the air itself. The second drone operator fights cable tension, wind shear, and small arms fire while lining up his shot on car number 8. In 33 seconds, he will discover that sometimes the hardest part of precision warfare is not hitting your target. It is hitting it while everything else is literally on fire. At 0350, the third drone pilot fights convection currents rising from the burning fuel cars. Wind shear from the thermal column throws his approach off by 15 meters, forcing a desperate course correction as small arms tracers streak past his camera feed like angry fireflies. But the fire does not just create wind, it creates something else entirely that complicates the targeting solution. Massive fire smoke particles scatter laser designators and degrade visual targeting, while the heat shimmer throws off infrared sensors, making the train look like a mirage. The operator finds himself flying essentially blind, navigating by thermal signature alone through a self-generated hurricane of superheated gases. Meanwhile, the fourth drone operator faces a different nightmare: battery degradation. His quadcopter shows 18% power remaining with 90 seconds to target. Ukrainian engineers optimize these drones for endurance, but fighting wind resistance from thermal updrafts drains batteries faster than anyone calculated in the lab. He has one chance to reach the locomotive, or his drone will fall harmlessly into the countryside, becoming nothing more than expensive litter. The second drone, still fighting the snagged fiber optic cable, approaches car number 8 like a tethered falcon diving for prey. The cable tension affects thermal velocity calculations, but the operator compensates with pure flying skill. At a closure rate of 60 meters per second, he has exactly 1.3 seconds to adjust the cable drag before impact. The simultaneous strikes come moments later, sealing the fate of the convoy. Drone number 2 slams into car number 8, while drone number 3 targets car number 11, their shaped charges detonating within milliseconds of each other. The overlapping blast zones create constructive interference, pressure waves that amplify rather than cancel, turning 2 separate explosions into one sustained detonation that shakes the ground for kilometers. However, the real devastation lies in what happens next to the steel itself. The sustained fires, now approaching 1,200 degrees Celsius, begin affecting the railway infrastructure. Steel rails designed for 60-ton locomotives start warping under thermal stress that exceeds their engineering specifications by 300%. What was once precision transportation infrastructure becomes twisted metal sculptures that would be perfect for a modern art museum but are useless for moving military supplies. The fourth drone, running with 8% battery remaining, executes the mission's final strike against the locomotive engine itself. The operator has no margin for error. Miss this shot, and a $2.4 million piece of rolling stock survives to haul more fuel tomorrow. The PG-7 VL-shaped charge punches through the engine block with mathematical precision, ensuring that even if some fuel cars survive, this train will never roll again. The economics tell an even better story than the explosion. $8,000 in modified commercial drones versus $2.4 million in destroyed rolling stock, plus 840 tons of fuel worth over $600,000, plus 3 weeks of supply disruption affecting 3 armored battalions. Not even the best Wall Street hedge funds could get you a 30,000% return on investment like that. At 22:30 hours local time on July 2, 2025, a Ukrainian Vilka-M crew operating in the dark tree lines of the Donbas region believed they were the hunters, completely unaware that they had just become the prey. In exactly 6 minutes, a seemingly routine fire mission targeting a Russian ammunition depot would transform into a desperate race for survival against physics and high-explosive ordnance. The 4-man crew had positioned their launcher to strike the strategic Kartsysk logistics hub when their passive warning receivers suddenly lit up with the distinctive electromagnetic signature of a Russian Zoopark 1M counter-battery radar located roughly 38 kilometers to the east. The radar operator sitting in a comfortable command vehicle had not just detected them. His phased array system was already calculating their exact grid coordinates with a margin of error of less than 30 meters. The math was brutal and unforgiving. The Russian Smerch rocket artillery batteries linked to that radar network have a standard reaction time of just under 4 minutes. The incoming 300mm rockets would be traveling at 1,200 meters per second, meaning the Ukrainian crew had less than 360 seconds before their grid square was erased from the map by a volley of cluster munitions. The crew chief screamed for emergency launch procedures, knowing that every second spent inputting targeting data was a second borrowed from their own survival. The Vilka-M system you see here is not just a modified Soviet relic. It represents the absolute pinnacle of the Kyiv Design Bureau's indigenous engineering. Each 800-kilogram missile carries a 170-kilogram warhead designed specifically to penetrate reinforced concrete structures. But the real magic lies in the guidance package. The system utilizes a triple redundant navigation suite combining standard global positioning system signals, the Russian GLONASS equivalent, and a high-grade inertial navigation unit. This combination theoretically provides a circular error probable of just 10 to 30 meters at maximum range. That precision comes with a heavy operational cost. Under normal conditions, uploading the encrypted flight path and target coordinates from the hardened military tablet to the missile's onboard computer takes about 3 minutes. Tonight, with a Russian counter-battery radar painting their position with high-frequency energy, they had to compress that timeline into 90 seconds. At 22:32 hours, the electronic warfare environment suddenly shifted from passive monitoring to active denial. The Russian forces, realizing a strike was imminent, intensified jamming across all known GPS frequencies. The gunner's tablet screen flickered as satellite locks dropped one by one, forcing him to switch to manual input mode. Without the comfort of satellite verification, he had to trust that the pre-surveyed launch coordinates were accurate to within 5 meters. A single-digit error here wouldn't just mean missing the target. It would mean wasting a $250,000 missile while inviting a counter barrage that was already on its way. At 22:33 hours, thermal sensors on the launcher's perimeter defense system detected faint heat plumes rising from a position 32 kilometers to the northeast. The Russian Smerch batteries had fired. The physics of artillery duels are absolute. The enemy rockets were now ballistic, following a parabolic arc that would terminate at the Ukrainian crew's exact location in approximately 4 minutes. The Vilka-M's automatic loading system is a marvel of mechanics, capable of preparing and firing one missile every 20 seconds. But thermal constraints usually dictate a 45-second interval between launches to prevent the guide tubes from warping. Tonight, those safety manuals were irrelevant. They had 30 seconds. At 22:34, the first Vilka-M roared from its tube, its solid rocket motor creating a visual and thermal signature that was immediately detected by every sensor within 50 kilometers. The launch plume was a 40-meter column of fire that essentially announced their presence to the entire sector. The crew did not wait to observe the trajectory. The gunner was already authorizing the second launch sequence, while the driver frantically revved the heavy 8x8 transporter's diesel engine, preparing to displace the moment the final rocket cleared the rail. Ukrainian doctrine strictly demanded displacement within 90 seconds of the first launch, but the mission priority overrode the survival instinct. They had to empty the magazine. The second missile launched at 22, 34, and 30 seconds, adding another massive thermal bloom to the infrared picture. The Russian Zoopark radar had by now refined the launch coordinates to within a terrifyingly precise 10-meter box. and was transmitting final corrections to a second battery of Smerch launchers. The Ukrainian crew chief could now hear the distinctive sonic whistle of the incoming heavy rockets. A sound that artillerymen know means you have less than 30 seconds before impact. The third Vilka M screamed away at 22:35, the blast overpressure shattering the windows of an abandoned farmhouse 200 meters away. The launcher's thermal coating was beginning to show stress fractures from the rapid-fire heat cycling, but the machine held together. One more shot. The driver pushed the engine to 2,200 revolutions per minute, his hand hovering over the gear selector. 30 seconds later, the fourth and final missile cleared the tube just as the first Russian Smerch rocket slammed into the earth 400 meters north of their position. The ground shook violently as the 30-ton vehicle lurched forward, tearing through the underbrush while cluster submunitions bracketed the empty clearing they had occupied just moments ago. They had revealed themselves to every Russian unit within 100 kilometers, but 4 precision missiles were now streaking toward Kartsysk at 1,100 meters per second, completely indifferent to the chaos they left behind. At 22:40 hours, the lead Vilka M rocket began its descent through 8,000 meters, entering the lethal envelope of the forward Russian air defense network. The missile's onboard computer was now processing navigation updates 50 times per second while simultaneously analyzing the jamming signals attempting to corrupt its guidance. In about 60 seconds, this metal tube would either deliver its warhead to the target or become just another expensive statistic in the ongoing electronic warfare battle over the Donbass. As the rocket crossed into Russian-controlled airspace, its triple-redundant guidance system immediately detected severe degradation in the GPS signal-to-noise ratio. The jamming was intense, creating an electromagnetic wall designed to strip precision weapons of their accuracy. But the engineers in Kyiv had anticipated this exact scenario. Within 500 milliseconds of losing the satellite lock, the Vilka M's guidance computer seamlessly defaulted to pure inertial navigation. Its fiber optic gyroscopes, immune to any external jamming, continued to measure every minute change in velocity and orientation with a drift rate of less than 0.2 degrees per hour. Meanwhile, 28 kilometers ahead, a Tor M2 air defense systems combat vehicle detected the incoming threat on its surveillance radar. The operator watched his scope as the target descended through 6,000 meters at supersonic speeds, well within his engagement parameters. The Tor's fire control radar began tracking, its phased array antenna focusing 600 kilowatts of radio frequency power directly on the Vilka M's radar cross-section. Lock-on was achieved at 22:41 hours and 15 seconds. The Tor M2 represents Russia's most capable point defense system against precision munitions, specifically designed to counter threats just like this. Its missiles can engage targets from a range of 1 kilometer out to 15 kilometers, at altitudes up to 10,000 meters. The system's reaction time from detection to launch is typically between 5 and 7 seconds, with interceptors accelerating to nearly Mach 3 within 2 seconds of leaving the vertical launch tubes. Against a standard ballistic target following a predictable parabolic arc, this interception should have been a mathematical certainty, but the Vilka M was not flying predictably. At 22:42 hours, just as the Tor operator prepared to fire, the rocket's guidance system initiated a pre-programmed evasive maneuver, banking 15 degrees to the left while maintaining its descent angle. This minor course correction, undetectable to the naked eye but massive on a radar scope, moved the rocket outside of the Tor's pre-calculated intercept zone, forcing the Russian fire control computer to dump its solution and start over. The operator, perhaps out of panic or frustration, authorized an automatic engagement anyway, and 2 missiles erupted from the Tor's launch tubes 30 seconds later. The first interceptor climbed aggressively toward the calculated impact point, its radio command guidance system screaming for updates from the ground station. But the Vilka M's designers had studied Russian air defense tactics for years. At 22:42, the rocket performed yet another programmed juke, this time breaking 20 degrees to the right with a slight pitch adjustment. The maneuver added only 300 meters to its total flight path, but completely invalidated the Tor's firing solution. Realizing the first pair of missiles was destined to miss, the operator switched to manual tracking mode. His screen showed the target now at 3,000 meters altitude, 18 kilometers downrange, with impact at the depot calculated in less than 60 seconds. He fired 2 more missiles while frantically alerting adjacent air defense units. A Panzer S-1 system, located 12 kilometers to the east, acknowledged the threat and began searching its assigned sector. The second pair of Tor missiles performed significantly better, their proximity fuses detonating within 50 meters of the Vilka M. Shrapnel peppered the rocket's aluminum skin, but the warhead casing and critical guidance components remained intact. The near miss did, however, affect the trajectory. Onboard accelerometers detected a 2-degree deviation, which the flight computer immediately corrected using control canards. As the lead missile descended through 1,500 meters, the second Vilka-M entered the engagement zone exactly 30 seconds behind it. The Tor crew, fixated on the lead target, did not expect a second arrival until 22:43. They had 4 missiles remaining and 2 high-speed targets approaching simultaneously. Standard doctrine prioritized the closest threat, but engaging multiple supersonic targets maneuvering in the terminal phase exceeded the system's real-world capabilities. The Pantsir S-1 system attempted to salvage the situation, but it faced its own set of physics problems. The Vilka-M rockets were approaching from the very edge of the system's blind spot, requiring the massive turret to traverse 140 degrees while simultaneously calculating a firing solution. By the time its missiles were ready to launch, the lead rocket had descended below 500 meters, entering the terrain masking zone that made terminal interception nearly impossible. Unless the Russian operators performed a miracle in the next 60 seconds, these missiles were going to be unstoppable. At 22:49 local time, the lead Vilka-M rocket entered its terminal phase just 8 kilometers from the Kartsysk ammunition depot. 4 separate Russian air defense systems converged their sensors on the incoming threat, creating overlapping fields of radar energy that painted the sky like a beacon. The next 45 seconds would determine whether months of painstaking Ukrainian intelligence work would pay off or vanish in a cloud of failed interception debris. The Tor M2 crew had one chance left. His radar indicated that the missile was following the terrain at an altitude of 400 meters, using a small ridgeline to mask its approach. In 15 seconds, it would clear the ridge and dive toward the target. He preset his remaining missiles for the calculated pop-up point and waited, his finger hovering over the launch button. 3 kilometers south, a second Pantsir S-1 finally joined the engagement. This modern system carried 12 radio command-guided missiles, effective out to 20 kilometers. The crew had been tracking the Vilka-M since it descended below 1,000 meters, but could not achieve a solid lock through the intense ground clutter. Their phased array radar cycled through different frequencies, trying to burn through the interference caused by their own friendly jamming systems. No luck. The depot's last line of defense was a ZSU-23-4 Shilka, positioned on the facility's northern perimeter. Its 4 23mm autocannons could pump out 3,400 rounds per minute, creating a wall of lead designed to shred low-flying aircraft and missiles. The gunner traversed his turret toward the anticipated approach vector, the radar-guided fire control system, struggling to differentiate the incoming missile from the background returns of the surrounding hills. At a closure rate of 300 meters per second, he would have perhaps 3 seconds to engage before the target was inside his minimum range. At 22:49, the Vilka-M crested the ridge exactly where the Tor operator had predicted. Both remaining missiles launched instantly, their rocket motors illuminating the darkness as they accelerated toward the intercept point. The missile's altitude was now 380 meters and dropping, following a ballistic trajectory that would impact the depot in 12 seconds. The Tor missiles had 8 seconds to intercept, but the second Vilka-M rocket chose that exact moment to appear, cresting the same ridge 2 kilometers to the north. The Pantsir crew, startled by the sudden appearance of a new threat on a different azimuth, made a split-second decision that violated every page of their training manual. Instead of concentrating their fire to ensure a kill on the primary target, they split their engagement, firing 3 57 E-6 missiles at each incoming rocket. This panic-induced violation of doctrine drastically reduced the probability of a hit against either target. Their command-guided missiles, capable of reaching speeds of Mach 3, would need 8 seconds to close the distance. But splitting the fire control radar's attention between 2 maneuvering threats maneuvering in opposite directions degraded the tracking solution below acceptable limits. The lead Vilka-M's warhead was now fully armed as it passed through an altitude of 200 meters. The impact fusing circuits activated while the radar altimeter provided final height corrections, ignoring the electronic noise screaming from the Russian jammers below. Russian ammunition handlers on the ground scrambled for cover, abandoning forklifts loaded with 122mm rockets. They had been alerted 30 seconds earlier, but moving thousands of tons of volatile ordnance required hours, not minutes. At 22:50, the Tor's missiles passed within 30 meters of the lead Vilka-M, close enough for their proximity fuses to detect the target, but the relative closing speed and the extreme angle of the intercept exceeded the weapon's design parameters. Both interceptors detonated harmlessly behind the rocket as it entered its terminal dive, the shrapnel cloud failing to catch up with the supersonic projectile. The Shilka opened fire at 600 meters range, its quadruple liquid-cooled cannons filling the air with tracer rounds in a desperate attempt to create a wall of steel. The gunner held the trigger for 2.5 seconds, expending 280 rounds in a futile effort to create an impenetrable barrier against physics. The third Vilka-M appeared 20 seconds later, approaching from the east where air defense coverage was thinnest, utilizing the confusion of the first two engagements to slip through the radar net unnoticed. Across the depot, sirens wailed as personnel ran for concrete bunkers that would offer absolutely no protection from what was coming next. At 22:49 and 10 seconds, the lead missile's radar proximity fuse detected the warehouse roof 5 meters below. The warhead detonated on contact, its 170 kilograms of high explosive, creating an overpressure wave that collapsed the building's eastern wall instantly. But this was just the primer. Inside were thousands of tons of Russian ammunition about to begin the deadliest fireworks show in the Donbass. At 22:49 and 15 seconds local time, the initial explosion from the first Vilka-M warhead breached the containment of the nearest ammunition stack. Pallets of 152mm artillery shells, stacked 4 meters high in violation of safety protocols, were subjected to the blast. The shockwave compressed the air between the wooden crates, creating temperatures exceeding 3,000 degrees Celsius in a fraction of a second. Within 300 milliseconds, the first secondary explosion erupted, a chain reaction that turned the warehouse into a directed energy weapon. The second Vilka-M impacted the northern storage building 30 seconds later, its warhead penetrating the reinforced roof before detonating among crates of BM-21 Grad rockets. Each 122mm rocket contained 18.4 kilograms of solid fuel that burns at 2200 degrees when ignited properly, or explodes violently when subjected to shock detonation. The initial blast set off 600 rockets simultaneously. Their combined explosion lifted the 15-ton roof structure completely off its supports, flipping it into the air like a playing card. The third Vilka-M struck the western warehouse at 22:50 and 20 seconds, targeting pallets of 9 M22U Grad rockets equipped with advanced warheads. These weapons contained not just high explosives, but submunition dispensers designed to scatter anti-personnel mines over a wide area. The heat and overpressure caused the submunitions to detonate inside their casings, creating a devastating secondary blast that collapsed the building's structural supports. Burning solid rocket fuel sprayed across the compound like napalm, sticking to everything it touched and burning underwater. At 22:51, the spreading fires reached the depot's prize stockpile, S-300 surface-to-air missiles in storage configuration. Each 5 V-55 missile contained 133 kilograms of high explosive, plus a massive amount of solid rocket fuel in its sustainer motor. The resulting blast wave shattered windows in Kharkiv city center 3 kilometers away, registering as a minor seismic event on geological sensors across the border. Within hours, panicked orders from Moscow dispersed remaining stockpiles across multiple smaller facilities, drastically reducing logistical efficiency and increasing vulnerabilities to partisan attacks. This was exactly what Ukrainian planners intended, forcing the enemy to spend more time moving shells than firing them. At just before 3 in the afternoon on a gray Tuesday, a Russian pilot in a heavy Sukhoi fighter jet picked up a ghost on his radar that physics suggested should not exist. He was patrolling the border regions, scanning a sector that was supposed to be impenetrable. Yet 10 Ukrainian machines were currently proving that impenetrable is just a marketing term used to sell expensive hardware. These drones had slipped over 600 kilometers into hostile airspace, hugging the terrain so tightly they were practically trimming the grass. The pilot's Urbis E radar was a beast of engineering, pumping out 20 kilowatts of peak power, enough energy to cook a turkey in seconds, and capable of spotting fighter jets from provinces away. But it was designed to hunt metal giants, not these plastic phantoms. The drones had a radar cross-section barely larger than a sparrow, flickering in and out of detection like a glitch in the Matrix. Then, the pilot saw the giveaway that sealed their fate. The high-speed propellers on the drones were spinning at thousands of revolutions per minute, creating a distinct rhythmic pulse in the signal. It was an electronic heartbeat that betrayed them to the machine. Pilot did not hesitate. He flipped the switch and authorized the launch. His R-77 missiles would close the distance in a handful of seconds. In the sterile cockpit, it felt like a guaranteed kill. Down in the weeds, the drones were about to pull a stunt that would leave the million-dollar missiles chasing shadows. The moment the drones detected the lock, they did the unthinkable. They cut their engines mid-flight. Instantly, the solid contacts on the Russian radar screen vanished into the background static. The missiles were already screaming through the air at supersonic speeds, but they had effectively just gone blind. Here is the simple optical illusion that saved the aircraft. When flying at treetop height, Radar waves bounce off the ground and create a ghost reflection below the surface. To the missile's guidance brain, there appear to be two targets, the real drone and its mirror image underground. The computer has less than a blink of an eye to decide which one to hit, because the ground reflection often amplifies the signal due to the angle of incidence. The missile is frequently tricked into attacking the dirt. The first weapon slammed into an empty field, excavating a crater of useless earth while the drone floated silently above the blast. But purely passive survival was not enough. The group needed to buy a permanent exit ticket. Drone number 3 suddenly roared to life and climbed aggressively, pulling up into the kill zone. It was a deliberate suicide run, lighting itself up like a flare to draw fire away from the pack. The resulting explosion was the price of admission. One sacrifice to let 9 others vanish back into the noise. With the threat distraction successful, the remaining 9 drones restarted their motors and leveled off just above the treetops, spreading out over a wide front. The math had shifted entirely against the Russian pilot. He would need several minutes to reacquire 9 separate targets that were now scattering like marbles, and by the time he could maneuver his heavy jet, they would be miles away, lost in the ground clutter. The swarm pressed eastward, trading altitude and one of their own for safe passage through the first ring of fire, but they were flying toward a different kind of wall. Over an hour later, they entered a region of flat, featureless farmland, a navigator's nightmare where every field looks identical. This was exactly why the Russian military had parked their heavy electronic warfare assets there. The first sign of the trap was not an explosion, but a silence. The lead drone's satellite navigation suddenly reported a complete loss of signal. It was not a fade. It was a cliff. The satellites did not just get quiet, they were shouted down by terrestrial interference. The Russians had deployed a Borisogledsk 2 jamming station that was pumping out a wall of electromagnetic noise across the spectrum, turning the airwaves into a chaotic static storm. To understand the scale of this fight, you have to look at the energy economics involved. A GPS satellite signal arriving from space travels 20,000 kilometers to reach the Earth, and by the time it gets here, it is incredibly weak, whispering at the power level of a dim light bulb. The Russian jammer on the ground, however, was screaming with the power of a rock concert from just a few miles away. The difference in signal strength was massive, a ratio of millions to 1, drowning out the delicate navigation data instantly. The drones were effectively blindfolded, their satellite links severed by sheer electromagnetic brutality. But the jamming was just the fence. The guard dog was something else entirely. A Moskva-1 passive electronic intelligence unit was sitting silently nearby, listening to the radio waves with the patience of a predator. It did not transmit anything, which kept it hidden from anti-radiation missiles, but its antennas were synchronized to split-second precision via atomic clocks. It was waiting for just one drone to panic and try to call home. The geometry of passive detection is brutal and unforgiving. If a radio signal hits one antenna a fraction of a microsecond before another, a computer can calculate exactly where the sound came from based on the speed of light. It is called time difference of arrival triangulation, and it creates a death trap for anyone foolish enough to use a radio in contested airspace. The drones, however, were flying on inertial navigation, using internal mechanical gyroscopes to feel their movement without needing outside signals. It is like a blind man counting his steps to navigate a room. The problem is that these mechanical sensors drift over time due to friction and the rotation of the Earth. After hours of flying without a satellite fix to reset the system, the drones could be kilometers off course, missing their target entirely. The mission was teetering on the edge of failure as the navigation error accumulated with every passing minute. The lead drone's logic board made a calculated decision. It would trade its life for a map update. It broke radio silence for a fleeting moment, just long enough to blast out a position request and sync the formation. That split-second transmission lit up the Russian sensors like a supernova in a dark room. The Russian operators did not even need to think. The system did the work for them. They had the coordinates, and the air defense batteries unleashed a volley of interceptors almost instantly. 48 N-6 missiles accelerated to hypersonic speeds, tearing across the sky at Mach 5 to the source of the radio burst. But the lead drone was already executing the second half of its plan. It banked hard and climbed to a higher altitude, transmitting continuously on all frequencies. It was acting as a Judas goat, a deliberate distraction designed to draw the wolves away from the flock. The missiles took the bait, locking onto the screaming signal source and detonating in a sequence of airbursts that shredded the lead drone but left the empty air behind it, filled with harmless shrapnel. Meanwhile, the other 8 drones had received the navigation update just before the jamming clamped down again. They corrected their drift, confirmed their position, and continued east in total electromagnetic silence, leaving the Russians to celebrate a kill while the real threat slipped away. The Russian operators inside the Moskva-1 electronic warfare station watched the single bright target on their screens disappear in a cloud of static and assumed the threat was over. They leaned back in their chairs, confident that their layered defense had done its job, completely missing the fact that the electromagnetic silence from the east was too perfect. 8 shadows were still moving, gliding through the blind spot created by their own arrogance. They thought they were invisible, ghosts slipping through the gaps in the radar coverage, but they were about to fly into a trap that did not rely on radar or radio waves at all. As the formation crossed the administrative border into the next province, the drone flight computers throttled their engines back to a whisper, reducing the acoustic signature and sipping fuel to extend their range. The landscape below was a patchwork of forests and tree lines, perfect for concealment, but also perfect for hiding the one thing these drones were not designed to fight. Then, without any radar warning receiver lighting up, a missile erupted from a birch grove 3 kilometers to their left. There was no lock-on tone screaming in the operator's ear, no laser warning sensor triggering an alarm. Just the sudden, violent visual shock of a solid-fuel rocket motor igniting against the dark tree line. The Russians had deployed a battery of the 1B-75 penicillin acoustic reconnaissance systems, a piece of hardware that is less about electronic warfare and more about the weaponization of physics. This system does not look for metal or heat. It listens for changes in air pressure. Sound travels at a constant speed of roughly 343 meters per second, depending on temperature, and this constant is the key to the entire trap. By measuring the tiny, microsecond delays between a sound wave hitting microphone A and microphone B, the penicillin's central computer can draw a 3-dimensional map of the sky with terrifying precision. But the real danger lay in the system's digital library. Every combustion engine makes a specific noise, a sonic fingerprint defined by its cylinder count, exhaust geometry, and RPM. The system knew exactly what a Ukrainian drone engine sounded like. It recognized the specific harmonic hum of the motors from 12 kilometers away and handed the coordinates to a Tor M2 missile battery that was running in complete passive mode. The battery commander did not need to turn on his search radar and reveal his position. He just trusted the math. The missile flew silent and dark, guided only by the predicted location of the noise, effectively invisible to the drone's threat detection systems. The drone pilots had zero warning until the missile's onboard radar flicked on for the terminal kill, giving them about 2 seconds to make peace with their maker. The lead drone tried to pull a high G maneuver, snapping its ailerons to full deflection and stressing its composite airframe to the breaking point. But physics is a strict judge, and a drone moving at 200 kilometers per hour cannot outturn a missile pulling 30 Gs. The warhead detonated 40 meters away, spraying thousands of tungsten cubes through the air in an expanding cone of destruction. The heavy metal fragments shredded the carbon fiber wings and turned the aircraft into a cloud of falling debris. However, the second missile, launched just seconds later, got confused. As the remaining 7 drones scrambled to evade the invisible threat, they wildly varied their throttle settings, revving up to maximum power and then cutting back to idle. This erratic behavior changed the pitch and frequency of their engines, since the acoustic system relied on a steady, predictable tone to maintain a firing track. The sudden Doppler shifts caused the firing solution to collapse. The computer could not predict where the sound was going next because the sound itself was changing. Another missile failed because of a software bug in its proximity fuse, activating too early and exploding harmlessly above the formation. But one more drone was not so lucky, lagging behind the pack and catching a direct hit that vaporized it instantly. 6 survivors remained, pushing their engines to the red line. Stealth was gone. Now it was a drag race against the inevitable. The 6 surviving drones were now closing in on their final target, a massive industrial facility spanning 40 hectares on the outskirts of the city. To the naked eye, it was a sprawling complex of gray factories and assembly lines, humming with the activity of the afternoon shift, producing the high-tech printed circuit boards and command modules that kept the Russian war machine breathing. But just half a mile out from the perimeter, the drone navigation systems suddenly went haywire. The facility was protected by a localized Pol 21 global positioning system spoofing field, a piece of electronic warfare kit designed specifically to protect high-value static targets. Unlike simple jamming, which just blocks the satellite signal like a wall of white noise, spoofing is far more insidious because it lies to the receiver. It captures the real satellite signal, adds a tiny microsecond delay, and rebroadcasts it at a higher power level. Because the global positioning system relies on precise timing to calculate distance, that tiny delay translates into a massive error in position. The drones were suddenly being told by their navigation computers that they were 3 kilometers away, flying in the wrong direction and at the wrong altitude. The onboard computers fell into a processing crisis known as filter divergence. The optical sensors saw the target dead ahead, but the satellites insisted they were somewhere else entirely. The autopilot began to fight itself, twitching the wings and oscillating wildly as it tried to follow 2 contradictory realities. It is the robotic equivalent of schizophrenia, the sensors reporting one world while the navigation data describes another. The drone's flight control software had to make a binary choice in milliseconds: trust the satellites, which are usually the gold standard of modern navigation, or trust the internal MEMS gyroscope, which drifts over time but cannot be lied to by an external radio signal. It chose the gyro. Ignoring the screaming satellite data that demanded a hard right turn to correct a phantom error, the lead drone held its course on blind faith. It broke through the electronic haze, and the optical camera locked onto the distinctive shape of the main assembly building's ventilation units. The dive was steep and fast, converting potential energy into kinetic violence. The shaped charge warhead slammed into the roof at nearly 200 kilometers per hour, punching through the corrugated steel plating and detonating inside the main assembly hall. The blast did not just wreck the delicate machinery. It cracked open tanks of volatile industrial chemicals used in the etching process. The mixture of aerosolized solvents and oxidizers turned the air inside the factory into a massive fuel-air bomb. The subsequent explosion was hot enough to weaken the steel structural beams, causing the roof to collapse inward and sealing the destruction. The pillar of black smoke rising from the first hit became a visual beacon for the rest of the swarm, rendering the sophisticated electronic spoofing completely irrelevant. The second drone did not need navigation or gyroscopes. It just aimed for the fire. It dove into the chaos, compounding the damage and ensuring that the facility's fire suppression systems would be overwhelmed by the sheer volume of heat. The remaining drones arrived from different angles, striking the power substation and the warehouse, igniting stockpiles of lithium batteries that burned with an intense, self-sustaining heat that water could not extinguish. This phenomenon, known as thermal runaway, meant the fire created its own oxygen as it burned, melting through concrete floors. Final drone arrived late, circling the inferno once to capture the damage on camera before diving into the few remaining standing structures to ensure the job was done. In a matter of minutes, a facility critical to the production of air defense command systems was reduced to twisted scrap metal. The production line was gone, meaning the replacement parts for Russia's defensive network would now be delayed by months, leaving the door open for the next wave. Shortly after 4:30 in the afternoon on a Tuesday, a Ukrainian MiG-29 was slicing through the atmosphere over Donetsk, hugging the earth at less than 200 meters. Its destination was the strategic dam at Miryubivka, which the opposing forces had converted into a primary artery for heavy logistics. The aviator had spent the last several miles weaving through jagged geological features to stay beneath the curtain of enemy sensors. That cloak of invisibility was seconds away from being torn aside. Tucked away in the surrounding landscape, a trio of high-end Russian air defense networks already had their electronic eyes fixed on the approaching jet. A long-range S-400 system had achieved a firm lock from roughly 40 kilometers away, while a Southern Tor M2 unit and an Eastern Buk M3 began saturating the airspace with tracking energy. This concentrated wall of electromagnetic force was more than enough to turn a multi-million-dollar fighter into a cloud of falling debris before the human mind could even register the threat. The pilot kept his focus on the real-time reconnaissance data appearing on his cockpit displays, which confirmed that the dam had been repurposed as a massive crossing point for military transport vehicles. To avoid harming any non-combatants who might be nearby, the mission required an incredibly tight window for the strike, leaving no room for a secondary pass or tactical error. The jet followed the winding path of the Dnipro River Valley, utilizing the natural curves of the Earth to physically block the signals from distant search radars. Traveling at nearly 900 kilometers per hour and staying just a few hundred feet above the rushing water, the pilot relied on his solitary advantage: geography. As long as he remained deep within the shadows of the valley, the surrounding ridges acted as a shield. However, that sanctuary was about to vanish in less than 10 minutes as the terrain flattened out into wide-open farmland, turning the final 5 miles into a gauntlet of active fire. Through the heads-up display, the environment vanished in a blur as the jet covered hundreds of meters every single second. Power lines and industrial structures whipped past the canopy with such speed that they were gone before the pilot could process their shapes. He was flying on pure instinct, his body reacting to the aircraft's needs with the fluid precision of a professional athlete. This was no longer a standard navigational flight. It was a high-speed slalom where the penalty for a single mistake was becoming a permanent part of the Ukrainian soil. The cockpit was filled with the rhythmic glow of the SPO-15 radar warning receiver, which mapped out the surrounding threats on a glowing circular interface. Each strobe on the screen indicated the bearing of a hostile emitter, but left the distance a mystery, creating a feeling of being watched by a predator whose exact location in the brush remains unknown. The pilot meticulously analyzed the intervals between the radar pulses, treating the gaps like the tempo of a grim musical score to gauge the level of immediate danger. The S-400 battery to the northeast was emitting slow, steady sweeps that indicated it was still in a wide-area search mode, roughly 60 kilometers distant. When the intervals shortened to less than 2 seconds, it signaled that the system was becoming fixated on his position at a range of 40 kilometers. Once those pulses became a continuous stream, it meant a missile was likely already accelerating off its launch rail. Currently, the jet was receiving a steady rhythm of electromagnetic attention from less than 30 kilometers away, a distance that provided just enough time to react, but left very little room for hesitation. This data forced the pilot to commit to a low-altitude sprint for the next several minutes of the mission. While navigating these threats, the pilot monitored the automated status of the precision-guided hammer bomb attached to the center pylon of the aircraft. Every few heartbeats, the weapon's internal computer performed a self-diagnostic check, confirming that it was receiving a strong signal from nearly a dozen global positioning satellites, while its internal inertial sensors remained perfectly calibrated. The rocket-assisted bomb was armed and ready for its terminal dive, but it required very specific altitude and speed parameters to reach the dam. Those conditions were impossible to meet while skimming the treetops at 200 meters. However, obsessing over the final release now was like worrying about the landing gears while the engines were struggling to stay ignited. The immediate goal was to survive the approach through a corridor of active missile batteries before attempting to deploy a high-tech weapon from a jet built decades ago. The fuel situation added another layer of pressure to an already saturated environment, as the gauge showed just over 2,000 kilograms of kerosene remaining. With the return journey to a safe airfield measuring nearly 150 kilometers, the pilot had a window of less than 20 minutes to loiter over the target before his fuel state became critical. The twin RD-33 engines were notoriously hungry at these low altitudes, consuming fuel with the intensity of a blast furnace during a winter storm. Any sudden defensive maneuver, use of the afterburner, or climb into the thinner air would rapidly drain his remaining reserves. The loitering drone near the objective reported that the dam was currently clear of civilian traffic, and no hostile interceptors had been detected in the immediate vicinity yet. The pilot nudged the throttles forward, knowing that every second saved was a second he wouldn't have to spend as a target. At exactly 16:38 hours, the jet crossed the boundary where the river valley gave way to the open plains, and the cockpit immediately erupted in a wall of sound. The radar warning receiver transitioned from rhythmic chirps to a frantic screech as half a dozen different emitters simultaneously found the aircraft. The S-400 that had been searching the horizon suddenly focused its energy into a narrow, lethal beam. The MiG had gone from being a ghost in the terrain to the most visible object in the sky in less time than it takes to blink. The Gravestone radar achieved a high-fidelity lock from nearly 40 kilometers away, turning the intermittent tones in the pilot's ears into a solid, unwavering scream. This sound meant that the ground crews had finalized their firing solution, and the automated systems were seconds away from initiating a launch sequence against him. The aircraft is covered in small sensors that detect the specific invisible energy of a radar beam hitting the fuselage. When that energy arrives in a continuous, focused stream, the jet knows it is being tracked for a kill rather than just being searched. The SPO-15 system can even identify the unique digital fingerprint of the radar, allowing the pilot to recognize the voice of his attacker. Right now, the jet was telling him that the most advanced long-range system in the region was staring directly at him. While the theoretical range of the 48N6 missile was hundreds of kilometers, the curvature of the Earth and the jet's low altitude limited the effective engagement range to roughly 40 kilometers. At 38 kilometers, the pilot was deep inside the lethal zone. He immediately threw the jet into a violent knife-edge turn, subjecting his body to intense gravitational forces while trying to stay below the horizon line. This sharp maneuver was designed to put the aircraft's path perfectly perpendicular to the incoming radar beam, a tactic known as beaming. By moving at a 90-degree angle to a Doppler radar, the jet's relative speed toward the sensor becomes zero, making it look exactly like the stationary ground beneath it. Modern radar computers are programmed to ignore objects that aren't moving toward or away from them to filter out hills and buildings. By mimicking a mountain, the pilot was able to momentarily break the electronic lock, though the move cost him a massive amount of speed and left him heading away from his objective. The relief was short-lived, however, as a Tor M2 system suddenly activated just 5 miles to the south. This system utilized command guidance, meaning the ground radar steered the missile manually, rather than letting the missile think for itself. You cannot easily jam a weapon that is being puppeted from the ground, as the instructions are sent over a high-speed data link in fractions of a second. The only way to escape such a system is to move faster than the radar can track, or to dive so low that the signals are lost in the clutter of the earth. The pilot rolled the jet over and plunged toward the soil, dropping from 150 meters to just 50 meters above the fields. Trees and farm equipment whipped past the canopy, hardly higher than a tall pine tree. While diving, he triggered the countermeasure system, releasing a massive cloud of aluminum-coated fibers into the air behind him. These fibers were cut to precise lengths to interfere with the specific wavelengths of the S-400's tracking energy, creating a glittering electronic decoy that looked like the jet was expanding into a massive cloud on the enemy screens. However, the smaller Tor system operated on a different frequency, requiring a second set of shorter fibers to be effective. The pilot deployed the additional chaff, creating a corridor of interference that allowed him to vanish into the background noise of the radar returns. To further complicate the enemy's task, he activated his internal jamming pod, which analyzed the incoming signals and broadcasted a fake version of the jet back toward the sensors. This technique, called range gate pull-off, creates a digital ghost on the Russian operator's screen that slowly drifts away from the real aircraft. Like a mirror in a dark hallway, the radar's automated systems are drawn to the brighter fake signal, allowing the real MiG to change course undetected. The operator would see the jet apparently climbing and turning, while in reality the pilot was still skimming the wheat fields in a completely different direction. Flying at 50 meters at such extreme speeds meant the pilot was operating on borrowed time, as a single power line or a slight dip in concentration would end the mission in a catastrophic collision. The release point for the precision bomb was now less than 5 miles ahead, and the pilot had to transition from a defensive posture to an offensive one. He decided to abandon stealth in favor of absolute chaos, figuring that if he forced every battery in the area to engage him at once, their coordination would break down. He prepared to throw a deck of cards into the wind turbine, intending to use the resulting confusion as his primary shield. He checked his fuel one last time, seeing just over 2,000 kilograms remaining. The next 60 seconds would decide if he became a headline or a casualty. With a firm grip on the controls, he prepared for a maneuver that would push the airframe to its breaking point. At exactly 1640 hours, the aviator slammed the throttles into full afterburner and pulled the nose of the MiG-29 straight toward the clouds. The twin engines erupted with massive power, turning the jet into a brilliant flare that was visible for miles in every direction. He had spent the last few minutes hiding, but now he was intentionally broadcasting his location to every sensor in the region. Inside the enemy command vehicles, operators watched in shock as the target transformed from a flickering ghost in the ground clutter to a bright vertical climb. The fire control computers struggled to keep up with the rapid change in altitude as the jet rose through thousands of feet in mere seconds. The S-400 battery commander authorized a launch, and 2 massive missiles roared off their rails, their seekers already hungry for the heat and radar return of the climbing jet. The physical strain of the climb was immense, as the pilot rose toward 5,000 meters in less than 20 seconds, while being crushed into his seat by 4 times his own body weight. His G-suit pulsed against his legs, forcing blood toward his brain to prevent a total blackout. At these extreme gravitational forces, the human eye begins to lose its peripheral vision, turning the world into a narrow tunnel of gray. He was riding the thin edge of his consciousness, using every bit of his physical endurance to buy the altitude he needed for the strike. To make himself a harder target for the incoming missiles, he added a barrel roll to the vertical climb, tracing a massive corkscrew through the sky. This non-linear path made it nearly impossible for the enemy computers to predict where he would be in the next several seconds, forcing them to constantly reset their intercept calculations. To the operators on the ground, the jet's path looked like a drill bit spinning through the air at supersonic speeds. Because fire control systems rely on predicting a steady ballistic path, the erratic spiraling caused the intercept point to dance around the screen without settling. 3 different batteries were now locked on simultaneously, filling the cockpit with a wall of sound that most pilots only hear in their worst nightmares. In response, the pilot rolled the aircraft completely upside down at the peak of his climb and pulled the nose back toward the ground, He was now inverted at 5,000 meters, peering through the top of his canopy at the dam below. The weapon system confirmed that the hammer was ready for release. As the weapon's release light glowed green, the pilot depressed the trigger, and the 500-pound bomb departed from the aircraft with a metallic jolt. The jet immediately felt lighter, responding with newfound agility as the heavy burden fell away. However, there was no time to celebrate the successful deployment, as the radar warning receiver continued to wail, signaling that multiple long-range missiles were now closing in on his last known location at several times the speed of sound. With hostile interceptors less than 20 seconds away, the aviator threw his jet into a vertical plunge, aiming the nose directly at the farmland below. He pushed the airframe to its absolute breaking point, pulling nearly 10 times the force of gravity to change his trajectory before the S-400 missiles could adjust their lead pursuit. The physical toll was massive. His vision blurred at the edges as the blood was pulled from his brain, and the airframe groaned under the immense stress of the turn. He pushed the jet through the sound barrier, the transition marked by a violent shudder that shook the cockpit as shock waves hammered the wings. The massive Russian missiles, unable to follow such an erratic and sudden dive, lost their lock and self-destructed high above, leaving the MiG to vanish into the shadows of the horizon. While the jet made its daring escape, the hammer bomb was just beginning its own mission. The internal rocket motor ignited with a brilliant flash, pushing the weapon toward an altitude of 8,000 meters, while the pilot sped away in the opposite direction. This clever design allowed the bomb to trade its rocket-assisted speed for height, giving it the vertical vantage point needed to scan the area for its target. The internal computer was now in total control, using a combination of satellite navigation and a sophisticated infrared seeker to stay on course. As it reached the peak of its climb, the bomb tipped forward, gravity and its aerodynamic fins guiding it into a steep, terminal dive toward the concrete structure below, which now sat defenseless against the incoming strike. In a moment of profound electronic confusion, the Eastern Buck M3 battery mistakenly locked onto the high-flying bomb instead of the escaping fighter jet. The Russian operators, desperate for a kill, launched a high-priced interceptor that cost nearly $1 million to chase a target that was already essentially a falling rock. This maneuver proved to be a massive waste of resources, as the interceptor struggled to track a small, non-evasive object that was moving according to the laws of physics rather than pilot input. To the ground crews, it appeared as if they were successfully engaging a target, but they were merely shooting at a bullet that had already been fired. This diversion provided the pilot with the final few seconds he needed to reach the safety of the river valley, while the hammer continued its descent, its internal thermal camera now locking onto the heat signature of the dam with unwavering mechanical focus. The thermal seeker on the nose of the bomb was now processing images at an incredible rate, searching for the specific temperature profile of the Miryubivka Dam. Because the concrete had spent the entire day absorbing heat from the sun, it glowed brightly in the infrared spectrum compared to the much cooler water flowing beneath it. This stark contrast made the target look like a glowing white stripe against a dark background, a signature that no amount of smoke or camouflage could hide. The bomb's computer analyzed the shape, ensuring it matched the architectural blueprint stored in its memory, and made a series of tiny adjustments to its flight path. Each movement of the control fins was smaller than a human fingernail, yet they were enough to shift the impact point with surgical accuracy. It was now traveling at over 300 meters per second, a velocity that turned the weapon into a kinetic hammer, even before its explosives were triggered. As the weapon entered the final few hundred meters, its intelligent fuse prepared for the impact. This was not a simple contact trigger. It was designed to penetrate deep into the reinforced concrete before detonating, ensuring the maximum possible structural damage. In the time it takes to blink, the bomb struck the center of the dam, its hardened casing slicing through several feet of solid material before the high explosive core was ignited. The resulting explosion generated a pressure wave of over 300,000 pounds per square inch, a force so massive that it pulverized the concrete into dust before the rest of the structure could even begin to collapse. The Ukrainian drone operator, loitering at a safe distance, captured the entire event in high-definition detail, watching as a 60-meter gap opened in what was once a vital military crossing. The wall of water rushing through the breach began to rapidly erode the remaining supports, ensuring that no simple repair could restore the logistics route. This single strike effectively severed the Russian supply line, forcing their transport units into a massive detour that would delay reinforcements for weeks. The economics of the mission were staggering. A single precision-guided bomb had neutralized a strategic asset worth hundreds of millions of dollars, while disrupting the operations of several armored battalions. As the dust and water spray settled, the drone began its return flight, leaving behind a shattered landscape and a permanent gap in the enemy's defensive plans. The mission was a total success, accomplished in less than half an hour from takeoff to impact. At 2:47 p.m. on a sweltering afternoon in the Kherson region, the Ukrainian attack helicopter pilot made a decision that seemed to violate every survival instinct written in the Manual of Combat Aviation. The Mi-24 Hind, a 10-ton flying tank, descended from the relative safety of altitude to fly low and slow straight into the engagement zone of a known Russian missile team. To the Russian operators watching through their optics, this looked like a suicide run, or a pilot who had completely lost his bearings, as the aircraft was practically begging to be shot down. The helicopter's approach over the quiet Oleski sector raised immediate questions for anyone familiar with the current frontline dynamics, as this area had seen minimal activity for months, mostly limited to sporadic artillery exchanges and drone reconnaissance. Yet here was a high-value gunship, fully loaded with 4 B-8V rocket pods, crossing into contested airspace at a dangerously low altitude where its armor offered little protection against modern air defense systems. On board, the weapon stations were packed to capacity with 80 S-8 unguided rockets, turning the aircraft into a flying magazine capable of leveling a city block. These 80mm rockets weigh 11.7 kilograms each and carry a 1.1 kilogram warhead capable of penetrating 400 millimeters of rolled homogeneous armor. But seeing a helicopter loaded with this much heavy ordnance in a sector with no active armored columns or fortified positions is like seeing an NFL linebacker show up to tackle a toddler. It did not make any tactical sense to the Russians on the ground. But in modern warfare, if your enemy is making a mistake that seems too good to be true, it is usually because you are the one about to fall into a trap. The Russian man-portable air defense system team, positioned in the ruins of an industrial building approximately 3.2 kilometers away, had been tracking the acoustic signature of the rotors for the past 4 minutes. This two-man team operated the 9K-38 Igla surface-to-air missile system, one of the most capable weapons in the Russian inventory for engaging low-flying targets. The system is a marvel of Soviet engineering designed to kill exactly this type of helicopter, weighing 17.9 kilograms when ready to fire and launching a 1.5-meter-long missile. The missile itself carries a 1.17 kilogram warhead containing 390 grams of high explosive, which is more than enough to shred the engine signaling of a Hind and turn the aircraft into a falling collection of burning scrap metal. However, the explosive yield is not the primary concern for the pilot. The real danger lies in the nose of the weapon. The 9M39 missile utilizes a cooled infrared seeker head that represents a significant leap forward from earlier generations like the Strela. By using a coolant system to lower the temperature of the sensor, the engineers significantly reduced background thermal noise, allowing the seeker to differentiate between the intense heat of an aircraft exhaust and the background radiation of the Earth, or at least that is how it works in the brochure. The engagement initiates when the Ukrainian pilot rolls the heavy gunship into an attack dive and unleashes all 80 rockets in a devastating ripple fire sequence that lights up the sky. The rockets streak toward the ground at 610 meters per second, but instead of converging on a specific bunker or tank, they spread across a massive 500-meter wide impact zone in what looks like a complete failure of aiming discipline. Many of the rockets splash harmlessly into the Dnipro River, sending up useless geysers of water, while others impact empty fields, churning up mud and destroying nothing but local vegetation. To an untrained observer, this appears to be panic fire or area suppression gone wrong, seemingly wasteful use of expensive munitions in a sector that did not require it. But this 500-meter spread pattern serves a specific physics-based purpose that the Russian operators failed to recognize in the heat of the moment. Not only does the barrage suppress a wide area, forcing heads down, but more importantly, it creates a massive thermal event. 80 rocket impacts create 80 separate heat sources on the ground, raising the ambient thermal signature of the entire sector. The pilot is not trying to hit a target. He is trying to paint the background with fire to confuse the sensors that are about to look for him. The Russian team follows their training manual to the letter, driven by the rigid doctrine that has defined Soviet and Russian air defense strategy for 50 years. The doctrine mandates the immediate engagement of any hostile aircraft that enters the Igla's 5.2-kilometer operational range, regardless of the broader tactical picture. The gunner checks his weapon parameters one final time, confirming that the target is valid. The Igla can engage targets traveling at speeds up to 800 meters per second and at altitudes up to 3.5 kilometers, meaning the Ukrainian helicopter, which is flying low and bleeding airspeed during its attack run, is deep inside the kill envelope. The gunner aims northeast, an angle that reveals a crucial detail that should have stopped him cold. The helicopter has deliberately crossed the river into occupied territory, placing itself in danger for no apparent strategic gain. The Oleski area offers no troop concentrations worth this risk, and the Igla's range would not have been able to reach the helicopter if it had stayed on the Ukrainian side of the river. The pilots effectively brought the target to the weapon, a tactical anomaly that should have triggered alarm bells in the gunner's mind. But the sight of a massive Hind gunship offering its broadside is a tempting target that overrides common sense, proving that the desire for a confirmed kill often outweighs tactical caution. At precisely 2:48 p.m., just as the last of the S-8 rockets impact the mud below, the Russian operator squeezes the trigger mechanism on the gripstock. The Igla's infrared seeker has successfully locked onto the distinctive thermal bloom of the Mi-24's exhaust ports, and the missile's solid-fuel rocket motor ignites with a blinding white flash that is visible for kilometers. The missile accelerates off the rail, reaching a velocity of approximately Mach 1.9 within seconds, streaking toward its target with the cooled infrared seeker maintaining a steady lock despite the interference from the afternoon sun. Inside the cockpit, the Ukrainian pilot's SPO-15 Berioza radar warning receiver immediately screams to life, though the pilot's calm reaction suggests he was already watching the launch plume. The SPO-15 is an older but reliable system that operates across multiple frequency bands from 0.6 to 17 GHz, detecting the electromagnetic emissions from hostile radar systems and missile seekers. The system utilizes 4 antennas positioned around the aircraft airframe to provide 360-degree coverage, calculating the bearing of the threat with roughly 15 degrees of accuracy. The warning system does not just detect threats, it prioritizes them on a 16-light emitting diode display that shows both the bearing and the relative threat level, while generating specific audio tones for each category of danger. A continuous 800 Hz tone would indicate a radar lock from a vehicle like a Pantsir or Tor system, while a pulsing 1,600 Hz tone warns specifically of a missile launch. In this instance, the distinctive high-pitched pulsing tone at 1,600 Hz confirms an infrared missile launch, which is exactly the signal the pilot was waiting for. Banking the aircraft hard to the left to mask the engine exhaust with the fuselage, the pilot simultaneously deploys countermeasures. The helicopter's UV-26 countermeasures dispensing system, mounted on the fuselage, ejects a precise pattern of 12 infrared flares in rapid succession. These flares utilize magnesium and Teflon pellets to burn at temperatures exceeding 2,000 degrees Celsius, creating intense infrared signatures designed to seduce the incoming missile away from the engine. The timing of this countermeasure deployment turns the battlefield into a thermal nightmare for the incoming missile's guidance computer. In this instant, the seeker head is looking at a scene of chaos. Below the helicopter, 80 exploding rockets have created a wall of heat signatures on the ground, igniting dry grass and fuel residues. Above the helicopter, 12 fresh flares are blooming like miniature suns, burning hotter than the engine exhaust. The missile seeker, which was designed in the 1980s to track a single hot target against a cold sky, is suddenly facing dozens of competing high-intensity infrared sources. It is the electronic equivalent of trying to identify a single specific candle in a room where someone just set off a box of fireworks. The seeker logic lacks the modern algorithms required to discriminate between the kinetic heating of the flares and the exhaust gas of the turbines. Confused by the sudden proliferation of targets, the missile loses its lock on the helicopter, and logic gates select the brightest heat source available, guiding the weapon into a cluster of burning rocket impacts 150 meters away from the aircraft. The missile streaks harmlessly past the Ukrainian helicopter, close enough for the crew to see the smoke trail, but far enough to avoid damage from the fragmentation warhead. The missed shot was always the expected outcome of this engagement, but the Russian team does not realize that the missile was never the point. By firing their weapon, the Russian Manpads team has effectively signed their own death warrant. The launch signature of the Igla is a brilliant infrared plume that is visible to multiple sensors across the battlespace, pinpointing their exact position in the ruined building. Ukrainian signals intelligence systems immediately triangulate the launch location by combining the thermal detection of the missile motor with the sudden spike in electromagnetic emissions from the team's radio communications as they report the engagement. This 90-second window for signal processing represents a revolution in battlefield awareness. In previous conflicts, identifying a firing position, processing the coordinates, and transmitting them to a strike asset might take 15 to 30 minutes. But Ukrainian forces have compressed this timeline through integrated software and Starlink connectivity. By the time those 90 seconds expire, the targeting data has already been formatted and transmitted to a waiting FPV drone operator positioned 8 kilometers away. This operation highlights a fundamental evolution in helicopter tactics that has emerged from the necessities of this war. Rather than avoiding air defense systems by hugging the terrain, Ukrainian pilots are now deliberately exposing themselves to draw fire, functioning as the bait in a complex hunter-killer loop. This acceptance of risk doctrine represents a complete reversal of traditional helicopter employment, where the aircraft is usually the protected asset. Instead, the pilots act as a lure, trusting in their flares and the limitations of Russian seekers to survive the encounter, all to achieve the greater goal of eliminating the enemy air defense network piece by piece. It is a calculated gamble that traditional military academies in the West would never teach, but it is proving devastatingly effective in an environment saturated with anti-air weapons. The acceptance of calculated risk transforms the Mi-24 from a potential victim into an active participant in the suppression of enemy air defenses, turning the hunters on the ground into the hunted. The Russian team begins their standard post-engagement procedure, completely unaware that an 8-minute countdown to their elimination has started. Soviet doctrine calls for immediate relocation after firing to avoid counter-battery artillery fire. In the Cold War era, this shoot-and-scoot tactic provided reasonable safety because enemy response times were measured in tens of minutes or even hours. However, the Russian team is slowed down by the physical reality of their weapon system. The 9K-38 Igla, while technically man-portable, requires several critical steps to properly stow before it can be moved. The missile's launch tube must be disconnected from the grip stock assembly to be carried effectively. The battery coolant unit, which is now expended and hot, must be safely removed and disposed of to prevent chemical burns. The thermal battery that powered the Seeker needs removal. Each component must be secured in its canvas carrying case for transport, a process that takes between 4 and 6 minutes under ideal conditions. But the conditions in the Dnipro River Delta are far from ideal. The summer rains have turned the ground around the building into thick, viscous mud that clings to boots and equipment, adding friction to every movement. Building that provided concealment and a stable firing platform now becomes a trap, as the team must navigate debris and damaged stairs while carrying nearly 18 kilograms of awkward equipment. This vulnerability window during the pack-up phase is a critical weakness that Ukrainian forces identified early in the conflict. During these few minutes, the crew is suffering from task fixation. They are looking at their equipment, managing the disassembly, and watching their footing, which means they are not scanning the sky for new threats. The distributed nature of Ukrainian operations has enabled the rapid exploitation of this window. The drone operator receives coordinates directly from signals intelligence and can engage without waiting for a battalion commander to sign off on the strike. This flat command structure compresses the decision cycle from 30 minutes to under 2 minutes, allowing the strike to be launched while the Russians are still struggling with their launch tubes. At 2:54 p.m., just 6 minutes after the failed missile engagement, the Ukrainian drone enters the final approach corridor, undetected by the very radar systems designed to protect this airspace. This is not a military-grade Predator or a high-altitude Bayraktar. It is a 7-inch carbon fiber quadcopter frame, likely assembled on a kitchen table in Kyiv for less than $500. The drone is running the Express LRS radio protocol at 915 MHz, a packet-based high-frequency link that hops channels 150 times per second to punch through the heavy electronic interference that usually grounds commercial drones in this sector. The operator, sitting safely in a bunker 8 kilometers away, views the world through the grainy, flickering static of an analog 5.8 GHz video feed. While civilian enthusiasts prefer high-definition digital video, combat pilots prefer analog for one simple reason known as latency. Digital systems have a variable delay of 30 to 40 milliseconds as they encode the image. Analog is effectively instant. When you are flying a kinetic kill vehicle at 140 kilometers per hour, that 30 millisecond delay is the difference between hitting the target and burying your drone in the dirt behind it. The drone hugs the terrain at an altitude of just 15 meters, staying well below the radar horizon of the Russian Pantsir systems scanning from the rear, effectively using the Earth's curvature as a shield. Its electric motors, spinning at 30,000 revolutions per minute, produce no thermal exhaust for infrared sensors to track and its plastic propellers absorb rather than reflect radar waves, giving it the radar cross-section of a sparrow. Through the first-person view goggles, the operator observes the two Russian soldiers still at their firing position, locked in a desperate struggle against the terrain itself. The operator checks his on-screen display. Battery voltage is sagging to 3.5 volts per cell under the load of the high-speed cruise, giving him exactly 90 seconds of flight time remaining before the lithium polymer battery hits critical cutoff. He pushes the throttle to 80%. The Russians are fighting the mud of the Dnipro Delta, a thick, clay-like substance that creates a suction effect on standard-issue military boots, requiring significant physical exertion for every step. They are attempting to move the 17-kilogram Igla launch unit and its associated battery coolant cases, gripped by the psychological phenomenon of sunk cost fallacy. They know they should run, but their training mandates they save the expensive equipment, pinning them to the X marks the spot. They are completely task-saturated, their auditory processing filtered out by the sound of their own heavy breathing and the squelch of mud, leaving them deaf to the high-pitched frequency of the approaching motors. Physics dictates that high-frequency sound waves attenuate or lose energy much faster over distance than low-frequency rumbles. This means that while you can hear a tank from kilometers away, you will not hear an electric drone until it is within a 200-meter radius, usually giving you about 4 seconds of actionable warning. At 2:55 p.m., 7 minutes after firing their missile, the acoustic equation changes instantly for the Russian team. The drone pilot initiates his terminal dive, pushing the pitch stick forward and dropping the altitude to 3 meters off the deck. As the drone accelerates past 100 kilometers per hour, the sound of the propellers shifts from a distant mosquito whine into the aggressive buzz of a chainsaw. The distinctive sound triggers a primal Pavlovian response in the soldiers, a reflex carved into them by months of watching videos of their comrades being hunted. One soldier looks up, his eyes widening as he spots the small black silhouette rapidly growing larger against the gray sky. But the geometry of the engagement is already fatal. In the confined space of the ruined building's courtyard, surrounded by knee-deep mud and debris, the human reaction time of 0.25 seconds is simply not fast enough to overcome the inertia of the heavy equipment they are holding. To drop the gear, turn, and generate enough friction in the mud to sprint to cover would take at least 3 seconds. They have less than 1. The operator maintains a steady lock through the analog camera feed, fighting the prop wash turbulence generated by his own aggressive maneuvering. He makes a final micro-adjustment to the yaw axis, lining up the crosshairs not on the men, but on the space directly between them to maximize the fragmentation radius. The drone's path is true, guided by a human hand but powered by the cold certainty of mathematics. 8 minutes ago, these men fired a $40,000 missile at a $12 million helicopter, thinking they were the apex predators of this sector. The drone impacts the muddy ground between the two soldiers at 42 meters per second. The payload is not a complex factory-made warhead, but a 1.5 kilogram block of plastic explosive wrapped in a fragmentation sleeve made of simple ball bearings or chopped steel rod. The trigger is a pair of exposed copper wires in front of the camera that complete the circuit upon physical contact. The detonation velocity of the explosive exceeds 8,000 meters per second, transforming the metal casing into a localized storm of high-velocity shrapnel that shreds the soft tissue of the operators and the delicate electronics of the Igla system with equal indifference. The explosion ensures that there is one less air defense team capable of threatening the airspace, but the physical destruction is only half the victory. Within hours, intercepted communications reveal a wave of paranoia spreading through the Russian air defense network. Every team in the sector now knows that firing their weapon is essentially firing a flare gun that summons a hunter-killer drone. This psychological suppression achieves what kinetic weapons alone cannot: